AWS Serverless Computing. Cloud computing now offers the opportunity for you to launch your functions and applications using what they call a serverless model. So the AWS cloud acts as the server. It'd be crazy to think that there would be no servers involved. There are still servers, but you don't have to worry about them in this model. The AWS cloud acts as the server, and the responsibility of the server and patch management, these kind of things, are now the responsibility of AWS. Its pricing scheme is based on resources, so you only pay for the resources that your function invokes and uses. Charges are built around the number of requests for your functions and the duration of time, rounded to the nearest 100 milliseconds. So the time that it takes for your code to run, the price is then determined based on the memory you assign to your function, and you can choose like the memory and CPU power amongst other resources. So these resources will be determining your Lambda bill. There is a free tier though that includes 1 million free requests per month and 400,000 gigabyte per seconds of compute time per month, which is quite a bit of time if you want to get in and get your feet wet. Previously, it was always done via the local computer model. So the traditional model, we had local servers, they executed our functions, and they did it well. That said, there are some issues with this model, such as infrastructure costs. Servers cost money, installation takes time and money, and if you want to scale up, you need to repeat the whole process again. You also need to be concerned about patch management on these servers, and this is time-consuming, can be a big part of one person's job alone. So by moving to the serverless model, you rid yourself of these concerns. AWS Lambda. AWS Lambda is the AWS Serverless Compute platform that enables you to run code without provisioning or managing servers. It's a simple pay-per-use model where you can trigger and execute your function or script on demand and just pay for what you use. And this involves zero administration. AWS Lambda supports many different types of code, and all you have to do is upload it. You write a function or a script in a language like PHP or Python or Node, and then you can associate a trigger that will invoke that function on demand whenever you need it to run. That trigger could be an HTTP endpoint or a file being uploaded to an S3 bucket. Lambda is sometimes referred to as what they call function as a service, or FaaS. AWS Serverless Computing. So where do the servers go? Well, they still require servers. But the servers are hidden, and management and planning are hidden from you. So it's no longer of a concern of yours. This is now AWS's responsibility. You can use serverless code in conjunction with microservices. In contrast, you can also write applications to be purely serverless and use no provision servers. AWS Lambda uses containerization to run your code. So containers created each time your function is triggered. Your code then executes in that container. So if a container is created on the first run, AWS refers to this as a cold start. When you set your container to run, it'll remain active or warm for several minutes before it shuts down. This allows to multiple function triggers in a small period of time without having to cold start a container each time. Right? So it's faster, it's more efficient. By default, AWS Lambda runs containers inside the AWS environment and not within your personal account or your personal VPC. However, you can run AWS Lambda inside your Amazon VPC if you wish to configure the permissions necessary to do so. Microservices. Microservices are an architectural approach to software development, whereby monolithic applications are now being replaced with small, decoupled services that communicate via APIs. This allows us to be more agile, as our big application is now divided up, meaning we can update different parts of the application at different times. And now our scaling is much more flexible. We don't need to scale all parts of our application at once. we can now only scale the parts we actually need to. So maybe we had a queue running in our application and we need to scale it up. If this was one behemoth monolithic application, the whole application would be scaled up to meet the needs of that one queue. This is inefficient. So with microservices, we can scale just the queue portion of the application. We can also deploy code faster than we ever did before. This is in a big contrast to that monolithic application we talk about, where all processes are coupled and rely on one another for the application to run as intended. AWS Lambda. Lambda allows us to write our functions and trigger them and let them run in a serverless architecture. So what type of code can we write our Lambda functions in? We can write our code in C#. We can write our code in the Go language. We can write it in Java. We can write it in Node.js, and we can write it in Python. So how do we go about creating an AWS Lambda function? Where can we access this AWS service? Well, we can access it via the AWS Management Console, which we can access via our web browser and gives us a good graphical user interface to use. We can also access via the AWS command line interface. This can be either on Windows PowerShell, Windows command line, or Linux shell. We can also take advantage of AWS SDKs for Java, Node.js, PHP, .NET, and Python to create our Lambda functions. And we can also use AWS APIs, such as sending HTTP or HTTPS requests. When you create a Lambda function, you have three options. You can author it from scratch, so you're manually creating all the settings, all the options, all the code, right? It's completely yours from scratch. You could also use a pre-configured template that you can modify. These are known as blueprints. A lot of people are running the same functions or have the same idea, so a lot of times you don't have to reinvent the wheel. Take advantage of these blueprints. And you also have the serverless application repository. You can deploy a publicly shared application that is shared on the AWS SAM, or the serverless application model. These are all the options you can have. If it's something really custom, you may want to go from scratch. If it's something that needs a little bit of tweaking, you can probably use a blueprint for. And if it's something that's a direct copy of something else that's publicly shared, then you can go ahead and use the serverless application repository. When we create our functions from scratch, there are three details that we deem necessary, that require. The first will be the name of your function. So if you want to keep in best practices, name the function based on what it's doing. So you can look at the name and see exactly what that function is doing. So this is required. We need the name of the function. We also need the runtime of the function. So what language is this written in? Is it Node.js? Is it Python? All right, so this information needs to be supplied. And we also need a role. So we need the permissions to give to the function. So we assign an IAM role, and our functions can assume the permissions in that role and have access to other AWS resources. So how do we invoke an AWS Lambda function? There are two invocation models for AWS Lambda. First, you have your non-streaming event source, or the push model. This is used by services like Amazon Echo, Amazon S3, Amazon Simple Notification Service, right? These are used when it's non-streaming data. In contrast, we also have a streaming event source, or the pool model. These will be used with things like Amazon Kinesis or Amazon DynamoDB streams when we're dealing with data as stream. It's also important to know that Lambda allows you to execute a function either synchronously or asynchronously. So when we set up our function, the invocation type parameter is what tells Lambda when to invoke a function. Right? So we need this invocation type parameter to tell it should you run it synchronously or should you run it asynchronously. So if you use the request response value, that's synchronous. So basically Lambda executes the function, then we'll wait for a response. If you supply the event value, that's an asynchronous execution. Lambda will queue the events, then a separate process will read the events from the queue and send them to the function. And finally, you have a dry run. So this is just a test, right? We test our function to make sure it does what we want. And if there's any issues, we can work them out before we actually call it in production and actually move some pieces around and get a real trigger. So these are the way you need to invoke Lambda, asynchronously or synchronously. But again, it depends on these parameter values of the invocation type parameter. How do we deal with permissions in AWS Lambda functions? AWS Lambda functions include two types of permissions. First, we have execution permissions. These are necessary so the Lambda function can access other AWS resources in our account. This could be an S3 bucket, for example. If the function needs access to the S3 bucket, the AWS IAM role that we assign to our function has the access to that particular S3 bucket. So when the function launches and needs access to the S3 object, permissions are granted through that role. Lambda refers to this as an execution role. We also have invocation permissions. So these are the permissions that an event source needs to talk to your Lambda function. When dealing with a push invocation method, you can update the access policy you associate with your AWS Lambda function. And if you're dealing with a pull invocation method, update the execution role. AWS Lambda also provides built-in permission policies. The first built-in permission policy we'll discuss is the Lambda basic execution role. This is to be used if your application is only used to write logs and will not access any other AWS resource in your account. This role will grant permission only for Amazon CloudWatch log actions to write logs. We also have the Lambda Kinesis execution role. This policy is needed if you're integrating Lambda functions with Amazon Kinesis streams. This function will grant permission for Amazon Kinesis data streams and Amazon CloudWatch log actions. The Lambda Dynamo DB execution role, much like the Kinesis execution role, this policy is needed if you're integrating Lambda functions with an Amazon Dynamo DB stream. And finally, the Lambda VPC access execution role. So if our function needs to access resources inside of our VPC, like an EC2 instance, then we need to attach this policy. This policy will grant permissions for EC2 actions to manage elastic network interfaces. Two parts of the AWS Lambda function are considered critical, are the function package and the function handler. The function package has every component that's necessary and makes it all available locally when your function is executed. It contains your code for the function itself, any assets or files that you reference in your code. This can be configuration files, imports, or binaries that your code requires. The maximum size of a function code package is 50 megabytes compressed and 250 megabytes extracted or decompressed. The function handler is used when the code executes. The handler is a method inside the Lambda function that you create and include in your package. The handler syntax depends on the language you use for your AWS Lambda function. So when the handler is specified and invoked, the code inside that handler executes. Your code can call other methods or other functions. The handler function can interact with other AWS services and make third-party API requests. It's important to note you can also pass event objects that you pass into the handler function. The first object we would pass is the event object. This includes all the data and metadata about our function and everything that Lambda needs to implement that logic. And finally, we have the context object, which does exactly what it sounds like. It provides context. or it contains data about the function invocation itself. The context and structure of the object will vary based on the language it's written in. So your function is comprised of these four main objects: your function package, your handler, and the event objects and the context objects that you can pass into the handler itself. Now let's discuss some AWS Lambda best practices. Best practices are based around four functional areas. The first being your function code. So when we're dealing with our code and actually writing our functions, we'll discuss some of the best practices around that. We'll also discuss some best practices regarding function configuration. We'll get into best practices regarding streams, so Kinesis streams and DynamoDB streams, and then we'll finally discuss some best practices regarding metrics and alarms. AWS Lambda function code. So what are some of the best practices when dealing directly with our function code? The first is to initialize the SDK clients. If we can initialize these client connections outside of the function and cache any static assets locally in our temp directory, subsequent invocations processed by the same instance of our function can reuse our resources. Always use environmental variables to pass parameters to your function. This is more secure and much more dynamic than hard coding them in. Control your dependencies, so minimize the complexity in your function code. Try to use simpler frameworks that use exaction context startup for quicker loading. Minimize deployment packages, so make sure they only include the necessities needed at runtime. This allows for a faster package download and reduces the unpacking time. Try to avoid recursive code, so you don't want the function calling itself. That could lead to a pretty high bill. So if this situation ever arises, change the function concurrent execution limit to 0, and that will immediately throttle all the invocations to your function. AWS Lambda function configuration best practices. First of all, perform testing in the areas of performance and load testing. This will ensure an optimum timeout value. You need to see how long your function will run and how this will affect any dependency services. So network load testing, performance testing, user feedback, all these things. You want to create a fine-tuned function that works exactly as you want, but you don't want to invoke more functions than you need to, or you don't want users waiting a long time for results. So performance testing and load testings are very important to your function configuration. You should also use the most restrictive policies on IAM policies. So only give these functions enough permissions to do what they need to do and no more. Be aware of resource limits, such as payload size and space in the temp directory. Sometimes these are overlooked and can cause a serious problem to developers who are expecting to have a certain amount of space in their temp directory, and they have much less than they anticipated. Perform housekeeping, so by deleting Lambda functions when you're not using them anymore. That's good practice in any software development. Retire, deprecate these old Lambda functions when they're not being used. And if you're using the Amazon Simple Queue service as an event source, make sure you set the function's expected execution time value to not exceed the visibility timeout value on the queue. That would mean that messages will time out while waiting for your function to finish. Some best practices surrounding AWS Lambda metrics and alarms. Integrate Lambda function metrics or CloudWatch alarms instead of creating metrics in your function code. So for example, you can create an alarm based on the expected duration of your function, and if that begins to creep up past the metric you set, you may have a bottleneck or some other performance issue. You also have the ability to take advantage of your logging library and the AWS Lambda metrics and dimensions to warn you of any application errors. AWS Lambda function streams best practices. Working with streams, you always want to test with different batch and record sizes to pinpoint the polling frequency needed to the function to complete its task. By default, Lambda invokes functions as soon as records are in a stream. So by changing the record size, you tell the buffer to record for, say, 5 minutes with something that they call a batch window. This will avoid invoking the function with a small number of records. It's more efficient, more cost efficient. You should also increase the Kinesis stream processing by adding shards. Increasing the number of shards will directly increase the number of maximum concurrent Lambda function invocations and increase your Kinesis throughput. And also take advantage of Amazon CloudWatch metric, such as iterator age, to confirm that your Kinesis stream is actually being processed. In this video, I'm going to create a simple Lambda function that triggers when a headshot image is uploaded to an S3 bucket and then outputs it to an SNS subscription that sends me an email to let me know that an image has been successfully uploaded. So the first we have to do is come up under Services, under Compute, you'll find Lambda. So you're brought to your functions page. Any of your functions that are here and already created are able to run or publish or create an alias for. We're going to create a function from scratch. So when we're brought in to create function, we're given 3 options. We can author it from scratch, so create our own code. We can use a blueprint. There's some sample code we can use. So maybe we want to get, like we have an idea and we want to implement something very close to this that returns the current status of an AWS batch job. We don't need to reinvent the wheel. We can use this as a blueprint. Or we can browse the serverless app repository and deploy sample Lambda applications like Hello World and some Alexa. So we're going to go back to author from scratch. We're going to give it a function name of headshot uploads. Here's where we choose a runtime, so it can be .NET Core 3.1, Go, Java, Node.js, Python, and Ruby, all with their version numbers. And some of the other older supported versions are below. You can also choose a custom runtime. I'm going to go ahead and choose Node.js. And now we're into permissions. So we got 3 options here. We can create a new role with basic Lambda permissions. We can use an existing role, or we can create a new role. So in the essence of time, I went ahead and created a role that not only has the basic Lambda permissions, but remember, we also need S3 permissions and SNS permissions. So just creating a new role with basic permissions is not going to do the trick. So we're going to use an existing role, and I created the Lambda S3 SNS access role. So I'll go ahead and create my function, and we're brought right into the designer. So in the designer, you can see a place to add your trigger, a place where you can put in your code for your function, and also a destination that you can output any return codes. So, and also a destination where you can send the results of your function. Come down a little lower, we can see our function code, and what we're just going to leave this function code here. It's just a simple response code of, if it's 200, say hello from Lambda, and we're going to send that to SNS, and I'm going to copy of that in my email. So I'm going to go ahead and add my trigger. My trigger can be it can be something hitting the load balancer. It could be a CloudWatch log. It could be streaming events like Kinesis, or it could be asynchronous events like we're going to use storage. So it asks us to select a bucket to use. I'm going to use tech headshots. And then the event type to trigger the function. Is it going to be all object create events? Is it going to be a put, a post, just copies, or only when a multi-part upload is completed? It can be done on delete events and some Glacier options. I want it on all object create events. I could enter a prefix or a suffix. They are optional. Then I can come down and enable my trigger. You do get a recursive invocation warning that says if you use an S3 bucket for input, you can't use it for output because that's going to create an infinite loop. Right? Your output will then trigger the input, and then we're off to the races, looping forever. So we acknowledge it and click add, and our trigger is created. Now let's click our function and look at our code again. Again, it's just a simple status code 200, say hello from Lambda. And now we need to add our destination. So it's going to be an asynchronous invocation. It's not a stream like a DynamoDB stream or Kinesis stream. And I want it on success. A lot of people use it on failure to see, when things fail. For testing purposes, I want it on success. And I want to send it to an SNS topic I've created called successful image uploads. That, if successful, will send me a message. So I click save. And now I'm ready to go. So I can also test this just to make sure the code works fine. So if I click test, you can create a test event. And you're given an event template. I'm going to go with something simple like hello world. And I'm going to call it test headshot. I create the test event, and then I run my test against this test event. The execution result comes back succeeded. It says the status code is 200. Your function ran. It took 9.33 milliseconds. You're billed for 100. Here's the resources you have configured and your max memory unit. So if I come down into the configuration again, and I look in, you also see the Amazon SNS. So we can also look at things like the qualifiers, right? If I had a qualified ARN or an unqualified ARN, we can publish it, we can create aliases, we can throttle. So if I come back to my function, headshot uploads again, I confirm everything is the way I want it. So I'm going to go and I'm going to actually upload an image to that bucket. So I go into my tech headshots bucket and I just upload a single headshot and click next. Doesn't need to be public, right? It can be private because Lambda has the permissions it needs. Standard class, and click upload. It's successfully uploaded. So at this point now, that just triggered my Lambda function. Now my Lambda function ran and it returned the code 200, hopefully, and send the hello from Lambda response to SNS, which then should email it to me. So let's now look in my email and see if it's there. And sure enough, it's already there. You'll see the version, the timestamp, the IP address of the source, right? The bucket name that was used, the image that was updated, and we've got our status code back. So we can confirm that the function worked exactly as it should. You also have some tabs for permission that show you your role and some access. And you also got a monitoring tab. So you can monitor the invocations and all those metrics. So it takes some time to get the CloudWatch to push it over to Lambda. We can also view our metrics inside CloudWatch itself. If we click metrics, once we're in CloudWatch, we can look at our metrics for, say, Lambda by function name. We'll go down to headshot uploads and click invocations. We'll change it to a number, and you'll see the invocations is 1. If we click duration, you'll see 43.9 milliseconds. So if we come back to our function again, and we come right back into functions, this function is here, right? It tells me what the runtime is, the code size, and when it was last modified. So I hope this video gave you a good overview on just how Lambda operates with regards to input triggers and the code and runtimes itself, and then outputs, where we can send our responses. So dig in, tear into the free tier from Lambda and really get your feet wet and create some simple functions to run. That'll just do some simple stuff just to get your knowledge where it needs to be on how this all flows together. This is much better than if I spun up an EC2 server and let that function run on an EC2 server. I'm paying for that EC2 server constantly. So by using a serverless architecture, I'm not paying for resources when I'm not using them. Now let's look at the process of configuring our AWS Lambda functions. First, we must implement some descriptions and tags. One of the best practices is to tag and give descriptions of your resources. You may start off on a small scale, but when you begin to get bigger, so will your infrastructure needs. With all these new AWS resources being created, identifying your resources will become a challenge if you do not implement a tagging strategy. Next, we deal with memory. So once your Lambda function code is created and your options are set, you have to set some parameters with regards to performance. For each AWS Lambda function, you can increase or decrease the amount of RAM available. You can allocate 128 megabytes of RAM right up to 3008 megabytes of RAM in increments of 64 megabytes. This memory setting also influences the CPU and the network resources that are available to your function. Lambda allocates CPU power linearly in proportion to the amount of memory configured. So one vCPU has a memory equivalent at 1,792 megabytes. So this is something we really need to take into account because we don't want to use more resources than we need or less than we need, right? So we need to make sure we provision the right resources. So we need to increase or decrease the resources being used by the function. And finally, timeout. So when we write our code, we must specify how long the function will execute for. The default timeout is 3 seconds, but it can go up as much as to 5 minutes. One thing to note is that you should not automatically set this function as the maximum value, because AWS charges based on execution time in 100 millisecond increments. If you have a function that fails quickly, you'll spend less time because you're not waiting the full 5 minutes for your function to return a timeout. AWS Lambda functions and network configuration. So there are 2 ways we can integrate our functions with any external dependencies, such as other AWS services like S3 or EC2, or publicly hosted web services. With the default network configuration, Lambda communicates via an AWS managed VPC. So internet connectivity is available, but you still can't access any of your own privately deployed resources in your own VPC. Your AWS Lambda function can also use the Amazon VPC network configuration. That will allow it to communicate via an elastic network interface. This interface is provisioned and placed in your VPC, in your subnets, in your accounts, and this NIC can be assigned to your security groups and be implemented into your route table. So if your function don't need any resources in your account, use the default network configuration. But if you do need access to your resources, you should take the Amazon VPC option. Now there's a lot more to set and a lot more configuration in the Amazon VPC option, right? You have to allocate your IP addresses. You have to implement a network design. You have to increase your cold start times, right? So you have to configure NAT. So there's a little bit more configuration, but if you need to access your resources, then that is the way to go. One thing to note is that if you deploy an AWS Lambda function in your VPC, you're going to need a way to estimate NIC capacity. So projected peak concurrent executions times memory in gigabytes divided by 3 gigabytes will get you your NIC capacity. So if we had 140, a value for projected peak concurrent executions, then I would times that by the result of my memory in gigabytes divided by 3 gigabytes. So my function is using 1 gigabyte. So I should divide that by 3 gigabytes. That gives me 0.3 remaining. Then I times that by my projected peak concurrent executions of 140. And then my E&I capacity is 46. So this is good to know, especially when setting your functions. And when you set memory and CPU, that's also important, but network usage is a resource that is also very important. Concurrency. Even though AWS allows you to scale infinitely, they recommend that you fine-tune your concurrency options. So by default, the account level concurrency within a given region is set to 1,000 functions as a maximum to provide you 1,000 concurrent functions to execute. To view the account level settings, use the Get Account Settings API and view the account limit object and the concurrent executions element. Next, we should set a functional level concurrent execution limit. By default, the concurrent execution limit is enforced against the total of the concurrent executions amongst all of your functions. So this shared concurrent execution pool is referred to as the on-reserve concurrency allocation. If you have not set up any functional level concurrency limit, the on-reserve concurrency limit is the same as the account level concurrency limit. So if your account limit is set to 500, your on-reserve concurrency allocation will also be set to 500. Any increases to the account level limit will have a corresponding increase in the on-reserve concurrency limit. AWS Lambda function failures. Every application or every web service will fail from time to time. What are some of the ways that an AWS Lambda function can fail? These can be, for example, timeouts. So our function experiences a timeout when trying to reach an endpoint. So maybe an HTTP endpoint is down and we can't get a response back, so our function returns a timeout. Maybe a function fails to parse the input data. It's in a bad format, corrupted, or we're not designed to accept data in that format, so we can't parse that input data. And finally, the function is dealing with some resource constraints, such as out-of-memory errors, network errors, or not enough NIC capacity, these kind of things. So if any of these failures occur, your function generates an exception. You can take this exception and send it to a DLQ, or a dead letter queue. A dead letter queue is a SNS topic, or an SQS queue, where you can send all your failed invocation events. The DLQ will take the failed message, analyze it, and then if it's necessary, it will reprocess it. Maybe the endpoint is offline, the function fails and goes to a DLQ. When the DLQ analyzes the function, the endpoint is back online and functioning. So at that point, the DLQ will reprocess the failed function. Another thing to talk about in regards to Lambda functions are environmental variables. No matter the platform, it's important to use environment variables as some of your configuration settings. Any configuration that involves sensitive information, username, passwords, these kind of things, should always be set as an environment variable. Some of the configuration settings would be key value pairs. So now instead of having the key hard-coded, we pass it to the Lambda function each time at execution as an environment variable. By default, environment variables are encrypted at rest using a default KMS key of AWS/Lambda. Some environment variables that we can store would be database connection strings, the environment type, is it a prod, dev, test, right? These kind of things. So always pass most of your configuration, or what you can, via an environment variable. It's more secure and it's more efficient. So how do we invoke the Lambda function? Remember, we can either use the push or the pull method. The push method, which integrates with SQS and SNS and S3, and it's more event-driven, and the pull method, which is used for data streams such as Kinesis and DynamoDB. We can use a custom application, Or we can use a schedule an event, such as creating a CloudWatch event to run every minute, which then, in turn, triggers our AWS Lambda function. Now let's take a look at some AWS Lambda function monitoring tools. As with all AWS services and all applications in general, it's critical to monitor your environment and your applications. With AWS Lambda, we have two options. We have Amazon CloudWatch and AWS X-Ray. So using Amazon CloudWatch, you can integrate metrics into alarms and base actions on these alarms. Some of the default metrics are invocation count, duration, and errors. So how many times has your function been invoked, for how long, and have there been any errors? There's also throttled invocations, iterator age, and DLQ errors. Again, we can leverage these metrics and set our alarms. And from our alarms, we can do so much. We can perform actions based on the alarms. That action can be an EC2 action or an auto-scaling action or an SNS topic. And then we have AWS X-Ray. AWS X-Ray is a service that collects data about requests in your application. So the code runs and it uses an X-Ray SDK. The AWS X-Ray daemon then listens for traffic, gathers the raw segment data, sends it to X-Ray via an API. And the AWS X-Ray displays in the management console window so you can look at it. So with the SDK, you can integrate X-Ray into your code. The SDK records data about incoming and outgoing requests, sends it to the X-Ray daemon, who then sends it to X-Ray in batches. X-Ray can then generate a detailed service graph, which will allow you to determine any bottlenecks or any performance issues. In this video, I'm going to show you how to manage the configuration of your functions in AWS Lambda. So we can go to our function that we've already created, click it, and then we're brought back to our designer page. So under the configuration tab, there's a lot of options now that we can look at, and we can see if we want to change anything, right? So first thing we should notice is our ARN. We can click copy on our ARN, and we've got a copy of it. You can use to reference it, right? If we wanted to change our trigger, then we can come up, we can change our function in here if we want to make any changes, and we also get a little IDE that we can look at, right? So we can save everything in our environment is here. If we wanted to add any comments or code folding or any formatting, so you got a nice little integrated development environment here as well. And you also got places, if your code had environment variables, we would add them here. So any key pairs and these type of things, we could manage them here. And tag. So tag would be a label. So if we wanted to manage a tag, we could add a new tag to the function. We could say created by tech and save that tag. Now we just got a key pair value. There's a lot more you can do, like if for some reason we had a recursive loop going forever and ever, we can throttle it. So that action will set the reserved concurrency to 0. So it'll throttle all the future invocations of the function. We're not going to go ahead with it. It should only be done in case of emergency. Any qualifiers we've got here. So we've got aliases, which is unqualified because we haven't published this function yet. And we've got versions, so $latest being the newest. Under actions, we can publish a new version. It'll save a snapshot of the code and configuration of the latest version. So I can add a version description if I want to. I'm just going to go ahead and click publish. And now that will publish the version. And now you'll see the drop-down box with the version and the number. So now I've got latest and 1. These are the same. So now I can actually create an alias on my version now that it's actually published, and I can go ahead and start using it. Some other actions, again, create alias. So if I click create alias, I have to give it a name, a description, and what version to map it to. So if I map it to latest, then that should always be up to date with the latest version. And that's the great things about Alias. We're not going to create the alias right now. We'll come back into our configuration and designer. Back up to actions. We can export this function. We can export it and download it as an AWS Serverless application model file, or we can download a deployment package. And we can delete a version should we want to. We also have the test, so we can test our versions with multiple test events. And you come down to our basic settings. Again, we've got our handler, how much memory, what our timeout settings are. All right, so if I click info, all right, and we also got AWS X-Ray. So if we have any traces set up in X-Ray, we can see it there. We can see our VPC configuration if we had one. If we had a file system and any provision concurrency, we'd also have it here. We're telling it it's an asynchronous invocation. Any aliases would be here, and data proxies would be here as well. So this is really where we get into the configuration and more the advanced configuration of our AWS Lambda functions. So I hope now you're more confident with creating a different version, with modifying any code, with looking at environment variables and tags, and some of the other advanced functions that you can incorporate into your Lambda function. In this video, I'm going to show you how to look at CloudWatch logs and monitorings for your Lambda functions. So I'm going to come into my function that I want to look at the monitoring for, and you'll see it's on the third tab over, monitoring. So if I click monitoring, and again, this is why it's important that the IAM role that you use for your function has access to CloudWatch. So if I look at my CloudWatch metrics, again, these are your default metrics: invocations, duration, error count, iterator age, delivery failures, throttles, and current executions. So this tells me within the last 3 hours, I've had a success rate of 100%. I've had one invocation, and the duration was 2.77 milliseconds. So if I look at throttles, I've got no throttles. And concurrent executions, I only ever had one. So these are your default metrics. If we come down, we can look at CloudWatch logs insights. So that gives us a query language for us to look at our log entries. And then it shows you the most recent invocation. So if I click the drop down, it shows me my build duration, my ingestion time, the memory used, the max memory used. And I could reference this in a query language to be able to analyze my logs a little bit easier. It also gives you your most expensive invocations. So if I come back up, I can add this to my CloudWatch dashboard. Here's where I can change my range, and I can click View Logs in CloudWatch. So I'm going to go ahead and click Add to Dashboard. It'll take me into CloudWatch, into my personal dashboard. I can create a new one or use an existing one. I'm going to create a new dashboard and call it Tech Function. Click the check mark to make sure the name is fine, and then Add to Dashboard. So now if I click under Dashboards in CloudWatch, the Tech Function dashboard, it looks very similar to what you see under monitoring in the function itself. So I can save the dashboard. We've also got logs that we can look at. So if we load up our log groups and come down, you'll see our headshot uploads. It was created 2 days ago, this log group. And you can see all the log streams and the last event time. So if you click the log stream, you can see what happened when the request started, the request ID, these type of things. And finally, we can come back to our metrics. we can come down into Lambda by function name, and we can choose all of our metrics here that we have on our front dashboard. So here's where we can create an alarm. So I'm going to create an alarm on invocation. So first, I'm going to check and see how many invocations I've had. You can come up here and change this from line to number. So I'll come back up to alarms, and I want to start creating an alarm. So first I have to select the metric. So if I come down into Lambda, just like we previously did, find my function, headshot uploads, and I want invocations. So I want to set an alarm on invocation. So if I select the metric name is invocations, my function name is headshot uploads. How long? I want to do it every minute. And under statistic, I want a sum. Right, so when the sum of all invocation reaches 2, I want this alarm to fire. So our conditions use a value as a threshold. Whenever invocations is greater than or equal to 2. I can do some additional configuration on data points and how to treat missing data. I'll click Next. Do I want to add any auto scaling? I don't need to. If the alarm triggers, send it to an SNS topic, which is successful image uploads. Click Next. Click Next. Give the alarm a name. Call it function invocations. And a description. This will return an alarm when function invocations equal or greater than 2. So click Next. Right, it shows it right now. The invocation's at 1. Here's where my alarm will trigger at 2. And just a review of the actions I want to take and the name and the description, and I'll create my alarm. So now you'll see my alarm, and the state is in insufficient data because it hasn't collected all the data points yet, right? It needs a minute for each data point. So I'm going to come back into Lambda, and I'm going to test that function and invoke it again. So if I test it, it comes back fine. I can even test it again. The alarm will still trigger, and that's fine. So now it's just a matter of waiting that minute or so for CloudFormation to sync up with Lambda, and you can get your alarm fired up. So if I come back into CloudWatch again, it's in alarm, right? And we look at the count. Invocations are now 2, which fires off the alarm and sends me an email. So this is just a simple demonstration on how to look at your default metrics, look at your logs, create alarms based on those default metrics. So now dig in to CloudWatch and integrate with Lambda, maybe even create some alarms of your own, and really dig into the powers of incorporating this monitoring and logging with AWS Lambda. Now let's discuss AWS Lambda functions and versioning. Versioning is a great option to be able to publish one or more versions for your AWS Lambda function. Versioning is integral to developing serverless compute architecture, as it allows you to create multiple versions without affecting current deployments. Each AWS Lambda function version has a unique Amazon resource name, or an ARN. After you publish a version, you can't change it anymore. So you can use versions to manage deployments of your Lambda functions. So for example, you can publish a new version of a function for testing without affecting users of the stable version, the production version that's currently in use. So the system will create a new version of the function each time you publish it. So every time you make a change and you publish the function, it'll create a new version. That new version is a copy of the unpublished version of the function. The function version includes a function code and all the dependencies, the runtime that it executes, a unique ARN to identify that version of the function, and all the function settings, including any environment variables that you set in your function itself. So how do we go about creating versions of a function? So to create a new version of a function, we have to go into the Lambda console, choose the function we want to publish in the actions area, and then publish your new version. So after you publish the latest version, the Lambda console will now display you a drop-down menu with each version that you can choose from. So the designer panel displays a version qualifier at the end of the function name so you can easily identify what version of the function you're dealing with. Managing versions with Lambda. To publish a version of a function, we use the Publish Version API action. If you publish a new version of a function, the response will return configuration information about the new version, including the version number and the function ARN with the version suffix. Your reference for your Lambda function will use its ARN, and there are two ARNs associated with an initial version. You have the qualified ARN, which is the function ARN with the version suffix, and you also have the unqualified ARN. So that's the function ARN without the version suffix. So if you decide not to publish function versions, you can either use the qualified or the unqualified ARN, but you can't map an alias to an unqualified ARN. So if you're going to use an alias, it has to be a qualified ARN. Each Lambda function version has a unique ARN, so after you publish a version, you can't change the ARN or the function code behind it. Once we create a version of a Lambda function, we can use that version number in the ARN to reference that exact version. That's fine until we make a change to a new version, then we have to find the reference to that old version in every line of code and service we have. So it's simpler to create an alias, and if we create an alias, every time that we update a version of a function, we only have to change it once. We only have to change the alias to point to the new function version. So to create an alias, we go into the Lambda console, we choose the function that we want to create an alias for, we choose Create Alias on that function, then we give it a name and a description. That name is then your alias name, and you can basically reference your functions with that alias. And it's good because, again, you don't have to have the time-consuming effort of going through every line of code and changing version 1 to version 2. You can just do it once and point the alias to the new version. To create an alias, we use the Create Alias command. And to update an alias to point it to a new version, we use the Update Alias command. These command line commands correspond to the Create Alias and the Update Alias APIs. Each alias has a unique ARN. An alias can only point to a function version. It cannot point to another alias, for example. Event sources, such as Amazon S3, invoke your Lambda function. These event sources are maintained in a mapping, and when an event is triggered, that identifies the function to invoke. In a resource policy, you can grant permissions for event sources to use your Lambda function. If you go ahead and use an alias to reference your ARN in that policy, every time a new version updates, you don't have to update the policy because you're going to update that alias to point again to the new. In this video, I'm going to demonstrate how to create function versions and aliases to simplify your deployments. So let's go into the function that we want to make a new version of. So what I want to do here is I'm going to create an alias, and that alias is going to point to our original version 1 function. At that point then, I want to go ahead and start creating a different version of that function, version 2. We can test version 2, and then I'll repoint the alias from version 1 to version 2. So let's go ahead and come up to actions, and first let's create our alias. Let's call it prod. So this is the one that's going to point to what we want for production. Right now it's 1, or I could put it on latest. The problem with alias, if I use the latest version constantly, and I'm pointing the production environment to the latest version constantly, whenever I publish a function, even if I don't want it to go to production, if it's tagged as the latest and prod is looking at the latest, then it'll be there for the users in production. So I'm going to go ahead and leave it on 1. You can also do a weighted alias. So if I had 2 versions, I could shift traffic between those two based upon a percentage that I want to assign. So I'm just going to go ahead and call it prod. And now you'll see a new drop-down list with alias prod. So if I look, I got 2. I got an unqualified, which is the latest version, and I got the production. And if I come over into versions, you'll see I've got latest and version 1. So let's go ahead and make a change to our function. So I can come back to my function again under configuration. We've got some function code. And let's go into our basic settings. And let's change the memory up to 1280 megabytes. And let's change our timeout from 3 seconds to 5 seconds. So I'm going to leave everything else the same and save. You'll see the changes have now been saved. So if I go ahead now and click action and publish a new version, here you can see that it says it saves a snapshot of the code and configuration of the latest version. So if I already had prod pointed to the latest, as soon as I click publish, then it's going to be pointed to the new version, but we haven't really tested it yet. So I'm going to go ahead and click publish. Successfully created version 3. So right now I have version 1 and version 3. Version 2 was created at one point and removed. So you can see that they keep the versioning in numbers even if you delete a version. So right now we have our configuration. You can see it has a :3 for the version number. Come back out under aliases and find the production alias. And now we're going to point this to the new version. So I come under configuration and click edit. And I could change it to version 3. So once we do our testing and everything is fine, now I change the alias to point to the new version. The beauty is this is that I don't have to go through lines of code and service to find where it points to version 1. And I don't have to do that 100 times. I only need to do it once at the alias level. So I click save. You'll see the changes have been saved. The alias prod now points to version 3. So if we finally come back to our function again, and up under actions, you'll see we've got capabilities. So we can deploy these to Lambda at edge now. We can delete the function. If I look under qualifiers, you'll see there is version 1, 3, and latest. And it shows you what version the alias is pointing to. If you click over on aliases, again, you can see that it points to version 3 and an unqualified latest version. So I hope this video helped you understand how we can integrate functions with aliases and new versions to make the deployment a little easier and testing a little easier. Aliases are great, right? We only need to, when we update a version number, we only have to change it in the alias. We don't have to change it in the code everywhere. So get in, create some new versions of your functions, create some aliases, and get your feet wet into the Lambda function alias and versioning. In this video, I'm going to demonstrate how we can incorporate external dependencies and packages into our Lambda functions. So I'm going to use a layer. A layer is a package of all our external dependencies in our function. At runtime, these dependencies specified in the layer are loaded and they become available to our Lambda function. So I'm doing something simple. I just downloaded and installed Flask. I created a zip file with it in it, and then I created a layer from that. So let's take a look at my directory. You'll see I have an AWS flask-lambda.zip and a Python directory. So if I go into Python and look, you'll see Flask was installed in this directory. So my zip file is just these Flask files. That's all it is. And then I uploaded that AWS flask-lambda.zip file to an S3 bucket. So this is the external dependency of Flask. So let's go into our AWS console. And once we get into the dashboard, we can come over to additional resources and choose layers. So I'm going to go ahead and create the layer. I'm going to call it Flask layer. And I'm going to give a description. This layer will provide Flask package. I'm going to upload a file from Amazon S3, which after I created my zip file, I sent it to Amazon S3 into my tech repo bucket, and it's called AWS-flask-lambda.zip. So I have to choose a compatible runtime. I want Python, and I want 3.8. I have no license issues I got to deal with, so I'm going to go ahead and create that layer. When that layer creates, I have a version. It tells me what it is, compatible runtimes. So my layer is now created. I can use this now for any Lambda function if they need to bring in the Flask package. So I come back to Lambda, and I'm going to create a function, just a simple function that will return my version of Flask. So I'm going to come down to function name, and I'm going to call it tech Flask example. Now my runtime should match 3.8 because that's the runtime we set for our layer. So I'll give it 3.8. I'll come down to my execution role. I'll use the existing role I've been using, and I'll create my function. Now you can see where I can change the code and configuration. So first thing I want to do is come down and put in the code. Import JSON, import Flask. So I need to find Flask. Flask in this case is an external dependency. So I can save it. Now if I went to test it and selected a test event, and I actually ran the test, it would fail. It'll say unable to import Lambda, no module named Flask. So to fix this, we need to come under layers, and we need to add a layer, right? We need to add that Flask layer as an external dependency. So I can choose a layer from a list provided by AWS, but I've got a custom layer. So if I hit the drop-down box, you'll see my Flask layer is here. It tells me what version to pick. I want version 1. We could also specify an ARN as well. So I click Add, and now I'm adding that Flask layer to my function. Now you'll see it has the 1. If I click it, here's where it is, and it'll download it, and it'll install that Flask. So let's test our function again and see if we have any different this time. We should. So I click test, and sure enough, the text has succeeded. I click details, the status code was 200, and the body says 1.1.2, which is the version I am using. So not only did the code work, but it pulled in that Flask external dependency from our layer, and then it returned me the version of the Flask. So the beauty of this is that now any function that I now deploy that need to use Flask, I can just add this layer. I don't have to integrate it into every bit of code or every zip file that I send up. Right? I have it once, it's in S3, then I can use that layer on any function I want. So we can do more. I mean, we can add multiple other external dependencies if we were to use them, if we needed to use them, depending on our code. And we can add them as different layers. So we're separating them, right? So we can update different versions of them at different times. So I hope this video showed you how to incorporate these external dependencies into your Lambda functions to make them even more powerful and to be able to use all the capabilities that Lambda has to offer. In this video, I'm going to demonstrate how to use AWS X-Ray with your Lambda functions to view all your calls and trace how your function is actually working and performing. So I'm going to use the TechFlask example function. It's a function that basically just returns your Flask version, and it has a layer that provides Flask for it. So you'll see we've got the configuration, we've got our layers. You can add a trigger and add a destination. For now, I'm just going to come down and make sure that under AWS X-Ray, active tracing is clicked on. So I click Save, and now we should have AWS X-Ray active tracing. So what I want to do is I'm going to run this test a couple times just to kick off a couple active traces. So if I come into execution result, you'll see that it returned the Flask version of 1.1.2. You'll also see a X-Ray trace ID and a segment ID and whether it was sampled. In this case, it was sampled. So let's come down to X-Ray and let's take a look. So if we click View Traces in X-Ray, it'll bring us into the AWS X-Ray console. And from here, we can click in our trace and take a little deeper dive, and we can see the graphs that they create for us. So if we look at our trace list, you'll see there's one here. So if I click the trace list, it brings me into the timeline, tells me how long ago it was, its ID, and it also creates a trace map from this data. So if we zoom in, we can see that the client called the Lambda test Flask example, and that function request took 1.02 seconds, and then the actual function call itself took 2 milliseconds. So if we come down, we can see the duration itself, how long it took. So the test Flask example took 2.1 milliseconds. Initialization was 472 milliseconds. Invocation was 1.2 milliseconds, and overhead was 0.6 milliseconds. So if your functions are running for a long time and you don't know what part is causing this delay, here's a good place to look. It breaks it down into initialization, invocation, and overhead. The raw data looks pretty much the same. Right, the duration is there, the document is there, the function name, the start time, its trace ID. So if we come into analytics, and you'll see time series, click and drag the filters to trace by time. So if I wanted to only subset this 1 minute, I can. If I wanted to spread it out over the whole day, I could as well. So I'm going to leave it during this time frame because these are the only traces that I had. And we can, kind of run some analytics over these. I can change it from the last 5 minutes to the last 10 or 15. Right? But the more traces you get, naturally, the better it will work for you. So let's come back into Lambda again, and let's kick it off a few more times and see how that looks in X-Ray after we run it a couple more times. So I'll test it. Always come down and make sure the active tracing is still on. I'll test it again, and I'll test it again. I'm not adding a trigger and a destination because I can invoke this function just by using the test, and for our purposes, for looking at X-Ray, that's more than sufficient. So I'll come back into X-Ray again. And now you'll see I have 4 traces. The one from earlier, and the 3 new ones. So I can click each one. You can see the age, the response time for each one. They should all look the same. If you click the timeline, it'll give you again the duration. It'll give you a trace map. What took more time than the others, right? So it's good for testing out those kind of things. If you come back to analytics again, you'll see our retrieved traces are now 4. So if we come back out to service map, now you'll see that it's computing a map for you. So if we had more functions, right, we can choose which function we want to take a look at. There's also services icons. We can turn them on. It tells you, this is Lambda, this is Lambda. We can turn that off. And now you'll see it gives you an average of 17 milliseconds for the client to speak to Lambda, and then an average of 6 milliseconds for the actual function to run. So to use Lambda, maybe you have an issue where you have a long-running function and you can't figure it out. Go in and trace it. You don't have to trace every one if you don't want to, if you're trying to troubleshoot something. But go in and click off the trace. Find the trace, come in, click it, and see what's actually happening under the hood. So that's the beauty of X-Ray. So I hope this video kind of gave you a little bit of insight on how to use X-Ray, turn X-Ray on, and how X-Ray really digs into your function, looks at all the calls, any external dependencies, any resources, any annotations, any metadata, any exceptions, and just provides you with a good overall insight or X-ray into your Lambda function. In this video, I'm going to demonstrate some of the AWS Lambda best practices when it comes to configuring and maintaining your Lambda function. So I'm going to go back to my function called test flask example. This is just a basic function that will return the Flask version if Flask is installed, and it also has a layer attached which has Flask on it. So I'm going to go over the 4 main areas of Lambda best practices. We got function code best practices, function configuration best practices, CloudWatch monitoring and alarm best practices, and best practices for streams. So regarding function code, let's take a look at our code itself. So they say you should define your handler outside of your logic for more unit testing functionality. We've defined our handler here. They also say avoid recursive code. So you don't want a function to call another function. Nor do you want a trigger like S3 and a destination being the same S3 bucket. That's a recursive call as well. So you want to avoid recursive calls. You don't want the function calling itself. It will be in a loop. And if you ever come across that, you'd have to go up and throttle your function. Minimize the complexity in your function code. So use a simpler framework. Right? So I use Python 3.8. You also want to maximize the size of your deployment packages. So you'll see that this one also has a layer. So the fact that it has a layer is also best practice. We're separating our external dependencies. Right? So I added a layer. So I can add this layer to any function if I deem necessary. So this is a best practice as well. And you also want to make sure that deployment packages only have what is necessary. So this deployment package only had Flask in it, for example. Right? It allows it to download quicker and unpack quicker. Now regarding function configuration best practices, you should always use your most restrictive IAM permissions. So I needed permissions to use CloudWatch. I needed permissions to access S3 because that's where my trigger is going to be. And I need permissions to send that to an output on SNS. So I've created a role that gives me Lambda, S3, and SNS access. Only what I need. So if you come under resource summary, you can double check and look and see Amazon CloudWatch. I'm allowed to create log groups. I'm allowed to create log streams. And I'm allowed to put log events. If I go under S3, I'm allowed all S3 resources. And if I go under SNS, I'm allowed all SNS resources. Or we can have a resource-based policy that allows us to grant usage permission to other accounts on a per-resource basis. Then it gives you a little thing about auditing and compliance. CloudTrail can log this function's invocation. So if we want to get started on CloudTrail for any operational and risk auditing and compliance measures, right, you want to incorporate CloudTrail as well. We also have monitoring best practices. So we know the default metrics. So I can view the logs in CloudWatch and create an alarm, for instance. So I can create an alarm if there's any throttles. So if the throttle is greater than 0, send me an alarm, right? So you want to monitor and you want to create alarms based on your default metrics. And one last thing we should look at is if we come down into our environment variables area, here's where you can add environment variables. If we want to pass in a user key, for instance, here's where we would pass in that environment variable. So you're not hard coding parameters and environment variables into your function. Tags are good best practice. You should always know, say, who created it, for example. And I could just say my name. At least then I have a running tag of me as the creator on any resources that I create. And you should also perform some load testing because you want to make sure that you have your timeout set appropriately. You don't want it to set too short. You don't want it set too long, right? Too short of a timeout, and then your processes and functions won't finish if they're waiting on something. But too long, if there's an error, then you're probably waiting, say, 60 seconds for the error to return, and you're paying for that time. So these are some best practices that you should employ when you're creating your function and managing your function. Your function code, right? Separate that handler from your logic. Use environmental variables. For the function configuration, load test. That load test will allow you to fine-tune your timeout value. Use some restrictive policies, only what people need to do. And perform housekeeping. So when you're done and you have no use for the function anymore, we go ahead and delete it. Alarms and metrics, you always want to monitor your alarms. Right? Use an SNS queue to send any alarms to you. And keep an eye on those metrics. And streams, you want to test with different batch and record sizes to really pinpoint your polling frequency. So good luck writing your Lambda functions, incorporating everything you've learned, and really harness the full power of serverless computing. So in this course, we've examined how to realize the serverless compute model on AWS Cloud through the use of the AWS Lambda Serverless Compute Service. We did this by exploring the serverless compute model and how it is implemented on AWS, the AWS Lambda Serverless Compute Service, including best practices for its use, how to use the AWS Management Console to create, configure, and manage AWS Lambda functions, and how to configure and test AWS Lambda logging and monitoring. We also looked at how AWS Lambda versions and aliases work, including how to publish AWS Lambda function versions and aliases, how to work with AWS Lambda function external dependencies, how to use AWS CloudFormation and AWS X-Ray to configure AWS Lambda function monitoring, and best practices to use when creating and configuring AWS Lambda functions. In our next course, we'll move on to explore the creation and management of serverless applications on AWS through the use of AWS Lambda and other Amazon services, including Amazon Simple Storage Service, S3, Amazon API Gateway, and Amazon Cognito. So what is the AWS Serverless Application Model? The AWS Serverless Application Model, or SAM, is an open source framework that you can avail of to build your serverless applications in the AWS cloud. Serverless as a general concept lets you run your code and functions as a service, meaning you don't have to buy or rent the hardware or even a VM. Cloud function providers charge based on the number of runs, the amount of RAM used, the amount of CPU, and of course, storage is limited. But you can access other cloud storage products or database to take advantage of that storage as well. So it's comprised of the AWS SAM template specification. So this is used to define the components that make up our serverless application. It's a clear and concise syntax that's used to describe our APIs, functions, events, configurations, and permissions. So you use this specification to define your serverless application. It provides you with a simple and clean syntax. And you can also use the AWS SAM command line interface to build your application that we defined in our template. So the CLI enables us to invoke Lambda functions, verify that our code is good, and it gives us a Lambda-like environment all locally. So we can do all our debugging locally, we can do all our testing locally before we go ahead and deploy our application. Some of the benefits of using AWS SAM. Because serverless application model integrates into other AWS services, creating serverless applications provides us with many benefits. One of this is AWS CloudFormation. So really, SAM is an extension of the CloudFormation. It's a layer that's built on top of CloudFormation, which is the way AWS describes resources in codes. So SAM is making it a little simpler. So when we write a scheduled event, for example, in a Lambda function using SAM, it's translated into a CloudWatch event in CloudFormation. And we can also mix CloudFormation codes into a SAM template. We can take advantage of the built-in best practices. Things like code reviews, safe deployments, and X-ray tracing are possible to integrate with AWS SAM. These best practices are easy to implement. They're kind of built into a lot of the AWS SAM features and applications that we use. We can take advantage of local debugging and testing. So that's the power of the SAM command line interface. It lets you build, test, and debug serverless applications in a local environment. So it has that Lambda-like execution environment, but locally. And it helps you catch issues up front before we actually deploy our applications. You also take advantage of the deep integration with development tools. So you can use SAM with a suite of AWS tools. You can use it with the serverless repository. We can use Cloud9 for authoring and debugging our code. We can take advantage of code build, code deploy, and code pipeline to deploy our applications using various deployment methods. And we can use CodeStar. That'll help us get started on like code repository, project structures, and provide you with a CI/CD pipeline. And finally, single deployment. It's easier to organize all of our related components and resources and deploy it in a single stack. So we can manage all those resources in one stack. We can update the resources. So it's a one single deployment, which makes everything a little bit more simpler and easy. So what makes up an AWS SAM template? The format of an AWS SAM template is very similar to a CloudFormation template file. The primary difference between the AWS SAM template and the AWS CloudFormation template files are, well, for starters, transform declaration. You have to declare it. So you need to form AWS : serverless dash and the date. Much like we had to declare a CloudFormation script, you have to declare your SAM template file as well. So that tells CloudFormation that this template is actually a SAM template. And then all of the other declarations like AWS : serverless : function and API, we need to put those in so these resources will inherit any properties that are in the global section. Resources in these template files, a lot of the times they share configuration. things like memory, virtual CPUs, and VPC configuration. So instead of duplicating this on every SAM template, we can put it in our global section, and all of our resources will now have access to them. And speaking of the resources section, in the AWS SAM templates, the resources section can be a combination of CloudFormation resources and SAM resources. So some SAM resources would be a serverless API or serverless application or serverless function, for example. The AWS Serverless Application Model CLI is our command line interface tool that creates an environment that mimics our cloud environment. This local environment lets us test and analyze our serverless application before we actually deploy them. So this can now all be done via the command line without having to enter the console. In order to use the AWS SAM CLI, you do have to meet a few prerequisites. You must install Docker, have Python involved, right? Whether it's Python 2.7 or 3.6, you need to have pip installed. You need to install the AWS command line, and then finally the AWS SAM command line on top of it. So to use this command line, we got to define three simple things. We must have a valid SAM template. Without that valid SAM template, then we don't have a serverless application. You must also have the AWS Lambda function defined. So without a Lambda function, again, it's not a serverless application. You can use Node.js, Java 8, Python, and so on. There's a few options you can use for writing your function. And finally, we must have an event source. We need something that tells the Lambda function what it expects to receive. So some valid events could be API gateway, it could be an upload to an S3, it could be a CloudWatch alarm, right? So we need that event source. So we need the template, we need the function, and we need the event source that's going to fire the function. The AWS Serverless Application Repository is a managed repository for serverless applications. We can publish our own applications, we can configure our serverless applications. Once we're done, we can upload them to the repository. Then we can collaborate between teams or the organization or even the public. We can also deploy applications. So we can browse the repository, look through all the source code and the README files, find any application that we want to deploy, change it as we see fit if we need to, and then go ahead and deploy it our own. Let's take a look at a standard three-tier application. So standard three-tier application are made up of, you guessed it, three tiers. You got the web tier, you have the application tier, and you have the database tier. So normally the web tier is used as an interface for the users to present data. The application tier takes the data, makes decisions on it, and may invoke storage into the database tier. So let's look at an analogy. You go to the bank and you ask for a loan. So you speak to the loan manager. The first thing they do is present you with a loan application form. They then take the data from you and present it to the loan manager. This is the web layer. It collects information from the user and communicates that to the application. The loan manager represents the application, or the middle tier. They collect the user input, which is your loan application form, and they make decisions about how to process it according to the bank policies. So maybe they will approve it, maybe they will reject it. However the loan manager decides to handle the application, they have to make a record of it. So it'll go in some filing cabinet or database. This is your database tier. So a good three-tier application will ensure that each tier is a discrete unit. If at some point the bank decides to change paper formats or accept email or web-based applications, the bank manager should still be able to understand the incoming application. So if the web tier changes, the underlying application should still be able to understand that input. This is a far cry from the serverless architecture that we're discovering. So the AWS serverless architecture uses a web application architecture, such as S3, where we can store our static files and create static web pages from it. It'll use an Amazon Cognito user pool for user authentication. It'll use an Amazon API gateway with AWS Lambda as its app servers, and it'll use Amazon DynamoDB as a database. So this is our serverless architecture. S3, we don't manage any servers, but we can host a static website. Cognito is no servers, but we can use a user pool for authentication. The API gateway and the AWS Lambda is the definition of serverless computing, and they will perform functions and act as the application. And the Amazon DynamoDB allows us to create a serverless database where we can store our information or session data. More AWS serverless components. You'll use Amazon Route 53 for your DNS. You can use Amazon CloudFront for your content distribution network. Again, these are all serverless. You don't manage any of the services behind them. You can also use S3 for your web servers. So again, for your static websites, we can host on S3. We can host the entire website on S3 and make sure JavaScript can make API calls using the Amazon API Gateway service. Right, so in this architecture, we'll use S3 to host the website, and then we'll use JavaScript to make API calls to the API Gateway service. So that's how everything will integrate together. Now, what about data? You can use Amazon DynamoDB as a serverless database service. You don't provision any of the Amazon EC2s inside your account. Right? It's also highly scalable, very fast, and a great database for storing session data. You can use RDS if you need a relational database. However, this is not completely serverless, so then you wouldn't be deploying a fully serverless stack. But there is a new service release called Amazon Aurora Serverless. It is a full RDS MySQL 5.6 that is considered fully serverless. So by using the Amazon Aurora Serverless Relational Database option, you would still be creating a fully serverless stack. In this video, I'm going to demonstrate how to install the AWS SAM command line interface on your Windows machine. So you'll know there's a couple prerequisites before you can install this command line. You need obviously an AWS account. We need the proper IAM permissions. We need to install Docker if you want to test your application locally. And then finally install the AWS SAM CLI. So I'm going to go with the assumption that we all have an AWS account at this point that has the IAM permissions that we need to access our serverless applications. So once we're ready to go, we can go ahead. If we want to install Docker, we can install Docker to test our application locally. If we don't want to test our application locally, it's fine. We can just go ahead and install the AWS SAM CLI. If you already have Docker installed on your machine, you can go ahead and skip this portion and move right along to the installation of the AWS SAM CLI. Installing Docker Desktop is a great advantage because from the command line you can create containers, you can upload images to a repository, or pull images back down from a repository. So, for starters, we want to go to the official Docker webpage. If we can go to Docker webpage, you'll see it's docs.docker.com/docker for Windows/install. So here we can view our prerequisites and we can actually download the file. So some system requirements: you need a Windows 10 64-bit, Pro, Enterprise, or Education. Hyper-V and container Windows features must be enabled. And you must have the following hardware: 64-bit processor, 4 gigs of RAM, and a BIOS level hardware virtualization support. That must be enabled. One thing I'd like to note is that if you're installing on Windows Home, your process will be a little different. You're going to need Windows 10, but you have to enable the Windows Subsystem Linux 2 feature for Windows. Then you actually need to have a 64-bit processor, 4 gigs of RAM, BIOS level hardware virtualization, and then you finally must download and install the Linux kernel update package. So it's a couple more steps for Windows Home, but it's still doable. So we'll go back to Windows 10 Pro, and I'll download the setup files from the Docker Hub. I come in, I click Get Docker, and I'm going to put it in my Docker install folder, and it's 391 megs, so it's a relatively pretty quick download. Once we get it done, we can kick off the install process, and I think it involves at least one restart. So once we're down to our final few megabytes, we can kick off the installation process. So the installation process will involve downloading more files and going. So it's not a lengthy process, but it's not short either. So we'll walk through it and see how it goes. So I get my security warning, I'll run it. I get my user account control, click OK. And now it goes into the downloading. It downloads more packages, it installs these packages. It's a bit of a lengthy process, but once it all gets done, you should be up and running very quickly. It'll go through and unpack all the resources. One thing to note is your Windows 10 must be up to the newest version. It's the 2004 version. If you try to install without the most updated Windows 10 version, Docker will fail and you'll have to eventually do the update. So we're still unpacking some files. As you can see, it's a pretty heavy-duty application. When you're in the world of virtualization, Hyper-V, these packages are not small, and they do take a moderate amount of resources to install and run. Now that everything is unpacked, we get into the installing. So we created a Docker users group. We add users to that group. It's enabling the extra features, adding shortcuts, adding binaries and CLI plugins, and now it appears to be clued up, and the installation is successful. So we click close, and let's come out of here and go into Docker for Desktop. So I click the link, wait for it to fire up. You'll notice it'll come up down here as a little whale. Tells us the Linux containers WSL2 backend is starting. We can always right click it and look at a dashboard. So if we click the dashboard, you can see it's spinning up. While that's spinning up, we can open up our command line and just be sure that it did install correctly. So it's important to note you should run your command prompt as an administrator. Account control again, and now we're in the command prompt. At the same time, Docker is still in the process of starting, but the dashboard has created. So we're going to go ahead and let that continue starting. But in the meantime, if we just type in docker -- version, we can see that it is installed. It's version 19.03.8, and it has a build of AFAC B8B. Now Docker Desktop is running. So once we're ready to go, we'll come down and find our install file that we're looking for. So we're going to install the AWS SAM CLI 64-bit. There's also a 32-bit Windows link as well. So I'm going to click the 64-bit. I'll have a download pop up, and I'll go ahead and save it. It's a pretty small file. We'll go ahead and open it right away, and we'll get our pop-ups. We can go ahead and click Next, accept the terms. Next, you can keep most of the default settings. It's a pretty quick install. It doesn't require any restarts or anything like that. Once it's installed, we should be able to go ahead and use it right away. So once it finishes up here, we'll just run a quick command to verify the installation. It's the SAM -- version command. And if it returns our version, then we know we successfully installed the AWS SAM command line interface. Now it's all complete, we can click Finish and launch a command prompt shell and see if it actually was successful. We type in sam -- version, and we should get the version number as an output, and we do. So it says SAM CLI version 0.53.0. So now we've got the command line installed. We can go ahead now and start creating our Lambda functions, event sources, and all the other components of our serverless application. In this video, I'm going to demonstrate how to use SAM, or the Serverless Application Module's command line interface. I'm going to create a template. We'll deploy our application using the AWS SAM command line. It'll create our Lambda function. It'll create our event trigger, which in our case is going to be an API, REST API. And we'll do this all from the command line. So our first command is the SAM init. So the init command creates a new SAM application and allows us to choose from different templates. So we can use a quick start template, or you can use a custom template location. In our case, we're going to use a quick start template. When you get a little more versed with the SAM command line and SAM itself, and you want to start incorporating your custom templates and your custom applications, then that's fine too. So we'll click 1 for a quick start template, and the first thing it asks us is which runtime will we like to use. So we can choose from Node, Python, Ruby, Go, Java, .NET, right, and multiple versions of each. I'm going to choose a Node.js 12.x. And now we have to give it a project name. So I'm going to call this one Hello World. And immediately it clones those app templates from the AWS GitHub. Once it brings back, you get 8 templates. You get a Hello World example, a step function sample app, a quick start from scratch, a quick start from scheduled events, S3, SNS, SQ, and a web backend. So you can customize these as you need them. And a lot of these templates will fit most of what we need. So it's a really good service from Amazon here by giving you these templates. So we're going to use the Hello World example. It generates the application, and then you can see it gives it a name, Hello World. Its runtime, which is Node.js 12.x. Its dependency manager will be npm. The application template is Hello World, and the output directory is in my current Richard.\hello-world. So it tells us our next steps can be found in the README file. So let's go into the application itself, and you'll see I have events. We have the application, a README, and the template. So if we look at the README file, it tells us this project has all the source code and all the supporting files for our service application. So let's take a look at the template. When we go in the template, you can see it gives you your AWS template format version. This is important, the transform AWS serverless. So it tells us we're deploying a serverless template here. And if we come down to resources, you'll see this is what the serverless is going to create. It's going to create a Hello World function of type serverless function. So it's going to be a Lambda function. Its code URI is hello-world, and its handler is app.lambda handler. So code URI and handler tell you the function code is located inside the Hello World /app.js file. All right, so we're telling it where to go and get that application. Under events, for our Hello World application, type is going to be API. So we're going to invoke this Lambda function by just sending a GET request to a REST API. Its properties is path is /hello, and the method is GET. So that's our template. If you come into the actual application, you'll see the app is here, the package is there in JSON, right, with all the information about it. So once we're pleased and we like how everything looks, we can go ahead now and start to actually build our application. So I'm going to first make sure I'm in the correct directory, and then I'll do a SAM build. It builds our function. It's running the Node.js npm builder, and the build succeeded. So it gives you your build artifacts and your build template. Then it tells you this is what you can do next. You can specify a SAM local invoke command or a SAM deploy. Right? So that local invoke, if we want to invoke this locally, and we still have to supply a trigger in this case because we're doing it locally. So what we want to do in our case is we want to deploy this. So we're just going to type in SAM deploy guided. So it guides us through, asks us the questions that need to be answered. It asks us for our stack name. I'll say hello world stack. What region? I'm going to leave it in US East 1. Now it's going to say, do you want to confirm the changes? So it's going to show you the changes that it made. In this case, the resources that it had. So yes to that. Do you want SAM to create the IAM role that it needs to connect to your resources? Sure. There may not be any authorization. That's fine in this case. And do we want to save this to our SAM config file? Yes. So now it gives you its deployment. It's saying we're deploying with the following values in the stack name. The region is US East. Do we want to confirm the change set? So right now it's creating that change set. And CloudFormation is coming back and saying, okay, this is what we're doing in this case. We're adding a Lambda permission called hello world function, hello world permission prod. We're creating an IAM role. We're creating a Lambda function. And we're creating an API gateway deployment stage and the REST API itself. So this is where we say yes or no. Do we want to create this or not? In our case, we do. That's exactly what we expected. We click yes. So at this point now, we're converting our SAM template to a CloudFormation template, and we're uploading it to S3. And then CloudFormation is going to deploy all the resources that we specified. And as you can see, this is much like the CloudFormation interface. Right, create in progress, so our resources are being created. It gives you the logical resource ID, and now it's totally complete. So it gives you your outputs. It gives you your IAM role outputs. It gives us our API gateway endpoint, and it tells us this is the function we created, and this is where you can find it. So in this case, we want to test our API. Okay, so we want to make sure that this Lambda function will kick off. So if we copy our endpoint for our API, we just send a simple GET request to this URL. That API then will trigger our Lambda function and then return just a simple hello world. So we'll know this works if we get a hello world back. So I type it in. This is my API ID, .execute-api.myregion.amazonaws.com/prod, which is our deployment stage, and then /hello. So I click enter, and sure enough, I get a hello world back. So what happened there was I sent that request to our API. Our API then triggered to Lambda. Lambda ran the hello world function and returned it back to us. So this was all done serverless. We did all this via the command line. Yes, we used a sample template, but that template is easily changed to fit your needs. So I hope this video helped you kind of get a good insight on creating your first SAM template, which includes your events, your functions, where you can find these files, how to deploy these files and build these files, and then how to test it. So everything we did was serverless. We didn't pay for anything. We only paid for the resources that we use. And in this case, a small API call, it's negligible. So get in, create some SAM templates, use some of the examples, and then when your skill set gets a little higher, start incorporating your own and make it fit your needs to do exactly what you want. In this video, I'm going to utilize Amazon's simple storage service, S3, to publish a static web page. So as you can see, I have my web page here. It's a very simple index.html. Title is example, and the body of this is example of a simple HTML page with one paragraph. So if I open it in my browser, you'll see this is what it looks like, but right now it's local. So we're going to come into S3, and we're going to create a bucket that will host this as a static website. So we come ahead and create a bucket. We can call it Tech First Website. Leave the region in US East because that's the region we're going in. We can copy settings from an existing bucket, but my existing buckets aren't public, so that would do us no good in this situation. We have some versionings. We can keep all versions of an object in the same bucket. We can log requests for access to our bucket. Right? We can do some advanced settings, like permanently allow objects in this bucket to be locked. And CloudWatch request metrics. I click off this because it's good to know if you're using a website, you want to see the request to your website. So I'll go ahead and click next. So here's the part where we block all public access. This wouldn't make sense for a public static website. So I'm going to turn this off, and it gives me a little warning that says, this is wide open to the public. I acknowledge it. Click next. So all my public access is blocked. And now I go ahead and create my bucket. Once I go into my bucket, I'm going to go ahead now and upload my index.html file. This is the website that I want to host. So I click next. I come down to public permissions and I say grant public read access. Again, you'll get another notification. That's fine. We click next. We'll leave it in standard storage class. We don't need any encryption at this point. We can have a key created by Richard, just so we have a running list of who created what. Click next and upload my file. So the file was uploaded successfully. And now we have to tell the bucket to create the static website, right, and host the static website. So we come into properties. You'll see static website hosting. So we go ahead and click it, and it'll come down, and we got three options. We can use this bucket to host a website, which you want to do. We can also use this bucket to redirect requests, or we can disable website hosting. So we're going to use this bucket to host a website. It has our endpoint available. So I click use this bucket to host a website. Now it's saying, what is the index document? So that is your starting web page. Ours is index.html. And if you wanted to have an error document, when an error occurs, you could have an HTML page for errors as well. So now that I've got my index.html defined, and I've told the bucket to act as a static web page, I'll click save. And now you can see the bucket hosting is clicked off with a purple check mark. So let's go in and again and click the endpoint. If all works well, we should see our static website. And we do. So if we want to look at the URL, now you can see that it says techfirstwebsite.s3-website-useast.amazon.aws.com. So we can give this URL to users. We can put this URL behind a domain name, whatever we want to do. So it's pretty simple. You create your index.html, create your bucket, make it public, and then turn on the static website hosting. So I hope this video gave you an insight on how to leverage Amazon S3 and all of its powerful capabilities to get your static website on the internet as fast and easily as possible. The Amazon API Gateway is a fantastic service to use as an HTTP front end. It integrates seamlessly with other resources to help you build your serverless application. A lot of people's knowledge about the API Gateway is limited to, well, a user sending a request. The API part is often a black box. We know a user sends a request, then the API Gateway does something. It is crucial to understand the many components of the API Gateway to really harness its power. So what is the Amazon API Gateway? API Gateway is an AWS service that can be used with your REST, HTTP, and WebSockets APIs. It allows you to create APIs, publish APIs, it will maintain your APIs, monitor your APIs, and secure your APIs. Developers can create APIs that access AWS or other web services, as well as any data you have stored in any of your cloud databases. The Amazon API Gateway creates RESTful APIs that are HTTP-based, enable stateless client-server communication, and implement the standard methods such as get, post, put, patch, and delete. So to create a REST API in Amazon API Gateway, you'll need to use an assortment of So to create a REST API in Amazon API Gateway, you'll build that REST API as an assortment of programmable entities known as API Gateway resources. Each resource entity can in turn have one or more method resources. Expressed in the request parameters and body, the method defines which API client a user will need to access the exposed resource. A method also represents an incoming request submitted by the client. So you then need to create an integration resource to integrate the method with a back-end endpoint. This is also known as an integration endpoint. This is accomplished by forwarding the incoming request to the specified integration URI. If necessary, you transform request parameters or the body to meet the backend requirement. For responses, you can create a method response and an integration response. The method response is used to respond to the client, while the integration response is the request response that is returned by the backend. After we successfully created our API to our liking, we have to deploy our REST API. So to deploy an API, we need to go ahead and create an API deployment, and then associate that with a stage. A stage can be anything from dev to test to prod, and even something like V2. It's just a logical representation of where your API is in its development lifecycle. These API stages are identified by the API ID and the stage name, and they're subsequently included in the URL that you use to call your API. Every time you update an API, you must redeploy that API to a stage you already created or a new stage. So as your API progresses and gets larger and bigger, you can deploy it to different stages for testing and quality assurance purposes. When the testing is done, you'll need to deploy that API to the clients. So you can deploy your API updates as what they call a canary release deployment. This is a software development strategy in which we deploy a new version of an API for testing purposes on the same stage as our production API. In a canary release deployment, total API traffic is separated for client access at random into a production release and a canary release with a pre-configured ratio. To call a deployed API, the client submits a request against an API's URL. The URL is determined by an API's protocol, host name, stage name, and if we're using REST APIs, the resource path. The host name and the stage name determine the API's based path. So a little about WebSocket APIs. In API Gateway, we can create a WebSocket API to use as a stateful front end for our serverless application or even an HTTP endpoint. Whatever happens on the back end is determined by what's in the messages that the WebSocket API receives from the clients. In API Gateway, WebSockets are bidirectional. So a client can send a message to our service, and then that service can send messages directly to the clients. So we're cutting out the middleman, and that gives us better exchanges because our services can push the data to the clients without requiring a request to do so. This is often used in chat applications and multiplayer games. In your WebSocket API, incoming JSON messages are directed to the backend based on the routes that we configure. So a route makes use of what they call a route key. This is the return value once a route selection expression has run. The route selection expression is an attribute that we define in our API. It specifies a JSON property that the services expects to see in the message payload. There are 3 predefined routes that can be used. We have the connect predefined route. This is used when a persistent connection is being set up between the client and a WebSocket API. Because these connections are stateful, you have the option to perform authorization on the connect route only. We also have the disconnect route. So when the client or the server disconnects from the API, this is used. This connection can be closed by either the server or the client. So sometimes the connection is already closed when it's executed. So disconnect route is a best effort event. And the API gateway also has a default route if no route is matched. So you could use this as a fallback route, for example. To create a WebSocket in API gateway, we can go in the API gateway console. We have to choose the WebSocket protocol and give the API a name. Now, one thing to remember, once you choose a protocol, you can't convert it. So you can't convert a WebSocket API into a REST API. So it's as simple as going in the console, going in the API gateway console, clicking Create API, choose a WebSocket API, and then choose Build. Give it a name. Enter that route selection expression that we talked about. That could be request.body.action. Enter description if you need to, and then click Create API, and then it's done. We can also create an API using the command line interface, so the create-API command, or we can use one of the various AWS SDKs to call the create API command. So there's 3 ways that we can create a WebSocket API in the Amazon API Gateway. So finally, we want to deploy our WebSocket. So how do we go about deploying our WebSocket? We've got the API just where we need it. Now we need to deploy it. So first we need to create an API deployment and then associate it with a stage. So this could be dev, this could be test, this could be production. Right? But we need to associate it with that stage. Once we deploy it to that stage, we can now call the deployed WebSocket API using the API's URL, which is comprised of the host name and the stage name. We can also set an API domain name. So we can use the default domain name, like api-id.execute-api.region.amazonads.com/stage, which is indeed a mouthful, or we can use a custom domain name like api.example.com/myservice, which is a lot easier for clients to remember. So once it's all done, it's deployed, you have a URL, you can continue to use the default URL, or you can add a custom URL for your clients more user-friendly. In this video, I'm going to demonstrate how to create a simple API using the Amazon AWS API Gateway. So once we're in our management console, we come up to services and you'll find API Gateway, or you could type in API Gateway, and it'll bring you into the API console. As soon as you're in, right, you see your APIs, any custom domain names, any VPC links. we're going to create an API. So we can choose an HTTP API, a WebSocket API, or a REST API. We also have an option for a public API. So it's interesting to note. It tells you, this HTTP API will work with Lambda and HTTP backends. The WebSocket API works with Lambda, HTTP, and other AWS services. The REST API is the same, so it kind of tells you what it should be used for and what it actually works with. So I'm going to go and develop a REST API, so I just click Build. There's an option there for import as well, but we're going to create one from scratch. So select whether you'd like to create a REST API or a WebSocket. We choose our protocol of REST. Then, do you want to create a new API? Do you want to clone from an existing API? Maybe you want to make changes. Do you want to import it from Swagger or OpenAPI 3? Or do you want to take an example API and make changes to it? So we're going to go with a new API. And just for some background, our API will be just a Lambda integration. Just a simple Lambda function that says hello from Lambda, so we know that it actually got the response from Lambda. So I'm going to call it my first API. We'll give it a description. API to call Lambda function hello from Lambda. Now endpoint could be regional. Right, what region we're in, US East 1. It could be edge optimized, which is great for public-facing APIs, right, much faster. And it could be private. Now, if you do private, you got to create VPC endpoints. So in our case, we'll leave it at edge optimized. Right, edge optimized is the good one for public-facing APIs. So we'll go create our API, and it brings us directly into our kind of API generator. So we can edit our API, right? So you'll see you've got resources, stages, authorizers, right? A lot of advanced stuff that we will get into. But first we have to create our API. So resource is the word used in API Gateway to describe a given URL path. So in this case, resource is just /, so like everything at this point. While method is used to describe the HTTP verbs. So my resource is a /. So we don't have any sub resources, it's just /. So I create a method. And you'll see a little drop down underneath the resources. It'll be any method. If they do a delete, a get, a head, options, patch, post, put, I'm going to choose a get and click OK. So now you'll see the get setup. Right, so choose the integration point for your new method. We can use Lambda, we can use HTTP, we can use MOT, we can use another AWS service, or a VPC link. We're going to use a Lambda function. Our Lambda region is in US East 1. And then we have to specify the ARN of our Lambda function. So if we come in, you'll see my Lambda function is there. I chose my Lambda. You'll get a list of all your Lambda functions. Do we want to choose the default timeout? Yes. And we click Save. You get a warning saying permission to your Lambda function is going to be given to API Gateway. We click OK. And it is saved. So what it'll bring you into now is method execution. So it gives you a little test, right? And it gives you a little map, right, of how it's all going to work. If they send a method request of get, it's going to integrate to Lambda. It's going to go to my Lambda function. It's going to pass through the response from Lambda and pass it to my method response, which gives it back to the client. So you can see the whole map of integration here with Lambda. If I wanted to add another method, like a post, for instance, I could come into post, and maybe I want to send a post to a different Lambda function. Right? So in this case, I don't. So I'm going to delete that method of post, but you can see that depending on the method they use, they may hit a different function. I could even create a different resource, right? And the resource path is maybe called upload. Right now you see your resource path as /upload. I'm not going to enable cores right now. I create that resource. Now you'll see I've got another resource, and I can just go ahead and create a method. So under upload, they may be doing a put or a post, right? So then I can incorporate that with a different Lambda function. Right? Maybe I incorporate that with a headshots Lambda function because they're uploading their headshots. Right? So I click save, same warning, click OK, and now you'll see my APIs there. So if they just did a put on the /API, then they'll retrieve the hello from Lambda function. If they do a get on the root of my API, then they will get the hello from Lambda function result. But if they do a put on the /upload resource, then they'll get a completely different Lambda function. Right? So that's how we can control our mappings and what resources are accessed by what methods and what integration happens, and gives us ability to really fine-tune our API. So if I want to go back to our get, it allows us to run a test. So if I click test, it says we're just going to make a test call to the method you provided. Right? We got no query strings or no headers or no stage variables. It's just a simple API call. So we click test, and it comes right back. Status of 200, 82 millisecond latency, status code of 200, and hello from Lambda. We got our Amazon X-ray traces, and we have our logs. Right, so we know that worked. If I come in on the upload one and run a test, right here, we had no path. There are some query strings and headers if we want to, but we should be able to run the test fine, and it came back 210 milliseconds, hello from Lambda, this is version 2. So you can see, depending on your resource and method, you can really send your clients to different areas of your API and can perform a lot of different functions in your API. So if we come back now, and our next steps would be to deploy our API, right, or export the API. But I wanted in this video to show you how to create that simple API, how to get in, look around at all the requests, the method requests, the integration requests. Right? So method requests is what method is it? Is it going to be a get? Is it going to be a put? What is this request? The integration request is what type? Is it going to be a Lambda? Is it going to be HTTP? The integration response, it's a pass-through in this case. And our method response model, if it becomes a status of 200, use the JSON application model for method response. So here is our simple, basic API. Once you get that down pat, then we'll get into deploying the APIs, setting up authorizers, setting up cross-origin resource sharing, and a lot of the advanced features of APIs. But I hope this video gave you a good introduction on how to get in, create your first API, play around with different methods and resources, play around with the testing, and do some fun and interesting integration. Right? So once you get your feet wet, start playing around a little bit more, doing a little bit more of the advanced features, and really get into what API Gateway can give you with regards to serverless applications. Amazon API Gateway stages. A stage is just a logical name reference to a specific API deployment in a specific phase of the system's development lifecycle, and it's essentially a snapshot of the API. Stages are used to manage and optimize your deployments. You may create a stage for each of your environments. So you start your API in a dev stage, then when finished and ready for testing, deploy it to a test stage. Then when satisfied, deploy it to the prod stage. Each stage may have some custom settings like request throttling and specific stage variables. No matter what stage you deploy to, the API is considered deployed and is accessible to whoever is granted access. So don't grant production users access to a dev API, for example. They'll get them mixed up and they'll think they're using the production one and they're really using the dev one. So this is where permissions really come into play. So how do we go about creating a stage? After our first initial deployment, we can add more stages and associate them with existing deployments. We can also create a new stage using the API Gateway console if we don't want to deploy our API to an existing stage. So to do this, sign into the API Gateway console. From the API's navigation page, choose Stages under an API. So find the API, choose Stages. From that Stages navigation pane, click Create. And then you'll come to the Create Stage. You enter your stage name. So that could be prod, dev, test, right? That's what we use for our stage name. We can put in a stage description optionally if we wish, and it's a good idea to do so. Then from the deployment drop-down list, we choose the date and time of our existing API deployment that we want to associate with this stage. And then finally, when we review everything and everything looks good, we can choose Create, and our stage is now created with an API associated with it. Stage settings. After we initially deploy our API, the stage is populated with default settings. But we can go ahead and change these to our needs by either using the API Gateway console, or we can also do it using the API Gateway REST APIs. If we're going to go about it using the API Gateway console, first we have to sign into the console, find the APIs pane, find the API that belongs to the stage we want to update. Then in the stage editor pane, choose the settings tab. Then we can make changes such as turning on the API caching or changing stage variables. Just remember, API caching is not free tier, so you will be charged for the use of API caching. To delete a stage, it's best practice that when we no longer want a stage or need the stage, we delete it, and we can avoid paying for any unnecessary costs associated with the stage. One thing to note is that when you delete a stage, it could cause part or all of the APIs to be unusual. So to delete a stage using the API Gateway console, we have to sign in to the API Gateway console, choose a REST API that we want to delete the stage of, choose Stages, then choose Delete. Then we go ahead, click Confirm, the stage is deleted, and that stage is gone. So maybe it was a test stage, and we don't need it anymore. We've deployed months ago, and everything is fine. We don't need to leave those resources hanging around and paying for them. So we delete it, and it's gone. And if we ever need it again, we can recreate it and associate it with an API. Stage variables can be used for REST API deployment. There are name value pairs which hold configuration attributes associated with a specific deployment stage. Does this sound like environment variables? Because it is basically the same idea here. They can be used in your API setup and mapping templates, and you can use these to pass configuration parameters to, say, Lambda or a specific HTTP backend. In this video, I'm going to demonstrate how to deploy our API to a stage and what its different stages entail and what options we can choose depending on what stage we're in and why stages are so important. So let's first click the API that we want to deploy, and it's going to be my first API. It's just an API to call Lambda function. So if we come in and look at our API, you'll see I have two resources, and a slash v2. If you do a get on the slash, it comes in to a Lambda function called myLambda function. And if you hit the v2 with a get, it runs myLambda function v2. Right, so if I want to test them just to see what we're expecting, if I run version 1, I get a hello from Lambda. And if I test a version 2, I get hello, you have reached version 2. So depending on what resource and method, you could get a completely different return back. So we want to go ahead and deploy this API to a stage. So if we come down and look at stages first, we've got no stages, and we can create a stage. But a stage is essentially just a logical reference to where an application, or in this case an API, is in its development lifecycle. So it could be in a development stage, it could be in a test stage, it could get finally deployed to a production stage. So in this case, with our API, we want to deploy the API, and we're going to deploy it to a development stage because we're still in the development mode. So if I click, I have no stages, but I can click new stage, and I can type in dev as the stage name. I can give it a description, development stage, and the deployment description is our initial release of API. Click deploy, and you'll see right away we've got the URL that we use to invoke our API. So a few settings you can look at. Right, we can enable the API cache, which are some of the more advanced, but we can look at throttling. Right, so we can enable throttling, and right now it's throttled to 10,000 requests per second with a burst of 5,000 requests. We can also include a web application firewall if we want to incorporate any certificates. We can do logs and tracing, right, with CloudWatch, X-Ray. We can also set stage variables. So I'm going to add a stage variable, and I'm going to call it Lambda alias. And I'm going to say dev. Because I create aliases for my Lambda functions, right, the ones I'm using for dev, I create an alias dev. The ones I eventually go to production, I'll create an alias called production. So if I come in and create stage variables and say the Lambda alias to use is dev, and for production, if I do the same, but I say prod, then the stage knows exactly what Lambda version to use because we're specifying the alias, and that changes with each stage. We've got SDK generation, we can export it. We've got deployment history, documentation history, and a canary deployment. So let's invoke our URL. So if we click it, we get hello from Lambda. But remember, we also had the v2. So if I click v2, we'll say hello from Lambda. You've reached version 2. So you see the API ID .execute-api.your-region.amazon AWS. And then you see that it's /dev. Right, so this is our dev environment, the root of our dev environment. And v2 can also be called. And if we go back into our gateway, you can see exactly where the slash and the v2 is. So right now it's deployed. We can delete our stage. We can configure our tags. Right, so I can say created by Richard. Again, tags are good just to keep a running record of who's creating what. So right now it's deployed. Right, I can go ahead, delete the stage. I can come back to the resource. If it's the way I like it, I can deploy it again and create a production stage. Right, this is for production versions. And our deployment description would be our first production deployment. And I click deploy. Now you see two stages. You see dev, you see prod. So I come back to stage variables. I say Lambda alias for this stage is always going to be prod. And now I've got two different versions. Right, I've got the dev one, which I can invoke using the URL /dev. And I've got the URL for the prod one, which I can invoke. So I hope this video demonstrated stages and how you use stages to deploy different versions of your API depending on where they are in the life cycle. Right, so dev, once you're happy with your changes, you can deploy it to a testing stage. Once that's fine, you're happy, you can deploy it to a production stage. So it separates your API code based on where it is. Right, so you don't want to have just one stage. People are using it, and users are using it, and developers are writing over it. It's impossible. So by creating stages gives you that more fine-tuned granularity to push out different versions as you see fit. In this video, I'm going to demonstrate how to use mappings in relation to an Amazon API gateway. So mappings can allow us to do a multitude of things. Mappings can take our inputs and transform them into a different output. So we've got applications waiting downstream. Maybe they expect first name and last name to be concatenated together. But when you accept the user input, you take the first name and the last name separately. So mappings allow us to concatenate those and transform any other names or telephone numbers or formats that need to be changed before the downstream applications can actually process it. It also allows us to pass through a lot of information like when it was ran, who ran the API, who the request was forwarded for. So let's take a look. This is my first API. It's a GET. And really all it does if we test it is that it returns a status code of 200 and says hello. So now we come back and we look at our integration requests. We know this is integrated with a Lambda function, and it goes to the Lambda function, but the integration response and the method response is where we want to pay close attention to. So if I click integration response, you'll see right now I only have one integration response, and that's for when we get a code of 200 back from our function, which we just did. So if I expand it, if I look through, the Lambda error rejects is default, content handling is passed through. Any header mappings that we want to have would be here if we add them, but our mapping templates. So I'm going to add a mapping template, and I'm going to call it application/JSON. And you'll see a template generation drop-down box here. You've got a method request pass-through, and you've got two models. The empty model, where you can just create your own, or an error model. So we're going to go with the method request pass-through. Basically, what this mapping is going to do is pass through the whole method request in the body of the API. So who did it, what time, the IPs that it were forwarded for. So we're going to go ahead and click Save there. Double click Save here. Come back to our execution. Now you can see here I'm using the default status pattern. If there were multiple status patterns, I can choose them here. Under method response, for instance, if I want to add a response for an error code of 403, I click OK. I can come back under my integration response, and now I can add an integration response for 403, which is considered forbidden. Right? And we're saying, is it going to be pass-through? Is it going to be convert to binary, convert to text? We'll click Save, and now we can go ahead and expand and create mappings for this as well. right? So we can add a application error mapping template, choose the error model, and we can make it whatever we wanted. You have an error, please contact the administrator. So it's just these little things that allow us to really say, if this happens, right, do this. So if you get a success error 200, map that error to, map the success code of 200 to something a little more readable. If you get an error code of 403, we'll map that to something a little more readable as well. Right? So that's your integration responses. So now, once I deploy my API, I'm going to still deploy it to dev. And we're going to say we added mappings. And I invoke it. And now we have our hello from Lambda. But we also have all the pass-through data. Right? We have the header. And the reason for doing this, mapping out these headers and stuff, is because these downstream applications will need that. So is cloud front forwarded? HTTPS. What's the host name? Right? Who was the referrer? Who referred us to this API call? What user agent? Windows 10, 64-bit. Right? It shows you your X-ray trace ID. Shows you the port it was forwarded on and who it was forwarded for. Any stage variables, so Lambda alias dev, because we're in a dev environment. And more context like API key, if there was any authorizers, the stage, then my source IP, the resource path, and so on. Because, again, yes, we got the success code, but a lot of downstream applications will take this information because they need it. So that's a good way. So you've successfully created mappings, right, for all your error messages if needed, like any 403 codes. You also modified the 200 mapping to include all the context mappings and the header mappings, right? So I hope this video gave you some insight on how you can use mappings, whether you want to convert an input to a different output, or if you want to pass through all your context mappings and your variables, right? But there's many ways you can do this, and it's a really powerful feature that can really help you down the line, especially with systems integration. In this video, I'm going to demonstrate how to export your API gateway APIs into either an open API approved specification or an API that you can incorporate into Swagger. So first I'm going to find my API. It's my first API and I click it. We go in. And now it's important to remember that we export at the stage level. So come down and click Stages and select your stage. If I had multiple stages here, you'd see them: dev, prod, test, right? So we export at the stage level. So once I click dev, you'll go ahead and we'll see an export tab. And we've got Swagger and OpenAPI 3. So OpenAPI is an API specification. Swagger is used widely for tools for implementing that OpenAPI specification. And Postman is an API client, right? So it's good for testing APIs based on specifications. So if we want to export an OpenAPI compliant definition file, we can choose it here. If we want a Swagger file that we can incorporate into Swagger and work on it, we can choose Swagger. So if I go OpenAPI, I've got three options. Export as the OpenAPI 3, export as OpenAPI 3 plus the API gateway extensions, or export as OpenAPI 3 plus the Postman extensions. So if we want to incorporate this API with any API gateway extensions or Postman after we export it, these are our options. If we just want the definition file, we can go ahead and click either JSON or YAML, whatever you want. So I click JSON. You automatically see it in line. Plus you can download it. Right, so I'm downloading the file right now. If I double click it, we look in there It shows you your Open API version, the title, the description, your servers, your default path, any other additional paths, and the methods and resources behind it, and how to reply. So mappings, right? What happens with a 200 response? What happens with a 403 response? And it'll be the same if I came into Swagger, right, and chose a JSON. You can see it in line. It also downloads it. If I want the Swagger as a Postman extension, I can click on the JSON file. It'll download it. And I can look at it here, but I can open it in Notepad and make any changes that I wish, right, should I want to. So I'll come back into my console again. And again, depending on what you want to do, if you just want the Open API specification, by all means, you got that option. If you want to incorporate it in with Swagger and work on it with Swagger and Postman extensions, you have that option as well. And it's just as simple as clicking on your format of your choice, downloading the file. So congratulations, you've successfully exported your API. In this video, I'm going to demonstrate how to enable caching for your API to reduce the number of calls made to your endpoint and also improve the latency of requests for your API. So choose the API you want to enable caching for. I'm going to choose my first API. It'll load up into the screen. Once your API is loaded, you'll notice that you want to go down to stages. Right? Much like exports, caching is set at the staging level as well. Right? So we could have a dev stage, a prod stage, a test stage. Maybe ideally you only want to turn caching on for a prod stage. Right? So your end users can get the increased speed and performance. So normally we wouldn't do it in dev. For our example, we can use dev. So we'll click dev and we should see all our options and settings come up. And you'll see under settings, the first setting, cache settings. Enable API cache. So it's simple as that. You click the checkbox. You'll get a warning. Enabling the API cache increases costs and is not covered by the free tier. So what happens when we enable this caching for a specific stage, the API gateway caches responses from our endpoint for a specific time, and that's our cache time to live. Right? And that's measured in seconds. The API gateway then responds to the request by looking up the endpoint response from the cache instead of making the request to your endpoint. So again, you can see how it's much faster. So you can pick your cache capacity ranging from 0.5 gigabytes to 237 gigabytes. Generally, a larger capacity gives a better performance, but naturally it's going to cost more. Do we want to encrypt our cache data? You can turn it on or turn it off. What's the cache time to live? So we go with normally 300 seconds, which is about 5 minutes. Do we want to require authorization? In this case, we won't. And then it comes down to our regular options that we had before, like throttling. So it's pretty simple to set up the cache. You just check the checkbox, set your cache capacity, choose whether you want to encrypt, set your cache time to live, and should there be any authorization. When you're done, we come down, we save our changes, and you'll see the stack being created. Right, so the cache status is create in progress, and once that's done, our cache will now hold our responses for that scheduled time to live. Creation time will have a lot to depend on your options as well. Right, the larger your cache capacity, it's going to create a longer creation time. Now the cache status has changed to available. It's been created. It was a bit of a lengthy process. Right, now the only options we have now are flush the entire cache. We can also change our cache capacity after we created it, and our time to live, and our encryption. Right, so we got flexibility even after the fact. So congratulations, you've now, whenever you invoke your URL, it's looking to the cache first. right? So any one of your users of your application is now going to take advantage of that increased speed to access your application, and you're going to take advantage of a lot less requests to your endpoint. In this video, I'm going to demonstrate how to integrate AWS X-Ray and AWS CloudWatch into your REST API. So I'm going to come in and select the API that I want to monitor. I click my first API, and I'm brought into the API section. The first thing that we need to do is come into the IAM management console. We need to make a role. So if we come in, we can create a role. We want to use the API gateway service. So we click Next Permissions. You'll see the policy is the Amazon API Gateway Push to CloudWatch Logs policy. So I click Next. Optional tags, I click Review. I give it a real role name, so I'm going to call it my first API CloudWatch role, and I click Create Role. I come down, find the role, and copy the ARN. Next, we come back to API Gateway. Once we're in Gateway, scroll all the way down to your settings. It's here in the settings where we have to specify what our CloudWatch log role ARN is. So it's here, you can update it, right? This is one that was previously here. I can replace it with the ARN that I specified. So this is the role that has write access to CloudWatch, and we're giving it to the gateway. So I save. Now we're using that role we just created. Now we come back up to our stages, and again, monitoring and X-ray is done at the stage level. So if I had multiple stages, you'd see them there. I'm going to click on the dev stage, and I'm going to come over to the logs and tracing tab. Once I'm here, you can see here's your CloudWatch settings. Do you want to enable the CloudWatch logs? Do you want to enable detailed CloudWatch metrics? There are some default CloudWatch metrics. So we want to enable the CloudWatch logs, and we have a log level. Do we want to log everything, which is info? So that's all the calls and everything about them. Or do we only want to log calls that result in an error? So I'm going to say info. I want to log full request response data, and I want to click the detailed CloudWatch metrics. So this method will generate metrics for API calls, latency, integration latency, 400 and 500 errors. These are not free default metrics. They are charged at standard CloudWatch rates. So we can also click Enable Access Logging. So once I click Enable Access Logging, I have to specify an access log destination ARN and the log format. So we can use the ARN that I've specified earlier, or we can go ahead and create a new access log. So if I want to come back into CloudWatch and I go into log groups, I'm going to create a log group, and I'm going to call it my first API log. I click Create. Now I need to find it and copy the ARN. So I'm going to go back into my API gateway, and where it says access log destination ARN, I'm going to paste in the access log destination ARN that we just created. In the log format, I've got examples. I can use CLF, JSON, XML, CSV. I'm going to use JSON. And I'm going to click off Enable X-ray Tracing. So I save my changes. And now I invoke the URL. Everything still seems fine. So at this point now we want to take a look at CloudWatch. Right, so let's take a look at our metrics, our API gateway. So we come under API gateway metrics. We can choose by API name, by method, by stage, or across all APIs. If I choose by API name, I see all the APIs I created. I find my first API, and I tick off these metrics. Let's just take a quick look at them. So you'll see I've got 500 errors, API gateway count, 400 errors, latency, integration latency, cache miss count, and cache hit count. Right? So these are metrics. We can create alarms from these metrics. Right? So I can call this my first API metrics. I can come back into log groups, and by this time we should have a log group created, and by this time we should have one, for my first API log. So right now we don't have any log streams, so we need to go ahead and hit the API. So I'll come out and I'll reload the API a couple times so we can get some of those metrics built up. I come back into my gateway, into CloudWatch, and I refresh. Now you can see the log streams are starting to come in, one for every time I click the URL. So if you click it, it shows you things like the request ID, the IP, the caller, the user, the method was a get, and what was the status. Right, so it logs all this for you for your log group. And finally, alarms. We can create alarms based on metrics. So if I want to create an alarm, maybe I want to create an alarm based on response time. Right, so I create my alarm, I look by my metrics, by API name, and I want to choose my first API app, and I want to set an alarm on latency. So right now, I can change this to 1 hour, and I'll just give it a number. Right now, my latency is 78.2 milliseconds. So I'm going to select that metric, and I want to give it a period of over 1 minute. And I want to say that if the latency ever goes greater than 100 milliseconds, I want an alarm kicked off. So I know this is going to trigger the alarm because this is lower than the current latency right now. That one's 141, that one's at 92. So once I trigger the API a few times, it should kick the latency up over 100. So I click next, select an email list that I'm a part of, click next. I give it an alarm called latency, my first API, and a latency alarm for my first API. I click next. Now you see your graph, right? So you see your line, and once it goes over that line, it's going to trigger. So our goal now is to make it go over that line. So we create the alarm. At first, there's insufficient data. It takes a little bit of time for the data points to build the data. In the meantime, I'm going to send a few requests to the API. Now we go back to our CloudWatch console, and while we're waiting for the alarm to go off, we can come back to metrics, and now we'll start seeing our metrics change as well. Right, so it's every 1 minute. So from the time I click that API, it'll take about a minute for it to show up under the metrics. Our count is still going up, our latency is still going up. I came back to my alarms just for the sake of explanation. I came back to my API and I edited my threshold to be 30. And I edited my latency threshold to be 30. So now I know we will kick off that alarm. We can actually see it in action. But so let's come back to our metrics and just take a little look again. Latency is up to 48.6. So when that alarm fires, next it will trigger. Right, so it's looking at a latency greater than 30 for one data point for 1 minute. And if we look at our metrics, the latency is greater than 30 for longer than 1 minute. Right, we have 24 counts hitting our API. Now you can see my alarm is in alarm status. Right, so if we look at it, it's telling you latency alarm is in alarm. Your threshold is set at 30, but your current latency is 42.5. So we had to lower the latency threshold to get the alarm to fire for this example. But again, it's just a good example of how you can create alarms for your APIs. So next we should look at AWS X-Ray. With X-Ray, if we come down to traces, you'll see the URL, how many % of traces that was taken, which is 100%. We traced every one, 79 traces. So that means I executed that API 79 times. I can say for the last minute, for the last 5 minutes, right? So, and then it gives you the age, the method, the response time, the URL, the client IP, and the annotations. So if I click a trace, it shows me a little bit in more detail. It shows me that it was a get, but most importantly, it shows me this trace map. Right, so it shows the client requested to the My First API dev, took 22 milliseconds, and then the integration with Lambda took 18 milliseconds. Right, so X-Ray can determine if you have any bottlenecks in certain areas. Right, remember if you click health or traffic, and remember if you click service icons, you can see, right, this is an API gateway, this is a Lambda. And so we come back to CloudWatch. So if you followed along and did everything in this video, congratulations. You created an API gateway. You enabled the CloudWatch logs, full requests. You enabled the detailed CloudWatch metrics, and then you enabled your custom access logging. Then we went over into CloudWatch. We looked at our metrics. We looked at the logs, right? We looked at a log group that we created. And that log group was called My First API log. And it gives you all the log streams. And we looked at creating alarms based on metrics. We also went into X-Ray and viewed every trace for every API call. It was there. So we can just click it, get a trace map, right? And it's a good way of looking at bottlenecks. So get in, create more intricate monitoring and intricate alarms and actions, and really harness the full power of the monitoring and tracing elements of the API gateway. In this video, I'm going to demonstrate how to enable CORS, or cross-origin resource sharing, for your APIs. CORS is a specification that controls how browsers decide when scripts from one domain are allowed to invoke services in another domain. Right, this is done for security reasons, designed to protect users from rogue or malicious scripts on one domain from abusing a user's active session on a different domain. So CORS uses additional HTTP headers to tell browsers when to give a web application running at one origin access to selected resources in a different origin. So a web application executes a cross-origin HTTP request when it requests a resource that has a different origin, such as a domain, a protocol, or a port from its own. So to create your CORS enabled, to enable your CORS on API, find the API that we want to enable CORS on. I'm going to choose my first API. Once the screen loads up, you choose your resource. Right, so I only have one resource at this point. I come up and click Actions, and I say Enable Cores. So now you'll see a few different options to choose from. So gateway responses, right? Do you want the default 4xx and the default 5xx? Right, because we don't have any custom responses, so we'll go with those. The methods is going to be a get. Right, we can have other options, but in this case, we don't have any other methods, so we only have a get method. So now that brings us down to these three following fields. We've got the access control allow methods field. This indicates which methods are allowed on a particular endpoint for cross-origin requests. Right, so we're saying get is our allow method. We could have, if we had puts and gets, so we're selecting get because that's the only method we have right now. The access control allow headers, this is a header that we used in response to a pre-flight request. Okay, so a pre-flight request is the information contained in the access control allow methods and access control allow headers. So the access control allow headers is used when there is a pre-flight request, and it includes the access control request headers. So it's used to indicate which HTTP headers can be used during the actual request. So you'll see we have content type headers, exams date headers. We also have authorization headers. We also have API key headers and API security token headers. So these are the headers that we're allowing. We also have the access control allow origin. So where do we want to allow these cross-origin requests to come from? We have a wildcard, so that means they can come from anywhere. If you come down under advanced, you'll see three more options. We have an access control expose headers, which indicates which headers can be exposed as part of the response. Right, so if we want to expose headers as part of our response, we can put it here. We have the access control max age. So that indicates how long the results of a pre-flight request can be cached. And we have the access control allow credentials. So if you're using any security, you must specify it under this access control allow credentials. It must be set to true. So in our case, we'll leave the advanced settings as they are, and we'll click Enable Cores and replace existing cores headers. Because when you created your serverless API, you can enable cores there as well. So the replace existing cores headers is basically saying if there's any cores specifications in there now, we're going to replace it with what you chose here. So I click Enable Cores, and it gives us our confirmation. So the following methods will be made to this resource methods, and we'll replace any values. So we're creating an options method. We're adding a 200 method response. We're adding mock integration. We're adding access control, and these are really interesting ones here. We're adding access control allow headers, access control allow methods, access control allow origin method response headers to the options method. And so everything that we added to the get method, they're adding it to the options method as well. So I say yes, replace the values. Hit checkbox down through, everything is fine. And at this point, congratulations, your resource has been configured for cores. So now you see a get, and you see the new options method. And your application now is completely ready. Your options method is your mock endpoint. So if we click the options method, we come in, it's just a mock integration web point, and our main information is under cores. So we can come back in and set it all again, or we can take out a content type and change it the way we want. But for now, I'm going to leave it as it is. And if you followed along with this video, you've now enabled your API for cross-origin resource sharing, and it can interact with services and APIs outside of its own domain, right, or of its own organization. In this video, I'm going to demonstrate how to use IAM to secure your REST API. So once I'm in my API Gateway console, I come to the API I want to secure. A couple things we have to take note. We have to make sure that the IAM users that are going to be using the API have the appropriate IAM permissions to invoke these APIs. And we also need to make sure that we get a secret access key, and we also need to tell the methods to use IAM authentication. So in this case, I have a get method, right? It's already deployed. If I look at stages and click the deployment on the dev stage, you'll see that I can view it fine, no problem, no security. So first thing we should do is go into IAM, right? So we have a user here. It's called developer. It has the Amazon API Gateway Invoke Full Access permission. We also have the security credentials over here as well. I'm also using Postman to make my API calls. So let's go back and secure the API. So we come back under resources. We come back on the get method of the resource, and you want to go into method request. So I click on method request, and you'll see under settings authorization. We can change this to be AWS IAM authorization. And we click the check mark, OK. And at this point now, we need to deploy the API again because we made that change. At this point now, we should not be able to access it because it needs authorization. And now we have missing authentication token, so we can't access it. So in order to change that, we need to get our credentials and put them into Postman. So I'm going to be using Postman to make this call. So if I come into Postman, you'll see I'm going to do a get on my API. And if I just do a regular send without any authorization, you're going to see the security token included in the request is invalid. So if I come under the authorization tab, you'll see I don't have an access key or a secret access key. Type is also interesting to know for authorization. If you're using OAuth and user pools and identity pools, these options are here as well. But if you're using IAM, you want to choose AWS signature. So I'm going to go back under IAM, create a new access key. I'm going to copy the access key ID, paste it in. Then I'm going to copy my secret access key, paste it in. Now I'm going to do the request again. So I click send, and sure enough, we actually get the API back, right? And this was all done by our authorization. So you can use this for people in your environment or in your organization. If you want to give developers access to invoke APIs, you can even fine-tune it so they can only invoke specific APIs. But you can integrate IAM features with security. And if you followed along with this video, then congratulations, you just secured your REST API using IAM. How do I secure my API? Well, in comes Amazon Cognito. Amazon Cognito provides authentication and authorization and user management for your web and mobile apps. The two main components of Amazon Cognito are user pools and identity pools. User pools are user directories that provide sign up and sign in options for your app. They provide us with JSON web tokens so we can use it as an authorizer for any existing API, while with identity pools, we get temporary AWS credentials, which means that it's meant to utilize AWS resources. Identity pools enable you to grant your users access to other AWS services. You can use identity pools and user pools separately or together. Amazon Cognito user pools. They control access to a REST API using something called an authorizer. So an authorizer is an alternate to using the IAM roles and policies or Lambda authorizers, which we used to know as custom authorizers. You can use an Amazon Cognito user pool to control who can access your API. So we first have to create the authorizer of the Cognito user pools type, then configure an API method to actually use that authorizer. After the API is deployed, the users have to sign into the user pool and get their identity or access token. The API is then called with one of those retrieved tokens, and it's typically set in the request authorization header. The API call succeeds only if the token is supplied and is an actual valid token. If not, you will not receive any results. The identity token is used to authorize API calls based on identity claims, right? So username and password. The access token is used to authorize API calls based on some of the scopes we define in our resources. To create our Amazon Cognito user pool for your API, you must go into the Amazon Cognito console or the command line or the API to create a user pool, or you can use one that's already in your organization in another AWS account. Create the API gateway authorizer with the chosen user pool, and then enable the authorizer on the selected API methods. So we create our user pool with our users, we create our gateway authorizer, we associate it with that user pool, and then we enable the authorizer on the selected API method. Amazon Cognito identity pools, these are federated identities that will enable you to create unique identities for your users, and it integrates with identity providers for federation. So with identity pools, we get temporary AWS credentials to utilize AWS resources. So the following are supported identity providers. First, we have developer authenticated. So we can register and authenticate our users in our own existing authentication process. We can integrate it into what we are already using. OpenID Connect. Amazon Cognito supports OpenID Connect and linking of identities that are in your identity and access management service. There's also user pools. So Amazon Cognito user pools, which you just talked about. So we can kind of combine identity pools and user pools for even more secure solution. We also have public providers, such as logging in with Amazon or Facebook or Google. And we have SAML identity providers. So if you have authentication with identity providers through Security Assertion Markup Language or SAML 2.0, Cognito will support that as well. To call the API methods with the user pool enabled, your API clients must use the Amazon Cognito CLI or SDK or API to sign our user into the chosen user pool and obtain any identity tokens or access token. If you're using a client-specific framework, to call the deployed API gateway API and then supply the appropriate token in the authorization header. Right, so we got two ways here. If you're using the command line or the API for Cognito, we choose our built-in user pool and then we get our identity or access token that way. If we're using a client-specific framework, we'll call the deployed API gateway, put the supplied token in the authorization header, and then we should have access to the API. In this video, I'm going to demonstrate how to create and manage a user pool, how to manage an identity pool, and how to combine the two for a secure API solution. So we know that user pools are just simply user directories. You can have users sign up and sign in. Identity pools are AWS credentials that allow users short-term access to your AWS resources. So let's go ahead and create our user pool. So we have no pools created. We click user pool and we'll call it tech pool. So we have two options when we create our pool. We can start by reviewing the defaults and then customizing, or we can step through each setting. So let's review the defaults and then change them as required. So pool name is still tech pool. If we come into attributes, how do we want the users to sign in? So we can go by username, or we can go by email address or phone number. So if we choose username, users can use a username, and we can also optionally give them the opportunity to sign in with a verified email address or a phone number, or with a preferred username, which is a username that your users can change. So I'm going to leave it on username, and I'm also going to allow them to sign in with a verified email address. Enabled case insensitivity for user input, so we don't, it doesn't matter if it's a capital R or a lower R, it's still going to work. And which standard attributes do you want to require for your user pools? Email, it's fine. We can also choose name, given name, should we want to. I'm going to stick with the default email. We can also add custom attributes. It's just a key value pair. Maybe we want to add a job function, but we don't need to in this case. So we'll click next step. Then we get into password policies. So what's the minimum length? 8. Required numbers, special characters, uppercase and lowercase. Do you want to allow users to sign themselves up? So should it only be administrators to create the users, or should you allow users to sign themselves up? It'll take a big burden off the administrators if users sign themselves up, and then the administrator can verify them. And then we can also say how long before these passwords expire if they're not in use, and we'll go with 7 days. So we click next. Do we want to enable multi-factor authentication? We're going to say no, but we can make it optional or required. If we do, then we got to decide, should it be text message, should it be time-based one-time password? Account recovery, email if available, otherwise phone, but don't allow a user to reset their password via phone if they're also using it for a multi-factor authentication. That makes sense from a security standpoint. What attributes do we want to verify? I'm going to go with just email. Amazon Cognito will then create the role. We click next. Do you want to customize your email address so we can send emails from SES, Simple Email Service? Or I can just use the default Cognito. So the difference is, if you need higher limits, use Amazon SES, because Cognito has some daily email limits. So if you use SES, you've got to verify your email address with SES before you can use it. So do we want to customize our email verification messages? We can have a link or a code, and this is what the email will look like. Do you want to customize your user invitation messages? So your username is and your temporary password is, and it's all provided to the users. So we click next step. We can add some tags. We'll say for app production, just so we know what stage we're using this pool for. Do we want to remember our devices? That would involve user opting in or always. We're going to go with no. We don't want to remember the devices. Is there any app clients that we need to give access to this pool? We can add one. So we can enable Lambda trigger-based custom authentication, refresh tokens, right? So we don't need any in this tape, so we can cancel. We click Next, and now we have some workflow triggers. So we can invoke Lambda functions, say on pre-sign-up or pre-authentication. We can also, if there's a post confirmation, we can invoke a Lambda function. We can invoke a custom message dynamically. We can create and verify authentication challenges. And we can migrate users over via Lambda functions. So any functions that we have would be down in the Dropbox. We're going to use none right now and click Next. Just to review, you see in the red, you've chosen to have Cognito send emails. Best practice is to just send emails through SES for production user pools due to a daily email limit. So for our testing, Cognito is good. For production, try to use a SES. So I come down, I create my pool. The pool is successfully created. Now I have my number of users. And down the side, we see everything we did when we started up. So attributes, policies, right? We saw all that when we set it up. Multi-factor authentication, advanced security. So let's go back to users and groups. So at this point, we can create a user. We'll give it a name of A. Smith. We're going to send it by email. Again, remember, casing doesn't matter, right? It's insensitive. We'll give it a temporary password. That meets all the requirements. We don't need a phone number because we're just verifying based on email. And we'll give it the email address of the user. So we can go ahead and create our user. Our user's created. I have A. Smith and J. Smith. J. Smith had the email verification and the phone number verification. A. Smith had just the email verification. So if I click the user, I can come in and see if it's part of any groups. I can enable multi-factor authentication. Tells me when it was modified, when it was created. Is the email verification set to true? And their email. And then if they register, we'll see their devices down below. So now we have our users created, our pool created. We want to integrate this into identity pools. So first thing we need to do is create an app client. Right? App clients can use different identity providers, but you have to enable at least one identity provider for each app client. So we have to create our app clients. So if we come out to App Client and click Add an App Client, we can call this Tech App. The token will expire in 30 days. We want to generate that client secret. And we're going to allow Lambda trigger-based authentication. We're going to enable user password authentication for admin APIs. And we're going to enable username password-based authentication. So we create our app client. We copy the app client ID. And we can return to our pool details. So now, if we come back into Cognito, we can manage an identity pool and use our user pool as our identity provider. So we'll call this Tech Identity Pool, right? We can enable access to unauthenticated identities. So that's people who don't sign into the app, but they can still view it. So we're going to leave that off because anyone with internet access can be granted AWS credentials with this option. Authentication flow settings, you have an enhanced and basic. Enhanced is the default. So we're going to leave that as it is. And the big part is the authentication providers. Who are we going to use as an authentication provider? So we can use Cognito, we can use Amazon, Apple, Facebook, Google, Twitter, OpenID, which is the open source, and SAML 2.0 version. So we already have a user pool, right? So we're going to configure this identity pool to accept the users that are in my user pool. So we have to give the client ID, which we copied. We also need the user pool ID. So if I come back to Cognito, come back into user pools, I need to get that user pool ID right here. I'll copy that. And I come back in and I paste it under user pool ID. And now I create pool. The pool creates successfully. But first, I have to assign one or more IAM roles to determine the level of access you want your application end users to have. So any users that using that application that I specified, how much level of access do you want to grant them? So right now, your authenticated identities would like access to Cognito. We'll create a new IAM role. The Cognito Tech Identity Pool authentication role. And our unauthenticated identities would also like access to Cognito. Create a new role called Cognito Tech Identity Pool unauthorized role. So you want to define these policies with the principle of least privilege. So the policy should only have permissions that they need. So we can view the policy documents, right? So anyone authenticated who want to access, allow them to put events, allow them to sync Cognito. Any unauthenticated identities, they're allowed to put events and sync Cognito on all resources, but you'll notice that they don't have the Cognito identity action. So these are just roles. We can change them as we want to. I'm going to allow this. The roles were created successfully. Now I have the options to download the AWS SDK, get my AWS credentials, and then initialize the credentials with the provider. So if I come back into my dashboard, that was just some sample code. You'll see total identities are 0 right now. If we go into Identity Browser, we can look and see we don't have any identities because no one has tried to use their username and password to authenticate with our user pool using this identity pool. So I hope this video helped you understand how to create user pools, how to add users to the user pool, whether it's via a Lambda function, importing them, creating them, or having users join them themselves. And then how to create identity pools to be able to authenticate with those user pools as a form of federation. Now you can use both, and you don't even have to. You can use just a regular identity pool and federate with, say, Facebook for your users, right? So if you're using a web app, chances are you won't have users in the Cognito user pool, so you can federate with, say, Facebook or Twitter or Google. But if it's an internal app and you're running a user directory, then by all means you create your own user pool and you can integrate your identity pool with it just like we have done. In this video, I'm going to demonstrate how to use the Amazon AWS command line interface to create an AWS RDS Aurora cluster. That is, and this is the key point, serverless. Okay, so you can have an Aurora database that's not serverless, right? You can employ RDS that's not serverless, but if we specify an engine mode of serverless when we create our Aurora cluster, then it will be considered a serverless architecture. So once we're in our command line, our command begins with AWS RDS create DB cluster. So we have to give it some parameters, right? One of these is going to be the DB cluster identifier. And we're going to call it our first cluster. Next, we have to specify the engine. So we want Aurora, and then we specify the engine version. We want 5.6.10a. Then we need to specify, and here's the important part, engine mode is serverless. That's what makes this serverless. We can put in our scaling configuration, and we can specify a min capacity of, let's say, 4. and a max capacity of 16. We specify our seconds until auto pause. So when do we, after no activity, when do we want to pause it, right? So we don't get those charges for nothing, just idling. So we'll say 1,000, and then we also have to turn on auto pause. So auto pause equals true. Then finally, we have to specify a master username. We'll say admin, and a master user password. And we'll say the ever secure password 1. So, and we look over it, right? We're creating a DB cluster called our first cluster using the Aurora engine version 5.6.10a. A serverless engine mode. We're scaling from 4 to 16. We'll wait 1,000 seconds until we auto pause, and we set our username and password. So we go ahead and hit enter, and you see the output return. So that indicates that it was a successful creation. So the database cluster is created. Here's the JSON. Availability zones 1C, 1E, 1D. Shows you your backup retention period, your cluster identifier, the parameter group, your endpoint, your reader endpoint, your master username, your preferred backup windows are already set, security groups are created for you, your hosted zone ID, your KMS key, the cluster ARN, right, the engine mode. So it's all there. That tells us that we have a working serverless database. So if we want to just confirm in the console, we come into our RDS console and come under databases, and you'll see our first cluster is here, and it's serverless. I had an old database from previous times that is not serverless, and you can see that it says regional. Okay, so you scroll over, it shows you the size. It's currently being created, right? We can click on it. We can come in and look at any of the monitoring, once it's been created, right? So it's still in creating mode. Come back to database, come back to our command line. Some of the other commands that we can run in RDS, right? So we type AWS RDS help, and we can see add options to option group, add a role to DB cluster, right? Add tags, cancel any export task, create global cluster, delete a cluster, describe a cluster, right? Describe subnet groups, proxies, events. So there's a ton of stuff that we can do. We can stop the database cluster, we can stop a database instance, right, all from the command line itself. So one more check back at our database. You'll see that it is now available and ready to go. Current capacity is running at 8 capacity units. And all your info is down below, your endpoint, your default VPC with your subnets, and any monitoring, logging, configuration is there. You can change your backups here, or you can do it in the command line. So congratulations, you've created a serverless Aurora cluster using just the AWS command line interface. So in this course, we've examined the use of AWS Lambda and other Amazon services to create and manage serverless applications on AWS. We did this by exploring the AWS Serverless Application Model and the differences between AWS Serverless and standard 3-tier applications, how to install and configure the AWS SAM command line on Windows 10, how to create a SAM template, Lambda function, and event source, and how to create a static website using Simple Storage Service S3. API gateway stages and how to deploy an API to a deployment stage, how to define API gateway mappings export an API gateway, and use API gateway to implement a cache for an API. We also looked at how to enable and configure logging, tracing, and cross-origin resource sharing for an API, how to use IAM features to secure an API gateway deployment, the use of Amazon Cognito for authenticating, authorizing, and managing users, how to create a user pool and an identity pool using Cognito, and how to use the AWS CLI to create an Amazon Aurora serverless cluster. In our next course, we'll move on to explore how to configure and work with the DynamoDB NoSQL database service offered on AWS, including indexes, table properties, security, and backups.
In this video, we'll explore the DynamoDB NoSQL database service. Amazon DynamoDB is a NoSQL database service that's both fast and predictable. It's a fully managed service, so that means that much of the administration workload associated with the operation of a distributed database is handled automatically for us by AWS. So no worrying about provisioning servers and other resources. Plus, it scales as required and provides encryption at rest to secure our sensitive data. DynamoDB also has on-demand backup capability, allowing us to create full backups of our tables for long-term retention and archival to meet regulatory compliance requirements. Traditionally, developers have worked with relational database management systems and structured query language, or SQL. DynamoDB, on the other hand, is a NoSQL database, and that implies that it's a non-relational database. It uses non-relational models for data management, like key-value pairs and document database storage. In general, NoSQL databases are ideal for mobile, big data, and web apps that demand seamless scaling and very low latency response. In DynamoDB, data is stored on solid-state disks, and the data is automatically replicated across multiple availability zones within an AWS region. This results in a highly available and durable data storage solution that automatically distributes data and traffic for our DynamoDB tables over as many servers as required in order to handle the throughput and storage demands. In addition, we can use global tables, which are designed to keep DynamoDB tables in sync across AWS regions. Now, let's consider the essential components of DynamoDB. First, we have tables, and these are similar to the tables you'll find in other database management systems. A table is simply a collection of data. For example, you could have a users table that stores information related to users. Each table, in turn, contains items. An item is a unique group of attributes. In a users table, for example, each item represents one user. In DynamoDB, items are similar to rows or records in other database systems, and with DynamoDB, the number of items we can store in a table is virtually limitless. And carrying on, each item has one or more attributes. An attribute is a fundamental data element that describes an item. For example, an item in a users table may contain attributes like user ID, first name, last name, email, and so on. Attributes in DynamoDB are similar to fields or columns in relational databases. Data types supported by DynamoDB include string, number, binary, Boolean, and null scalar data types. Document types supported include list and map, and set types supported include string, number, and binary sets. When you create an Amazon DynamoDB table, you must specify a table name along with its primary key. Each item in the table has a unique primary key. DynamoDB supports two types of primary keys. The partition key is a simple primary key composed of one attribute, and no two items share the same key. The partition key's value is used by DynamoDB as input to an internal hash function, and the output from that hash function controls the partition where that item is stored. Then we have a composite primary key, and it's composed of two attributes: the partition key, which is the first attribute, and the sort key, the second attribute. Here again, the partition key's value is used as input to an internal hash function, with the output determining the partition where the item is stored. With a composite key, all items having the same partition key value are stored together, sorted by the sort key value. A table with a partition key and a sort key may have multiple items with the same partition key value, but if that's the case, they must all have different sort key values. After all, the composite primary key must uniquely identify an item. Note that each primary key attribute must hold only a single value, and the valid data types for primary key attributes are string, number, or binary. One important option from DynamoDB is a feature called DynamoDB Streams. DynamoDB Streams captures events relating to data modifications that occur in DynamoDB tables. Data relating to the modification events appears in the stream in near real time in order of their occurrence. Each event is a stream record. If DynamoDB Streams is enabled for a table, it writes a stream record each time a new item is added to the table, in which case it captures all the new item's attributes. Each time an item is updated, the stream captures the before and after attributes that were modified, and each time an item is deleted from the table, it captures the entire item before it was deleted. Stream records also capture the table name, the timestamp of the event, as well as other important metadata. Stream records persist for 24 hours, after which they are automatically removed from the stream. In this video, we'll examine DynamoDB's provisioned throughput. Amazon DynamoDB offers two read-write capacity modes for processing reads and writes against tables. They are on demand and provisioned, which is the default and free tier eligible option. The read-write capacity mode determines how we're charged for read and write throughput and how we manage capacity. This can be set when a table is created, or it can be changed afterwards. On-demand mode is a flexible billing option that can serve up thousands of requests per second with no capacity planning. DynamoDB On Demand has pay-per-request pricing for read and write requests, and it's just basically another service on AWS that allows us to pay only for what we use. In on-demand mode, DynamoDB instantly scales to handle workloads as they ramp up or down as required. Note that on-demand is available for new and existing tables and does not affect the existing DynamoDB APIs, so no code changes are required. The only limit on request rate is imposed by the DynamoDB throughput default table quotas, but request rate may also be raised. To use provisioned mode, we specify the number of reads and writes per second that are required for our application. We can leverage autoscaling to adjust provisioned capacity automatically based on traffic changes. This allows us to stay within defined request rates for cost predictability. Provisioned mode is most applicable when you have a predictable, consistent, and gradually ramping traffic pattern where we can forecast capacity. Some considerations when changing read-write capacity mode. First, recognize that you can change read-write capacity modes only once every 24 hours. When managing capacity, if we're updating from provisioned to on-demand mode, we needn't specify how much read and write throughput we expect from our application. Now, when going from on-demand to provisioned mode, initial provisioned capacity depends on the environment that you're doing that from. Now, if we're using the AWS Management Console, the console estimates initial provisioned capacity based on consumed read and write capacity of our table and global secondary indexes over the past 30 minutes, but we can also override these values. If we're using the AWS CLI or SDK, we should use Amazon CloudWatch to determine what our historical consumption is and use those values to establish new throughput settings. With respect to managing autoscaling, when updating a table from provisioned to on-demand mode, if we're using the console, all existing autoscaling settings are deleted. In the AWS CLI or AWS SDK, all of our autoscaling settings are preserved and therefore may be applied if we update our table back to provisioned mode again. When updating a table from on-demand to provisioned mode, in the console, DynamoDB recommends enabling autoscaling with some specific default values, including a target utilization of 70%, a minimum provisioned capacity of 5 units, and a maximum provisioned capacity based on the maximum for the region. Using the AWS CLI or SDK, our previous autoscaling settings are preserved. In this video, we'll explore the DynamoDB API. The DynamoDB API provides access to different types of operations, which may be categorized as control plane operations, data plane operations, transactions, and DynamoDB streams. Let's have a closer look at these 4 different types of operations. Using the control plane operations allows us to create and manage DynamoDB tables and work with other objects associated with tables like streams and indexes. The create table action creates a new table. We may also create secondary indexes and enable DynamoDB streams for a table with the create table action. Describe table retrieves information about a table like its primary key schema, index details, and throughput settings. List tables returns a list of all our tables. Update table actions are used to modify table settings, indexes, and DynamoDB streams, and to create or remove indexes. And the delete table action removes a table along with its dependent objects. Data plane operations allow us to perform the so-called CRUD actions on a table. That's create, read, update, and delete. For creating data, we have actions like putItem, which writes a single item to a table, and batch write item, which writes multiple items to a table up to 25 items per operation. Batch write item is far more efficient than calling putItem multiple times, since only a single network round trip is needed to write the batched items. Batch write item can also be used for deleting multiple items from tables. For reading data, there's getItem, batch getItem, query, and scan, which provide various methods for retrieving data from tables. Updating data actions include update item, which modifies an item's attributes. And for deleting data, we have delete item, which removes a single item from a table, and batch write item, which may delete as many as 25 items from tables in one operation. Similar to writing in batch, deleting in batch is more efficient than calling delete item multiple times. Next, we have transactions. DynamoDB transactions are ACID compliant, so they're atomic, consistent, isolated, and durable, which helps guarantee the validity of the data. Here we have transact write items, which is a batch operation allowing put, update, and delete operations, providing a guaranteed all or nothing result. And transact get items, which is a batch operation allowing get operations for retrieving multiple items from tables. Then there are DynamoDB stream operations, which allow us to enable or disable a stream on a table. Here we have list streams, which returns a list of all of our streams. Describe stream, which returns information about a stream like its Amazon resource name or ARN. We also have get shard iterator, which returns a shard iterator, which is simply a construct that we give to our application so it can retrieve records from the stream. And get records, which returns stream records by using a shard iterator. In this video, we'll explore DynamoDB indexes. DynamoDB supports secondary indexes on tables. A secondary index allows us to query data in a table using an alternate key in addition to queries based on the primary key. Secondary indexes, therefore, provide greater flexibility for querying data. Once we've created a secondary index on a table, then we can just read data from the index similar to how we would read data from the underlying table. There are two types of indexes supported by DynamoDB: a global secondary index and a local secondary index. Each DynamoDB table has a quota of 20 global secondary indexes and 5 local secondary indexes per table. Every secondary index is associated with one and only one table where it gets its data from. This is known as the base table for the index. A global secondary index is an index with a partition key and a sort key that may be different from those associated with the base table. It's considered global because queries on a global index may span all data across all partitions in the base table. A global secondary index resides in its own partition space separate from the base table and also scales separately from the base table. To create a table with global secondary indexes, we use the createTable operation with the global secondary indexes parameter. Then we specify the alternate key, one attribute as the index partition key, and optionally, another attribute for the index sort key. Neither of these key attributes need to be the same as those in the base table. Each index key attribute must also be scalar data of the type string, number, or binary, so it cannot be a document or a set. We also define the attributes from the base table that we want to copy or project into a global secondary index, including scalars, documents, and sets. A global secondary index inherits the read-write capacity mode from its base table. A local secondary index is one that has the same partition key as the base table, but a different sort key. A local secondary index is considered local since every partition of a local secondary index is mapped to a base table partition with the same partition key value. To create local secondary indexes when creating a table, we use the createTable operation with the local secondary indexes parameter. When a table is deleted, so too are any local secondary indexes on that table. When we create the local secondary index, we must specify one non-key attribute, and that will be the sort key for the local secondary index. The attribute must be scalar data of the type string, number, or binary. To determine the type of secondary index to use, it's important to carefully weigh our application's requirements. And with that in mind, let's consider how the characteristics of the different secondary index types compare. First, with respect to key attributes. With a global index, the index partition key and the index sort key may be any attributes from the base table of string, number, or binary data type. For a local index, the index partition key attribute is the same as the base table partition key attribute. The sort key may be any attribute from the base table of string, number, or binary data type. For key schema, with a global index, the primary key can be a simple or composite key, while the primary key of a local index must be a composite key. So both partition and sort keys are required. For online index operations, global secondary indexes may be created when the table is created, but you can also add a new global secondary index to an existing table or delete an existing global secondary index. Local secondary indexes, however, are only created when we create the table. We cannot add a local secondary index to an existing table, and we cannot delete any existing local secondary indexes. For our projected attributes with a global secondary index, when we perform queries or scans, we can only request the attributes that are also projected into that index. DynamoDB will not fetch items from the base table. However, when we perform a query or scan on a local secondary index, we can also request attributes that are not projected into the index. In this case, DynamoDB will pull those attributes from the base table. With respect to provisioned throughput consumption, each global secondary index carries its own provisioned throughput settings, and queries or scans on a global secondary index consume capacity units from the index, not from the base table, and the same applies for global secondary index updates because of table writes. Queries or scans performed on a local secondary index consume read capacity units from the base table, and when we write to a table, its local secondary indexes are also updated, meaning that the updates consume write capacity units from the base table as well. Now, considering queries and partitions, a global secondary index allows us to query against the entire table across all partitions, while a local secondary index only allows us to query over a single partition. For read consistency, queries on global secondary indexes support eventual consistency only, but when querying a local secondary index, we can specify whether we want eventual or strong consistency. And considering size restrictions per partition key value, for global secondary indexes, there are no size restrictions, whereas for local secondary indexes, for each partition key value, the size of all indexed items must not exceed 10 gigabytes. In this video, we'll explore the DynamoDB concurrency model. Database concurrency describes the ability of a database to allow multiple users to affect multiple records, essentially concurrent updates. An optimistic concurrency model uses optimistic locking, and DynamoDB is an optimistic locking database. DynamoDB verifies that the client-side item being updated or deleted is the same as the item in Amazon DynamoDB. With this strategy, our database rights are protected from being overwritten by others, and that we don't overwrite someone else's updates as well. Under an optimistic locking strategy, each item has an attribute that serves as a version number. Let's say we retrieve an item from a table. The application records the version number of that item. We can update the item only if the server-side version number hasn't been changed. If there is a version mismatch, it signals to DynamoDB that the item was modified by someone else before we did. This means we have a stale version of the item and our update attempt fails. When this occurs, we simply try again by retrieving the item and attempting to update it again. The AWS SDK for Java provides the DynamoDB version attribute notation to support optimistic locking. To use the annotation, in the mapping class for our table, we would assign one property as the version number and mark it using the DynamoDB version attribute notation. The DynamoDB mapper assigns a version number when we save an object for the first time, and this version number is automatically incremented each time the item is updated. Our update and delete requests will only be successful if the client-side object version matches the version number of the corresponding item in the DynamoDB table. A conditional check failed exception is thrown if the version value on the server is different from the value on the client, or if we specify conditional constraints of our own when saving data using DynamoDB mapper with DynamoDB save expression and our constraints fail. Optimistic locking impacts DynamoDB mapper methods. For the save method, if it's a new item, the DynamoDB mapper assigns an initial version number of 1. If an item is retrieved and some of its properties are updated, if we attempt to save the changes, the operation will only be successful if the version number on the client side and the server side match. The DynamoDB mapper increments the version number automatically. In the case of the delete method, it takes an object as a parameter, and the DynamoDB mapper does a version check prior to deleting the item. Note that the version check can be disabled in the request. And for transaction write, for puts and updates, if a new item, DynamoDB mapper assigns an initial version number of 1, and subsequent updates are only successful if the version number on the client side and server side again match. To disable optimistic locking, we change the enumeration value of the DynamoDB mapper config save behavior from update to clobber. We can also set locking behavior for a specific operation. For example, we could add the DynamoDB mapper config parameter to the save method and thereby set the locking behavior for this specific operation. Note though that disabling optimistic locking for transaction write is not supported. In this demo, we'll create a table and we'll define the table's properties, including the read and write capacity units and both global and local secondary indexes. Okay, so I've signed into AWS Management Console. In Find Services, I'll start typing DynamoDB. And in the list that returns, I'll select DynamoDB to go to the DynamoDB dashboard. I'll click Create Table. My table name is going to be orders, so I'll specify orders in the table name field. Now for my partition key, I'm going to have order ID as my partition key. I will have a sort key, so I'll click the Add Sort Key checkbox, and I'll specify customer ID for my sort key. Okay, now scrolling down, I'll uncheck Use Default Settings, and under Secondary Indexes, I'll select Add Index. Now in the Add Index dialog that appears for my partition key, I'll specify order ID again, and when I check the Add Sort Key checkbox or click out of this field, the Create as Local Secondary Index checkbox will be activated. So I'll click Add Sort Key, and now the Create as Local Secondary Index checkbox is now activated. So I'll click to select it because we're creating this as the local secondary index. And the reason it did that again is because the order ID, which is my partition key, is the same as the underlying table, and that defines a local secondary index. Okay, so now for my sort key, I'll specify order timestamp. For index name, I'll leave the default, very descriptive name. For projected attributes, if I click the down arrow, I have a choice. I can select all, I can have it return keys only, or select include. And if I select include, that means that in addition to the attributes in keys only, the secondary index will also include other non-key attributes that we can specify. But for this, I'll leave all selected, and I'll click Add Index. Now I'll click Add Index one more time. This time for the partition key, I'm going to specify country. That is a string, so I'll leave the string data type selected. I'll click the Add Sort Key checkbox, and my sort key is going to be order total. I'll select the down arrow on the data type list box, and I'll select number as the data type. Again, I'll leave the default index name and projected attributes. I'll just pull in everything, and I'll click Add Index. Okay, now scrolling down. For read-write capacity mode, I'm going to leave provisioned, which is the default selected. It's free tier eligible. Now scrolling down, I'll uncheck the read capacity and write capacity checkboxes because we're going to specify them here. Now I'll click the capacity calculator, and in the capacity calculator that appears, I can specify the average item size. I can also specify the item reads per second, as well as whether it's eventually consistent, strongly consistent, or transactional. I can specify the item writes per second, either standard or transactional. And that leaves me with a read capacity of 1 and a write capacity of 1. And that's good for my demo. So I'll just click Update, and all my read and write capacity unit settings will be 1. Okay, scrolling down, for encryption at rest, I'll leave the default selected. The key is owned by Amazon DynamoDB. We're not charged a fee, and this is really an excellent selection. So I'll scroll down, and I'll click Create. And now my table is being created. So now down in the taskbar, I'll click the Visual Studio icon to bring up Visual Studio Code. And I've got a Python script open that I'm going to use to write items to my table. Now I won't go over this code extensively, I just want to go over, for example, lines 15 through 21. So basically, I'm specifying my items here. I'm using the batch writer and the put item method, and my item is going to have a customer ID on line 16, an order ID on 17, a name on 18, the country on 19, order timestamp on 20, and the order total on 21. And if I scroll down, the other 4 items that I'm going to write to my table are similar. Okay, so now let's make sure that the table is created. So I'll click the browser icon to bring up my orders table, and it has been created. If I click on items, well, right now I have no items. So now let's go back to Visual Studio Code. Now that we know that the table is created, let's go into the terminal session, and we'll run this script by typing Python and the name of the script, which is dynamo_batch_writer.py. Now I'll press enter, and a message appears saying successfully wrote items/records to the orders DynamoDB table. All right, so now let's go back to the taskbar. We'll bring up the browser again by clicking the browser icon. Here's our orders table. Now, if I click Start Search, that does a scan on the entire table. I can see the records that I just added here. So now, if I want to query by one of my indexes, for example, if I click the down arrow beside Scan and select Query, I'll now be able to select my indexes, my global index, my local index. And so, for example, let's say that we're going to do a search by the local index first. I'm going to specify an order ID of 6,000. And I won't specify a sort key for this part of the demo. I'll just click Start Search. And that returns the only item with an order ID of 6,000 here. Okay, so now scrolling back up, let's say that I want to search by the global index. I want to search by country and the order total. So I'll select country and order total, and I'll specify for country a string, which is US, and for order total, I'm going to specify that my order is greater than 1,000. Scrolling down, click Start Search, and that returns 2 records, or 2 items. So order ID 5003 has an order total of 10,000. Order ID 5000 has an order total of 11,000. So now if I made this number in order total greater than 10,000, then that should eliminate order ID 5003 from appearing in the results list. So I'll click Start Search, and lo and behold, it's gone. Okay, so we've successfully created the table, and we've created a global secondary index as well as a local secondary index, and specified the read and write capacity units for this table. In this demo, we'll examine how to create a DynamoDB accelerator cluster. A DynamoDB accelerator, or DAX cluster, is basically in-memory acceleration, a cache, if you will, for DynamoDB. In most scenarios, the DynamoDB response times are in the range of single-digit milliseconds, but some use cases may require response times in microseconds. For these situations, DAX delivers super-fast response times when accessing eventually consistent data. DAX addresses 3 core scenarios. As an in-memory cache, DAX slashes response times from single-digit milliseconds to microseconds. DAX reduces complexity as well. As a managed service, it's compatible with DynamoDB API, requiring minimal changes to use with an existing application. And for read-heavy or workloads that spike, DAX can provide elevated throughput and potentially save on operational costs too by eliminating the need for over-provisioning read capacity units. This is particularly useful to address situations where applications must perform repeated reads for specific individual keys. Okay, we're going to create a DAX cluster using the console. I've signed into AWS Management Console, and I've navigated to my DynamoDB dashboard. In the left navigation menu, under DAX, click Clusters. There are no clusters created yet, so I'll click Create Cluster. I want to give my cluster a name first, so I'll specify my DAX cluster. Now for node type, if I click the down arrow, I have quite a range to select from. I have all the way from a T2 small to an R4 16 extra large. I'll leave the R4 large node type selected. Now for cluster size, if you want a single node cluster, we could specify 1 here. In that case, the cluster consists of 1 primary node, and that's it. But if you want to create a multi-node cluster, we choose a number between 3, which is the default, and 10. So 3 means that we have 1 primary and 2 read replicas. Now we could choose up to 10, which would give us 1 primary and 9 read replicas. For cluster size, we'll choose 3. Scrolling down, encryption is enabled by default, and to protect my data at rest, I will leave it enabled. Now we have to specify an IAM service role for DynamoDB access. Now here's the thing, because we're using the console, this workflow checks for the presence of a pre-existing DAX service role. If one doesn't exist already, then the console creates a new service role for us. If I click the down arrow here, I'll see that I don't have an existing service role. So I'll click Create New, and that opens up the area below for me to specify the IAM role name. Now I'll leave the default DAX to DynamoDB. I think that's a good name. And for the IAM role policy, the default is no policy, but I want read-write access. So I'll click the read-write option, and that opens up a field above to specify the IAM policy name. The default DAX to DynamoDB policy is a good name, so I'll leave it. For target DynamoDB table, I could choose an individual table, but I'll just leave all tables selected. We want to select a subnet group for our DAX cluster, and that will determine the VPC and availability zones for our DAX nodes. So I'll click the down arrow beside subnet group, and I'll click Create New. So now in the area below, I'll give the subnet group a name. I like the default name, my-subnet-group, so that's what I'll specify. And I'll leave the description blank. Now we choose a VPC. I'll select the down arrow beside VPC ID, and I'll choose the VPC labeled VPC-A86 and so on. And scrolling down, for security group, if I click the down arrow, I have a number of different security groups. I'll just select the default security group. Now I will leave the Use Default Settings checkbox checked. What that means is that we'll have an automatic cache eviction enabled with a TTL 5 minutes. We're not specifying any preference for availability zones, nor for a maintenance window, and notifications are disabled. And at this point, you're ready to launch the cluster. Now I'm actually not going to go all the way and launch the cluster, because if I were to do that, this is not in the free tier. But we've seen how to successfully create and configure a DAX cluster. In this demo, we'll enable and work with DynamoDB streams. All right, I've signed into my AWS Management Console, and I've navigated to the DynamoDB dashboard. From here, to enable DynamoDB streams, we start by navigating to Tables. So in the left nav menu, I'll click Tables. Now I'm going to be working with the Orders table, so I'll click Orders. And now in the right side, under Stream Details, click Manage Stream. Now the Manage Stream dialog appears. Now we can choose what we want to appear in the DynamoDB stream when an event occurs. We can have keys only, that is the key attributes of the modified item. The new image, that's the entire item. The old image, that's the entire item as it appeared before it was modified. And the new and old images, so we get both. And I'm going to leave new and old images selected and click Enable. Now we need to create a trigger in order to be able to read the logs. So DynamoDB triggers hook up DynamoDB streams with Lambda functions. So when an item in the table is modified, a new DynamoDB streams record is written, which in turn triggers the Lambda function and causes it to execute. So to find the Triggers tab, click More, and there we'll find Triggers. So let's click Triggers. So now on the Triggers tab, click Create Trigger, and now select New Function. And this brings us right into the Lambda Management Console. And to start with, we need to give the function a name. So I'll call mine Lambda Trigger Function. And now we need to choose a role that defines the permissions of the function. So I'll specify create a new role with basic Lambda permissions. And this will create an execution role with permissions to upload logs to Amazon CloudWatch logs. But we'll have to come back later once we've created the function and modify permissions. So we'll do that shortly. Okay, so let's carry on. I'll click in the DynamoDB table field and I'll select orders. Now for batch size, we can specify the largest number of records that will be read from the table's update stream at one time, but 100 is a good size, so we'll leave the default. Now the batch window, it's optional. This is the maximum time that we'll gather records before invoking the function. Now this is optional, so I'll just leave it blank for now. Now for starting position, we want every event, clicking the down arrow beside latest, and I'll select trim horizon. There are additional settings, so if I expand additional settings, there's an on failure destination, which is a queue or topic ARN, retry attempts, maximum age of a record, split batch on error, and so on. I won't change any of these additional settings, so I'll close additional settings. Click the Enable Trigger checkbox. Here's the code that's going to be used for this function. So basically, this is going to capture all the events, and for each record, we will display to the console the event ID, the event name, as well as the record itself. Okay, so scrolling down, click Create Function. Okay, and our Lambda trigger function has been created. Now we see an error, and it tells us that the Lambda trigger function was successfully created, but there was an error when the trigger was created, and that error has to do with the fact that it can't access the stream. So we need to provide access to DynamoDB. So I'll click the Permissions tab, and we're going to edit the execution role. But under Resource Summary, I can see very clearly that I have Amazon CloudWatch logs access. But if I click the down arrow here, I should see DynamoDB, but I don't. And that's because no DynamoDB permissions were added to this role yet. Okay, so let's close this up and let's go back up. I'll click to open the Lambda trigger function role, and that opens it up right in IAM Management Console. Under Permission Policies, I'll select Attach Policies. And now in the search field, I'll just type Dynamo to bring up everything related to DynamoDB. And the one that we need is AWS Lambda DynamoDB execution role. So I'll click the checkbox beside it and select Attach Policy. Now a notification appears indicating that the policy has been attached to our Lambda trigger function role. Okay, let's go back to the Lambda function itself. So I'll click the Lambda trigger function tab. Now let's update the page. Scrolling down, if I click the down arrow under Resource Summary where Amazon CloudWatch logs is, I'll see now that I have Amazon DynamoDB permissions provided for this function. And we can see the resources and actions allowed. So all resources, and we're allowed to describe stream, get records, get shard iterator, list streams, and so on. These are the permissions that we require in order to interact with DynamoDB streams. Okay, now let's go back up and click on the Configuration tab. Now we need to add the trigger again because it wasn't added the first time because there was a failure. So I'll click Add Trigger, click the down arrow, search for DynamoDB, and select it. And now the DynamoDB table, let's click inside the field, we'll select Orders. Batch size is 100 still, that's fine. Trim horizon's good. And the trigger is enabled, so let's click Add. Okay, and so the trigger orders was successfully added to our Lambda trigger function. So the function is now receiving events from the trigger. So let's click the Monitoring tab, and now inside here we should be able to see any events that happen. Now, since no events happened, let's go back over to the DynamoDB console. So I'll click the DynamoDB AWS console tab, and now I'll click the orders table. I'll go into items, and now I'll change one of these items. I'll click to bring up order ID 5000, and I'll change the order total from 2500 to 11,000. Click Save. Okay, now let's go back over to the Trigger Function tab. Okay, where we're looking at the monitoring of CloudWatch metrics. Let's click View Logs in CloudWatch. If an error notification appears, just click View Existing Log Groups, and our Lambda trigger function should appear. So click AWS Lambda trigger function, and scroll down under Log Streams. We'll click the log stream, and it has our event in it. So if we look under Info DynamoDB Record, so I'll expand this event. Scrolling down, I can access the details for this event. So this tells me that we had a record that was edited. It gives me the key, the new image, and the old image, and some other information. All right, so we've successfully enabled and configured DynamoDB streams. In this demo, we'll enable DynamoDB Time to Live, TTL, to define when items in a table expire. TTL is a feature in DynamoDB that automatically deletes an item after an expiry date. Now, there is no cost. It also doesn't use read capacity units and write capacity units. It's a background task performed entirely by DynamoDB. Now, keep in mind that it doesn't happen immediately, but DynamoDB guarantees that any records that are supposed to be deleted will be deleted within 48 hours of the expiry date. When enabling TTL on a table, you have to specify attribute name that the DynamoDB service is going to examine to see if an item should be expired. The item must contain the attribute specified when TTL was enabled on the table. If it doesn't, the process ignores them. The TTL attribute's value must be a number data type, and the TTL attribute's value must be a timestamp in the Unix epoch time format in seconds. We'll see how to convert time to a Unix epoch time format shortly. But for now, let's start by creating a new table. Now I'm signed into AWS Management Console and I'm on my DynamoDB dashboard. So I'll select Create Table. Now I'll give the table a name. I'll just call my table TTL-demo. Now for a primary key, I'll just have a simple primary key, and the partition key is just going to be ID. Scrolling down, I'll uncheck Use Default Settings. Scrolling down, ensure that Provisioned Read-Write Capacity mode is selected, and I'll uncheck Read Capacity and Write Capacity, and I'll specify 1 for each. Now scrolling down, I'll leave the default encryption as it is, and I'll select Create. Okay, and now our table is being created. Once it's created, I'll be able to click the Items tab, and I'll create an item which will have the TTL attribute. So now the table's ready. I'll select the Items tab. Now I'll select Create Item. Okay, when I create an item, the ID attribute is there, so I'll just give it a value of 1000, and it's a string. And now I want to add an attribute, so I'll click the plus sign beside ID, and under Append, I'll specify the number data type, and now I'll specify the name expires. And for the value, I have to specify the Unix epoch date time. And for all intents and purposes, really the epoch is just the number of seconds that have elapsed since January 1st, 1970. Now, there's a neat website that you can use, and it's actually referenced by AWS if you view the documentation. So let's open a new tab, and we'll navigate to epochconverter.com. This displays the current Unix epoch time. I want this record to expire in an hour. So in the hour field, I'll increment it by 1. So I'll specify 10, click human date to timestamp, and now I'll copy the epoch timestamp. I'll highlight it, right click, select copy. Now let's go back over to our create item dialog, and I'll paste that epoch time into the value field and select save. Okay, so now we have our record. So let's go up to overview. Scrolling down, I'll select manage TTL. And for TTL attribute, I have to specify the field that I want DynamoDB to examine, and that will be expires. And I want to enable DynamoDB streams, and that by default uses a view type with new and old images. So I'll check the checkbox. AWS recommends that we run a preview to see what items will be deleted once TTL is enabled on the table. And we've got a reference time for items expiring by July 21st, 2020 at 03:59 UTC-6, which is the current time. Now, if I run preview, I'll find that I don't have any items expiring. And that's because I set the TTL attribute, the epoch time, to be over an hour from now. So we'll increment the hour by 2 hours. So I'll click the down arrow beside the hour and I'll select 5. And now if I select run preview again, the item does appear. Okay, so we've successfully enabled DynamoDB TTL. In this demo, we'll work with DynamoDB in the AWS command line interface. All right, to get started, I've opened Visual Studio Code, and I've got a couple of files open. I've got a README with a number of different commands, and I've also got an expression attributes.json file, and I'll explain how I'm going to use that shortly. But for now, let's examine these commands and use them in the terminal. So the first command is just AWS DynamoDB describe table, and I specify the table name, which is orders. So I'll highlight line 1, press Ctrl+C to copy, and now down in the terminal, I'll right mouse click to paste that command in and press enter. And that returns quite a bit of detail about my table. I've got the attribute definitions, I've got the key schema, the table status, the create time, the secondary indexes, both local and global, as well as the ARN and a bunch of other information. So quite a bit of detail. Okay, so now I'll clear by typing clear and pressing enter. Now, my second command is a DynamoDB scan command. Now here I specify the table name, but I'm also using another parameter called projection expression. And this just specifies what projected attributes I'm going to bring over when I do the scan. So let's highlight lines 3 through 5, Ctrl+C to copy. Now down in the terminal, I'll right click to paste it in, press enter, and that reports a count of 5, a scan count of 5, and scrolling up, I can verify that there are 5 items. All right, now let's clear, and now back up into the readme.txt file. Now, from line 7 through 9, again, I'm doing a scan on the table named orders, but I'm specifying this time a page size of 3. Now, the page size parameter, which is an integer, is the size that each page will get in an AWS service call. It doesn't, however, affect the number of items returned in the command's output. So setting a smaller page size simply results in more calls to the AWS service, retrieving fewer items in each call. And the reason why we use this is that this can help prevent AWS service calls from timing out. Okay, so let's highlight lines 7 through 9, Ctrl+C to copy, and now down in terminal, I'll right mouse click to paste the command in, and I see the count is 5, the scan count is 5, and it did in fact return all 5 records. Okay, so now again, let's clear. Now back up to the next command. Now in this command, I'm using scan again, but this time I'm specifying max items. Now, max items is also an integer, and this is the total number of items that are going to be returned in the command's output. Now, here's what happens. If the total number of items available is more than the value that we specify here, then a next token is provided in the command's output. And then to resume pagination, we need to provide the next token value in the starting-token argument of any subsequent commands. Okay, let's copy this, Control-C, and we'll paste this by right mouse clicking down in the terminal, and that returns 2 items only, although it does say count 5. The scan count is 5, but I can verify that there are 2 items. But I also see a next token. So I'll highlight the next token. I will right mouse click to copy that to the clipboard. Okay, so now again, let's clear by typing clear and pressing enter. Now back up to my readme.txt. I'll highlight token on line 18, and I'll paste the token that I just copied in. So when we run this scan, it's going to use the starting token, and it's going to return as many items as it can for the next pagination. So let's highlight lines 15 through 18, Control-C to copy. Now down in the terminal, I'll right mouse click to paste the command in, and there are 2 more records. Now the count says 0, the scan count says 0, and it has provided me with another next token. So I'm going to highlight this next token. Right mouse click to copy to the clipboard, clear by typing clear and pressing enter. Now up in the README on line 18, I'll highlight the former token value, and I'll paste the new token value in with Control-V. And now I'll highlight lines 15 through 18, copy with Control-C. Now down in the terminal, I'll right mouse click to paste that command in and press enter. And we return 1 item, and only 1 item this time. And notice that there is no next token provided with the output this time. And that's because we have 5 records in total in this table, and now we've cycled through all 5. Okay, so let's clear by typing clear and pressing enter. Okay, and for our last command, we're going to use the query command. So I specify the query command, the table is orders. Now I've got a projection expression, which is going to return order ID, customer ID, and the order timestamp. I specify a key condition expression, and that's order ID equals :V1, and that's on line 26. Now, what am I doing here? Well, I'm specifying the key condition expression, but along with that, I'm also specifying the expression attribute values on the subsequent line, on line 27. And I'm referencing a file. Now, that file is going to express what the value of V1 or value 1 is. So now clicking on the expression-attributes.json tab, I'll see from lines 1 through 3 that the value of V1, it's a string, and it is 5,000. So we're going to be looking for an order ID of 5,000. So clicking on the readme.txt tab again, that's the order ID that we're going to be looking for. Now, because this is a command with so many parameters, if you need to find help in the terminal, just type AWS DynamoDB query help and press enter. And this brings up the help pages for the AWS DynamoDB query command. Now, scrolling down through the help file for this command, under synopsis, I can see that query has 1 required value, and that's table name. But there are also several different parameters that I can use. Okay, so now let's press Q to exit out of here and clear to clear the screen. Now I'll go up in the readme.txt file. I'll highlight lines 23 through 27, Control-C to copy. Now down in the terminal session, I'll right mouse click to paste the command in and press enter. All right, now this should only have returned 1 record, and it did return 1 record. So it reports a count of 1 and a scanned count of 1. And it returned exactly the item that we were looking for in our query. Okay, we've successfully worked with DynamoDB in the AWS command line interface. In this demo, we'll work with DynamoDB transactions. The value of transactions lies in the fact that you can group actions together to be coordinated and submitted in an ACID-compliant transaction. That means atomicity, consistency, isolation, and durability. So basically with a transaction, when you have a group of actions that are performed together, if one of them fails, then the entire transaction fails. So it's all or nothing. All right, to get started, I've opened Visual Studio Code, and I've got a readme.txt file and another file, a transact-items.json file. I included in the README a note about how DynamoDB rejects the entire transact write items. There are a number of conditions, but for our use, we're going to introduce a user error, an invalid data format, as indicated on line 14. So our command for the transaction is on lines 1 through 4. So the command we use is AWS DynamoDB transact-write-items. That's line 1. Line 2, I'm using the return consumed capacity parameter, and I specify total. So that's going to return the total consumed capacity for the entire transaction. I'm also going to use the return-item-collection-metrics parameter, and here I'm specifying size. So this will return information about the item collection size. And then transact-items on line 4. Here I reference a file named transact-items.json, and it's in this .json file that I define the transaction. So let's go and have a look at the transact-items.json file. So I'll click the transact-items.json tab. So in this file, I've specified a couple of actions to collect together as a transaction. First, there's an update action starting on line 3. I include the key, the update expression, and in this case, that's set order total equals new val, and the new val is a value that I'm going to define under expression attribute values, which starts on line 9. So new val is a number, and it's 2500, and of course the table name is orders. Now on line 16, I'm specifying a delete action. I here again specify the key and the table name, but nothing else because I'm just going to delete this record. Now, here's the thing though. On line 19, I've introduced an error. The customer ID is not a number. It's actually a string. It is the number 1000, but it is a string data type, not a number. And here on line 19, I've specified a number. So in essence, what should happen here is when I run this transaction, it should fail and nothing should be updated. No changes should take place. Okay, so now let's go down to the taskbar. I'll click on the browser icon to bring up my DynamoDB dashboard. I'll click Tables in the left nav menu and click on Orders, then Items. And I have 5 items. I'm just going to expand this window a little bit, so I'll pull it to the left. And now order ID 5000 has an order total of 11,000. Well, we're going to change that to 2500. Then order ID 6000 is going to be deleted outright. Now, if I click on order ID 6000 to bring up the edit item dialog, I can see that customer ID, as I mentioned, is a string. So it should be specified as a string. So I'll cancel here. I'll uncheck order ID 6000. Now down in the taskbar, I'll click the Visual Studio icon to bring up Visual Studio Code. And now let's click the readme.txt tab. And now I'll highlight lines 1 through 4. Control C to copy. And now down in the terminal, I'll right mouse click to paste the command in and I'll press enter. Okay, and we see an error. And it's a validation error. So now let's go down to the taskbar. I'll click the browser icon to bring up my table, the orders table. And now I'll refresh. And now let's have a look. Did anything change? Well, not for order ID 5000, and we see 6000 still here. So obviously it wasn't deleted. So the entire transaction actually failed. So now let's go back to Visual Studio Code. So down in the taskbar, I'll click the Visual Studio Code icon again to bring up Visual Studio Code. Now I'll click the transact-items.json tab, and let's go to line 19 and fix customer ID. That's not a number, it's a string, so I'll specify a capital S here instead of the capital N. Control S to save, and now I'll clear. I'll right mouse click to paste the transaction command back in and press enter. Okay, and now it comes back with the information that we requested, the item collection metrics, as well as the consumed capacity. Okay, so now let's go down to the taskbar, click the browser icon to bring up the orders table again. Let's refresh, and now I can see that order 5,000 now has an order total of 2,500, and obviously order ID 6,000 is no longer in the table. So we've successfully created and used a DynamoDB transaction. In this demo, we'll explore the configuration of DynamoDB security and backup and restore. First, let's consider security. DynamoDB has VPC endpoints available for access inside our VPC. You should first confirm that the endpoint service is available in your region. So for example, I have my readme.txt file open here, and on line 2, I have an AWS EC2 command that will describe the VPC endpoint services for a specific region. So I'll highlight line 2, Control C to copy, and down in the terminal, I'll right mouse click to paste that command in and press enter. Okay, now scrolling up, I want to find service names. So I'm in service names, and I want to find DynamoDB, and there it is. So the DynamoDB VPC endpoint service is available from US-East-1 as I specified in my command. So now I'll clear. Now considering encryption in transit, DynamoDB uses SSL TLS. So for example, here from the AWS CLI, when I type AWS configure, I'm asked for an access key ID and a secret access key. And we use those to provide the SSL TLS communication from the AWS CLI over to DynamoDB. And that obviously includes any of the AWS DynamoDB commands. So again, encryption in transit uses SSL TLS. One of the things that you should understand is that because this is a fully managed service, a lot of the security is handled for us. Let's go down to the taskbar, and I'll click the browser icon to bring up my DynamoDB dashboard. In the left nav menu, I'll click Tables, and I'll click my Orders table. And I'm here because on the Overview tab, I can manage my encryption type. So here we're talking about encryption at rest. And DynamoDB uses Key Management Service, or KMS. So if I click Manage Encryption, in the Manage Encryption dialog, I can choose the default, wherein the key is owned by Amazon DynamoDB, and this is a good free option, but there's also a customer managed CMK and AWS managed CMK. Again, that's encryption at rest using KMS. All right, now access to DynamoDB is integrated with IAM. So for example, if I click More and select Access Control, here I can use Web Identity Federation and use an identity provider such as Facebook, Google, and log in with Amazon for fine-grained control of DynamoDB. Again, access is integrated with IAM. So if I click More again and click Triggers, I have a Lambda trigger function that I created. Now, I've disabled my stream, but I can still look at the function. So I'm going to click my Lambda trigger function, and that opens the Lambda trigger function up in the Lambda console. And now clicking the Permissions tab, and under Resource Summary, I have access to Amazon Cloud Watch Logs and Amazon DynamoDB. If I click on the role name, that will open up the role in the IAM roles page. And I can see, for example, that I have 2 policies associated with this role, and they allow access to, for example, DynamoDB and the Lambda basic execution role. But again, integrated with IAM. Okay, now let's close the IAM Management Console tab and the Lambda Trigger Function tab and go back to the Orders table. I'll click on the Overview tab, and now we're talking about backups. Okay, for backups, if you choose backups from the left nav menu, that allows you to do on-demand backups. But going down into the table, on the Overview tab, under Table Details, you can click to enable point-in-time recovery. You can also access the backups by clicking More and selecting Backups. From the Backups tab, you can enable point-in-time recovery and create an on-demand backup and restore. Now, to create a backup is pretty simple. Just click Create Backup. The table is Orders. The backup name, I'll just call it My Backup. Very simple. Click Create. And the backup request was successful. Now I'll close. Now my backup is available. If I want to restore it, I select it, click Restore Backup. Alternatively, I could also delete the backup. But if I click Restore Backup, then it will ask me for the new table name, and I can choose whether to restore the entire table data or restore without secondary indexes. I can choose the region, the default encryption type, and so on. All right, so scrolling down, I'll cancel out of here. Now, point-in-time recovery is where DynamoDB maintains continuous backups of our tables for the last 35 days. And to enable, you just click Enable for the table. You'll be asked to confirm. There will be additional charges. Then if you just click Enable, then it's enabled. I won't enable it right now because this does incur additional charges. So I'll just cancel. Okay, so that's a good look at DynamoDB security, backup, and restore. So in this course, we've examined how to configure and use the DynamoDB NoSQL database service offered on AWS. We did this by exploring Amazon DynamoDB and how to work with read capacity units, RCUs, write capacity units, WCUs, and the DynamoDB API. We explored global and local secondary indexes, the DynamoDB concurrency model, how to configure table properties, and how to create a DynamoDB accelerator or DAX cluster, and enable and work with DynamoDB streams. We also explored how to enable DynamoDB time to live or TTL for item expiration in a table, how to work with DynamoDB commands in the AWS CLI. We also explored how to group actions together with DynamoDB transactions, and how to configure security backup and restore services for DynamoDB. In our next course, we'll move on to explore the AWS services available for developing stateless applications, including Elasticache, Simple Storage Service S3, and Elastic File System EFS.
Stateless applications on AWS. Stateless applications are defined as those who don't require knowledge of previous individual interactions, and they don't store session information locally. I think the biggest benefit of a stateless application is that it's easier to scale. The state doesn't disappear, it just gets separated from the application, say to a database or a cache. So if the application is not strongly tied to the data, which would happen, for example, by having session state stored locally on the server, then we can spin up instances and kill instances of our application, and everything will still work fine. So it's stateless. It doesn't keep track of interactions and conversations. Stateless applications design is beneficial because it reduces the risk of a loss of session status, right? Or any of our critical data that we're using. It also improves user experience. It reduces the chances that content-specific data is lost if a specific resource that hold that data failed, right? So AWS offers some services to accomplish this stateless applications. These are Amazon S3, or Simple Storage Service, EFS, or Elastic File System, Elasticache, and DynamoDB. So over the next few slides, we'll discuss each of these options in detail, and by the end of this course, you should be ready to go and create a stateless application on AWS. Scalability. I mentioned previously, and I'll mention again because it is a major benefit to a stateless application. A stateless application can scale horizontally, so it can add new instances, for example, because requests can be serviced by any of our EC2 instances or Lambda functions. This is possible because our session data is not stored locally. So with no session data shared locally, you can add more compute resources as necessary. And when the compute capacity isn't needed anymore, you can get rid of it. Because again, we're not storing that session data locally, right? So we no longer require individual resources to stay persistent. Amazon DynamoDB. DynamoDB is a fast and flexible NoSQL database service. It's used by many applications that require consistent single-digit millisecond latency that can scale infinitely. Right? So it's beneficial to store and retrieve session information. A lot of games use it to store session information. A lot of applications as well, popular web applications will use it to store and retrieve session information. And it's really built for a stateless application design. DynamoDB supports global secondary indexes and local secondary indexes. So this is used to improve the speed of access. A global secondary index contains a subset of attributes from a table and uses an alternate key in order to perform custom queries. A local secondary index has the same partition key as the table, but uses a different sort key. But that global secondary index has a different partition and sort keys. So how do you pay for DynamoDB? DynamoDB uses read and write capacity units. So a single RCU, or read capacity unit, represents one strongly consistent read per second, or two eventually consistent reads. So if you need strong, consistent reads, right, updated completely right away, your table needs to be updated right away, then you want to go with a strongly consistent read. Now, if you have an application where you can wait a little tiny bit before that application data gets updated, then you can increase your, cost optimization by double by using eventually consistent reads, because you get one single strong consistent read per second or two eventual consistent reads per second. And this is for items up to 4 kilobytes in size. A single write capacity unit, or WCU, represents one write per second for items up to 1 kilobyte in size. This is an important topic on the developer exam. So you have to learn how to calculate your read capacity units and your write capacity unit to determine your costs to use Amazon DynamoDB. Amazon Simple Storage Service, or S3, can be used in times where we need to store state information that includes larger files, like photos, for example. So Amazon S3 can support millions of operations per second on trillions of objects. So just like DynamoDB, it can scale almost infinitely, right? So we store objects in buckets. We're giving a unique URL that's addressable, right? So where we can reach our data via an addressable unique URL. And it supports versioning and lifecycle configurations. So if someone uploads a new version of the document in S3 or a new image, say, right, we'll get versioning control. We'll also get lifecycle configurations to move some of that data out of S3 after a certain period of time where it's no longer been used. Amazon Elasticache enables you to quickly deploy, manage, and scale distributed in-memory cache environments. So we can use this to store our application state information in a, again, shared location by using an in-memory key value store. So DynamoDB, S3, Elasticache, you'll notice that it's always a shared location. It's never local. Caches can be created using Memcache or Redis caching engines and offer great performance advantage, especially when we're using heavy use applications. Elasticache offers various scalability configurations that improves access time and availability. So for example, if you've got an application that gets a lot of read requests, right? You can spin up an additional cache cluster to respond just to queries. Or should there be an increase in demand, we can spin up additional cluster nodes very quickly to scale out. Amazon Elastic File System. So think about your shared network drive on your corporate network. Well, migrate that to the cloud, and that's what you have for Elastic File System. Amazon EFS provides simple, scalable file storage for use with multiple concurrent EC2 instances or even your on-premise systems. In a stateless design, having a shared block storage system removes the risk of loss of data in situations where one or more instances becomes unavailable. EFS can store data and metadata across multiple availability zones in an AWS region, and they can grow to petabyte scale. Now let's talk a little bit about Amazon DynamoDB. DynamoDB is an incredibly fast and infinitely scalable NoSQL database service. It's used by many applications that need the consistent single-digit millisecond latency. You can use DynamoDB to store and rapidly retrieve session information. So this can be used in stateless application design, right? These can be document storage. It can be a key value storage. So this separating of session information from application resources responsible for processing user interactions makes it ideal for things like mobile or web or gaming or ad tech and many IoT applications. Right, so that's what makes it so stateless. It provides these applications a place to store their session data, thus making those applications stateless. Amazon DynamoDB throughput capacity. When you create a table or an index in DynamoDB, you have to set your capacity requirements for read and write. So these are known as read capacity units and write capacity units. That's how we measure throughput. The advantage of defining the throughput capacity in advance allows DynamoDB to reserve the necessary resources to meet our read and write activity that the application needs. So throughput capacity is specified in terms of read capacity units or write capacity units. One read capacity unit represents one strongly consistent read per second, or two eventually consistent reads per second for an item up to 4 kilobytes in size. If you need to read an item larger than 4 kilobytes, DynamoDB will consume additional read capacity units. The total number of read capacity units required depends on, well, the item size and whether you want it to be eventually consistent or strongly consistent. One write capacity unit represents one write per second for an item up to 1 kilobyte in size. So remember that. So if you need to write an item larger than 1K, DynamoDB will again consume additional resource units. So let's take a look and make an example. Let's say we create a table with 10 read capacity units and 10 write capacity units. So our application at this point could do the following. It can perform strongly consistent reads of up to 40 kilobytes per second. Right, so I calculated that by timesing my RCU, or my read capacity units of 10, by 4K. And that gives us 40 kilobytes per second. So our eventually consistent reads would be up to 80 kilobytes per second. It's twice as much read throughput. And we can write up to 10 kilobytes per second. So it's 1 kilobyte times 10 write capacity units. DynamoDB can also throttle requests when a throughput settings for a table has been exceeded. So if a request is throttled, it'll fail with an HTTP 400 code, and a provision throughput exceeded exception metric will be updated in CloudWatch. So DynamoDB provides the following mechanisms for managing throughput. DynamoDB auto-scaling. So we configure auto-scaling. We set a minimum and maximum level of read and write capacity. We also set a target utilization percentage, and DynamoDB automatically scales to try and meet that target utilization percentage. We also have provision throughput, which we talked about earlier, where we specify our throughput and AWS will provision that capacity for us. We also have reserved capacity. So much like reserved EC2 instances, reserved capacity offers significant savings over the normal price. Right, so for a 3-year term, a reserved capacity could provide a 76% discount up front. And finally, AWS Lambda triggers can be used to also trigger DynamoDB streams. Amazon DynamoDB streams. DynamoDB streams capture data changes in DynamoDB tables. So the data about these events appear in a stream in pretty much real time and in the order that they were created. So each event represents a stream record. When you enable a stream on a table, DynamoDB captures information about every modification that happens. It's an image of the entire item, including all the attributes. Stream records have a lifetime of 24 hours, after which they are deleted automatically from the streams. So DynamoDB cross-region replication. You can create a table that automatically replicates across 2 or more AWS regions, with full support for multi-master writers. Using cross-region replication, you can build fast, massively scaled applications that has a global user base. AWS uses stream endpoints for DynamoDB and DynamoDB streams. These endpoints are separate endpoints, so to work with database tables and indexes, your application must access a DynamoDB endpoint. To read and process DynamoDB stream records, your application must access a DynamoDB stream endpoint in the same AWS region. Amazon DynamoDB autoscaling. Amazon DynamoDB autoscaling actively manages throughput capacity for tables and global secondary indexes. So with automatic scaling, you define a range of upper and lower limits for read and write capacities, and then you also have to define a target utilization percentage. DynamoDB will then automatically scale to maintain that target utilization as the application workload changes. DynamoDB automatic scaling is enabled by default when you use the AWS Management Console. In this video, I'm going to demonstrate how to create a global table using Amazon DynamoDB. So we know DynamoDB is a NoSQL database, and it's used heavily for storing session data, online games, leaderboards, right? It has super fast latency and infinite scaling. So once I'm in the Amazon DB console, I click my Create Table, and I'm brought to the Create Table page. So one thing to know, we're going right into creating tables. We're not creating schemas because it's schemaless. We only need that table name and primary key. So I'm going to create a table name. I'm going to call it Music. And I'm going to give it a partition key of artist. And that's a value string. I can also add a sort key here as well. Right? So this table's primary key will be made up of 1 or 2 attributes. So in this case, it's going to be the partition key and the sort key. So for a sort key, I'm going to add album. So right now, as our primary key. So you see it says the table's primary key is made up of 1 or 2 attributes that uniquely identifies items, partitions the data, and sorts the data. So my partition key is going to be artist, and I also added a sort key, album. So if I come down to table settings, right, default settings provide the fastest way. I can use default settings, which have no secondary indexes. Provision capacity is already set for you to 5 reads and 5 writes. You get basic alarms with an 8% upper threshold for DynamoDB and encryption at rest. So I'm going to uncheck use default settings just so we can look through. So any secondary indexes that we want to create, right? We can create a secondary index here. Any read-write capacity mode. So if we do provision, it's free tier eligible. Or if we do on demand. I'm going to go with provisioned. I'm going to leave it to 5 read capacity and 5 write capacity units at an estimated cost of $2.91 a month. Auto scaling, again, is set for read and write capacity. So my target read capacity is 70%. My minimum provision capacity is 5 units, and it can scale up to 40,000 units. And the same settings apply for write capacity. I'm also authorizing DynamoDB to create a role so it can scale for me. And my encryption at rest. So I can have default. The key is owned by Amazon DynamoDB. We're not charged any fees. We can use KMS, and it's one of our own keys, so it's customer managed, and the key is stored in our account. Or we can use an AWS managed CMK via KMS. Right? So we're going to go ahead and click the default. We can add some tags here if we wanted to. Maybe I just say created by and give it a name just so we know. So I click create and you'll see it spinning around. The table's being created. Now that the table's created, you can look and see, is there a stream enabled? No, we didn't enable any DynamoDB streams, but you'll see all our details are here. The table name, partition key, primary sort key. We can enable point-in-time recovery. We can manage our encryption, right? Any cloud watch. Is the table status is active, when it was created, what our provision RCU and WCUs are, right? Any items. And we also have tabs, so I can go to items, and here's where we can, write some items in our database. I can say artist Tom Petty, album Full Moon Fever, click save, and now we've got an item in our database. From here, we can manage the time to live, manage our live count. We've got metrics. Right now we can view, these are the default metrics: read capacity, throttle read requests, throttled write requests, put latency, scan latency, read capacity. We have alarms if we want to create alarms. We can also come over to our capacity and change the capacity. We also have indexes, so these global secondary indexes, if we created one, we can query any table as a key. Right? Even attributes not presented. Our global tables tab. So to create a global table, ensure that DynamoDB streams are enabled. So we want to create a global table so we can have that multi-region, multi-master database. So in order to do that, we have to enable streams. Right? So to enable the DynamoDB streams, it's there. In our next video, we're going to create replica tables in other regions and replicate our data across regions for that high availability that we're always looking for. In this video, we're going to create a global table and replicate that across multiple regions. So once we're inside our DynamoDB console, let's click Create Table and create a new table. We'll call this table name Cars. We'll give it a partition key of Make, and we'll add a sort key of Model. We'll uncheck the default settings. We'll leave most of it the same. Read and write capacity, auto scales when they hit 70%. We'll use default encryption. And I'll go ahead and create my table. Now I want to replicate this table and make it a global table. So if I come in under cars, once the table is created, I come in under items, I'm going to create it one item. I'm going to call it a Mazda 6. Just to get a little bit of data in the table. Now, the tab that we're concerned about is global tables. We want to replicate this, right? So to create a global table, again, we have to make sure DynamoDB streams are enabled. So I click Enabled Streams, and I want new and old images. So I click Enable, and now it's available to be a global table. So we don't have a global table right now. So I'm going to click Add Region. So where do I want to replicate it? I'm in US East, North Virginia. I'll do US East, Ohio. So it tells me the region is ready. Click Replicate to proceed. So I create replica. It begins the creating process. And it comes back and says the replica in the intended region has been initiated successfully. It may take a few minutes for the replica to be created. So it gives me my table name, the new region, right? Because we're currently in North Virginia. Now it's replicated to Ohio. And now my replica is being updated. So depending on the size of your table and how many items, it could take a little longer for some rather than others. And once it's created, it starts to update the throughput capacity. Right? It's still creating. Right? So this is the original one. It gives you the endpoint. And this is your replica that we've created. It's still in creating mode. It's updating the throughput capacity. It's important to note that also you're only going to pay for the resources for these replica tables and reading from streams, the SQSQ, and the EC2 instance. Right? This all runs the cross-region application. So you're only going to pay for those resources. This cross-region replication, once finished, will build globally distributed applications, right? So we can, rather than have someone in Hong Kong hit a database in US East, we can replicate that to their region, closer to them. And it makes our application completely global. You'll see now that the original is updating and the US East, the new one, is creating. So we're updating the first one to include it as a global table, and then we replicate it to our new region. So that's why we're doing an update on the original and a create on the new. So now that it's finished, you'll see that I have two tables, one in the US East, North Virginia region, and one in US East, Ohio region. They're both active, they both have auto-scaling for read and write, and they both have separate endpoints. I could go ahead and create more. I could put one in Canada for my Canada users, South America for South America users, and again, create that real global application with low latency because you got those global tables all over the world servicing users at every end of the world. And they don't have to make long trips over the internet to communicate with the DynamoDB because they've got a replica table right next to them. And now these replica tables will stay in sync as a fully managed multi-region, multi-master database. And you can, once you're done, you can go ahead and delete a region if you want, right? Just to clean up your resources. But now you are much more apt and able to adjust to and respond to requests all over the world. Amazon Elasticache is a high-performance, scalable, and cost-effective in-memory key value store. You can use this to store application state data, right? Applications often store session state data in memory, but that doesn't scale well when you're storing session data in your local memory. So if you want to scale more and provide a shared data storage for sessions, Elasticache is the answer. By storing this frequently accessed data in memory, performance is greatly improved and the responsiveness of these read-intensive applications are much faster. So Elasticache supports the following open source in-memory caching engines. It supports Memcache, which is an open source distributed memory object caching system. It's widely adopted and protocol compliant with Elasticache. And Redis. Redis is an open source in-memory data structure store that you can use, say, as a database cache and a message broker. Elasticache supports master-slave replication and multi-AZ replication that you can use for Redis to achieve that multi-AZ redundancy. Amazon Elasticache. Let's look at some of the terminology around Elasticache and what makes up Amazon Elasticache. So first we have nodes. The node is the smallest part of the whole Elasticache deployment. It's a fixed size chunk of secure RAM, network attached RAM. Each node will run an instance of Memcache or Redis, depending on what you choose, depending on your needs. Next, we have clusters. So you guessed it, one or more nodes make up a cluster. So when we create our cluster, we choose from many different nodes based on the requirements of our application. Right? So one Memcache cluster could be as large as 20 nodes. A Redis cluster consists of a single node, but you can group multiple clusters together in what they call a replication group. So these individual node types are kind of like a subset of EC2 instance types, such as like T2, which is your general, your M2, memory optimized, and R3, right? So T2 cache node, much like T2 EC2 instance, is good for development, low volume, right? M3 and R3, right? M3 is a mix of memory and compute. R3 is for really memory intensive workloads. So you can see that these aren't like CPU type based nodes. They're more based around memory because, again, Elasticache is memory store. So depends on our requirements. We might want to have a few large nodes, or we may want to run a lot of smaller nodes, right, for redundancy purposes or for replication purposes. Even though failure doesn't exist a lot, always plan for it, right? So for a Memcache cluster, to decrease any impact of failure, use a large number of nodes with a smaller capacity instead of a few larger nodes, right? Like I previously mentioned before. Next, we have replication groups. So replication group is only for Redis. So remember that anytime you hear replication group, we're talking Redis clusters, right? So it's a collection of these Redis clusters with one primary read and write cluster, and then you have multiple, up to 5 secondary read-only clusters. These are called read replicas. So each read replica is a copy of the data from the primary cluster. It copies asynchronously to keep the read replicas synchronized with the primary cluster right away, so there's no lag and loss in data. So application endpoints can read from any cluster in the replication group. It doesn't have to be a specific one specific read node. If you've got 5, then it can read from any of those 5 read nodes. Applications, on the other hand, can only write to the primary cluster. And finally, we have endpoints. So an endpoint is our unique address the application will use to connect to an Elasticache node. Right? This is no different than all the other Amazon endpoints that we use. Right? So Memcache and Redis are a little bit different in how they treat endpoint. So a Memcache cluster has its own endpoint and an endpoint to perform your configuration. So 2 endpoints. A standalone Redis cluster has an endpoint to connect to the cluster for both reads and writes. So you got 1 endpoint. And when you're dealing with Redis replication groups, you have 2 types of endpoints. You get the primary endpoint that connects to the primary cluster in the replication group for writing, and the read endpoint for reading to a specific cluster in the replication group. Amazon Elasticache strategy. So how do we get our data into our cache? All right, how do we implement populating and maintaining our cache? So it all really depends on what we're caching and our access patterns, how our data is accessed, how often is accessed. So you've got 2 options. You've got lazy loading and write through. So with lazy loading loads data into the cache when it's required. So whenever your application requests the data. So if you make a request, you're first making that request to an Elasticache cache. If the data is there, that's great, right? Its current Elasticache to return it back to your application. If the data doesn't exist, or the data is expired, the cache is expired, your application then requests the data from the original data store. That will then return the data to your application. Your application then writes that data received from the store to the cache, so it can be retrieved more quickly for subsequent requests. Some of the advantages of this is that we're only requested data is cached, so we don't have data that is never ever being requested sitting in the cache, right? And we're avoiding filling up our cache with that data that was never being used. And when it comes to node failures, they're not fatal, because when a new empty node replaces a failed node, well, if we're using lazy loading, then that's the plan, right? It's going to be empty. So the application will continue functioning and it'll fill up the cache as requested. Some of the disadvantages of lazy loading is that we got a cache miss penalty. So each cache now results in 3 trips. Our first initial request for data from the cache. Then we got to query the original data store for the data. And then we've got to write that data to the cache. So it's a little bit more work, right? There's a lot more going on behind the scenes. You got to, get a 3-way trip in order to populate that cache. So it all depends, again, on your data, how it's retrieved, how often it's retrieved. Next, we have write-through. So write-through strategy adds or updates data in the cache when it's written to the database originally. So if you put data in the database, unlike lazy loading, which waits for it to be requested before it loads it in the cache, write-through will automatically write it through the cache. So it's good because our data is never stale, right? Because it's automatically being written to the cache. But some disadvantages is if you get a write penalty. So every write involves 2 trips, a write to the cache and a write to the database. You'll have missing data if a node goes down. You'll have unused data. You got a bunch of data that's never requested just sitting in the cache, right? Causing you money. So kind of avoid that. And you get cache churn. So the cache may be updated often if certain records are updated repeatedly. And so you're constantly writing to the cache, which also gets expensive. So it all comes down to how your data is retrieved. If you've got a lot of data and a lot of it is stale, then lazy loading might be your best option. If you need constant, fast, up-to-date information and you don't care about cost, then write-through may be your choice. Amazon Elasticache scaling. So as our workloads get bigger, our Elasticache is going to have to change, right? It's going to have to meet the size of our new environment and our new workloads. So you can expand your cluster by scaling. You can scale horizontally or you can scale vertically. By scaling horizontally, we know that we're adding more, right? So the functionality differs depending on the cache engine. With Memcache, we can partition our data and scale up to 20 nodes or more. Whereas a Redis cluster consists of, remember, a single cache node that handles read and write transactions, and you can create additional clusters to include a Redis replication group. So although you only have one node handle that writes commands, you can have up to 5 read replicas. And a lot of the times it's the reads, right? You have so many reads going on that's what's chewing up performance. So that may be why you need to scale out horizontally. Scaling vertically is not supported in Elasticache, right? You can create a new cluster with a desired cache node and begin redirecting. So if you've got a class T2 node, and you don't want to scale horizontally, well then you can create maybe an M class node and point your traffic towards that and then start migrating your traffic over. So vertically is not a great option. Plan ahead so that you can scale horizontally. Amazon Elasticache replication. Replication is an effective method for providing a speedy recovery if a node fails or if we have a big traffic increase in read queries. Elasticache clusters running Redis support both, but cache clusters running Memcache are standalone in memory service and they don't provide any data redundancy. So it's important to remember. Cache clusters running Redis support replication groups. A replication group, again, can consist of up to 6 clusters. 5 of them are read replicas. 1 is your master that you read and write to. You can also provision multi-AZ replication groups. So our application then, we're increasing our availability because we're spreading it out over multiple availability zones. If a primary node goes down, multi-AZ will select a replica and then promote it to the new primary. So again, it's all in the name of disaster recovery, high availability. Amazon Elasticache snapshots, or backup and recovery. Elasticache clusters that run Redis support snapshots. Use these snapshots to persist your data. Each snapshot is a clone of the data that you can use to recover to a specific point in time. Snapshots are not available to clusters that use memcache. It's because memcache, again, is purely in-memory key value store and it always starts empty. Elasticache attempts different backup techniques depending on the amount of memory available, right? Your node size. So, as a best practice, set up a replication group, perform the snapshot against one of the read replicas instead of creating a snapshot against that primary node. You can automate snapshot creations or you can create them manually, right? Manual snapshots, remember, are stored forever until you delete them. Amazon Elasticache access. We want to restrict connectivity. We don't want it to be open to the world. So primary way to do that, to restrict this connectivity, is through a security group, much like your EC2, right? You'd have a security group. You define inbound rules and you restrict the source. When you deploy a cache cluster in a VPC, every node has a private IP address based on the subnets that you chose. So you can't access individual nodes from the internet or from an Amazon EC2 instance, right? So if you want to use your memcache internally and not for a web application, deploy it in a VPC. And you can also use access control lists, right, to constrain network inbound traffic, right? So if you use a proper ACL with a proper security group, then you're really controlling your Elasticache access. The access to manage the configuration and infrastructure of the cluster is controlled separately. So you use the IAM service and you define policies that control Elasticache infrastructure that your AWS users can manage. In this video, I'm going to demonstrate how to create an Amazon AWS Elasticache cluster. So first we need to get into the Elasticache dashboard. And once we're in the Elasticache dashboard, we can choose from the left-hand side. So we have memcached, which is just your basic key value cache. We have Redis, which also could include a global data store. Any reserved nodes, any of our backups, parameter groups, subnet groups, and some more of the advanced features. So let's create a Redis cluster. So we click Redis and we click Create. So it asks you, what engine do you want? Do you want a Redis engine that you can use as a database, a cache, and a message broker, right? It got more advanced features like multi-AZ and auto failover, or do you want the memcache, the high performance distributed memory object caching? We're going to go with Redis. We're going to give it a name. We're going to call it Tech Redis, and we'll give it a description. Redis cluster for tech. Engine version compatibility, we'll go with 5.06. Port will be 6379. We're going to leave that as the default. The parameter group will also be on the default. And here's the node type. So here's where we can check our node. So cache.r5.large gives you 13.07 gigabytes. If you want to come back down to more general purpose T2s, say T2 medium or T2 small, you're in the 0.5 to 1.5 gigs. So I'm going to go with a T2 small. Just for time purposes, it'll obviously provision a lot faster. Number of replicas, I want 2, and I want it spread out over multi-AZs. So now I have to come down and select the subnet group. So I can create a new one, or I can use one that's already created. If I click Create New, we'll call it Tech Redis Subnet. And we'll give it a description of my subnet for Redis cluster. We'll choose a VPC, and then we'll choose 2 subnets for that VPC. We can check preference for availability zones, or we can select their zones. So I'm going to say no preference. I'll let it just put them there in 1A and 1B. We need to create a security group, so we can use one of the ones we already created. I'm going to go with the default security group that I've already created. We click encryption at rest. We can use a default or customer manage customer master key, or we can use encryption in transit. We can also choose Redis authentication if we wish, and then we'd have to specify our authentication token. If we need to import any data to the cluster, right? So if there's any data in a relational database, we need to put that in S3 and then seed it to our cluster from S3. I want to enable automatic backups every day. I can specify a backup window at 00 UTC for 1 hour. And I can also specify a maintenance window if I wish. And I can specify a topic for SNS notification. So if I specify a maintenance window, I can send out an email telling everyone that, it's maintenance time. So I'll click create. And now you'll see that the cluster is creating. And it takes a little bit of time to create the multiple nodes, again, because we're replicating 2 ways. So once it gets finished, we can go in and take a look around. You can see that when you click, you can see kind of what's happening. We've got no nodes available right now. Auto failover is currently enabling, so it's in process. While that's processing, I want to talk to you about how to load this cache. So we talked about 2 ways of loading the cache, right? Write through and lazy loading. So lazy loading is we only write to the cache once it's requested. That's great because we don't have stale data sitting in the cache anymore, right? Never being used. But there's a cache miss penalty. We also have write through, which writes everything to the database and the cache, right? Which is fine as well. But a lot of times you'll have data that's never being used just sat there. So it depends on what your trying to purpose is. If you want to add a time to live, then you can take advantage of lazy loading, right? Load it in once it's requested and assign a time to live so it doesn't get stale. So let's look at 2 ways of actually loading. So in this way, if we have a function called getUser, right? The user record looks to the cache. If the user record is null in the cache, it'll go to the database and get it. And then it will set it in the cache, right? So this is lazy loading, right? We're checking the cache. It's not there. Select it from the database and load it in the cache. Here we have write through, where a user record is going to be saved, right? So it queries the data, update where the ID is what we pass in. For the user ID, set the cache, right? And then return it. So anytime it goes to update the database, it cache sets at the same time and then returns it. So that's write through loading. So how you integrate your application with your cache will depend on your strategies, right? So depending on how you want it, if you've got all your data and it's going to be accessed frequently and there's no stale data, then write through, right? It's all going to be there and it's all going to be there right away. If you've got data that, it gets picked through bits and pieces, lazy loading may be your answer. As you can see, now the cluster is available. It's up to date. It has 3 nodes, right? So it shows you your primary endpoint, your master.techredis, which is our name, right? And always has the port 6379. Shows your engines, your availability zones, the number of nodes, right? Your failovers. So if we click the name, we'll see the nodes, right? This is our primary, this is our replica, this is our replica. They're all in sync. And it shows you any endpoint. So your primary endpoint, your reader endpoint, and a lot of the other information that you set up. So I hope this video showed you how to create that Redis cluster and kind of give you some tips on how to load that cache, whether it's lazy loading or right through loading or some form using time to live, right? But get your application writing to the cache and reading from the cache and really see the performance difference when using an in-memory store, when using an in-memory key value store. In this video, I'm going to demonstrate how to use Amazon Simple Storage Service, or S3, to provide you with some object level storage for your application. So any persistent files, maybe our profile pictures, right? So in our case, we're allowing our users to upload a profile picture for their web app, right? It's not like a Facebook profile picture where it's just a running list of all your previous ones. You get one profile picture. So we want to store that in S3 and then use lifecycle management to move that out as newer versions come in. So first we need to click Create Bucket, and we're going to give it a name, and we're going to call it Tech Profile Pics. We're going to put it in US East 1. We don't want to block all access because that would defeat the purpose of making it a public bucket. And we have to click that you acknowledge that this is a public bucket. We also need versioning. In order to do any lifecycle management, we need versioning, so we'll click Enable Versioning. We won't bother with any tags. It is a best practice, so when you're really doing this, bring in tags. I'm going to turn off default encryption, and I'm going to create my bucket. The bucket creates. We come down and we find it, Tech Profile Pics, and click the name. Now we can see the overview. So we can go into Properties. We know versioning is enabled. We can make sure that, if you want to enable server access logging, you have to just make sure there's another bucket that you can put those logs in. There's object level logging, so you can set up CloudTrail, right, to make sure you know who's accessing what, right, on each object. We come to permissions, right? We make sure that block all public access is off. We can go to our ACL, and this is important for public access. Click Everyone and Write. So we want to be able to write. We want to upload our profile pictures. So it's going to scream at you, this is public access. You shouldn't do that, but, again, it's just to let you know if this is for internal use and this is a bad idea, but it's not. We want public access. Under management, right, we can start creating life cycles. So we're going to say archive old pics as a rule name. Apply it to all objects in the bucket. Click Next. And we only want to transition previous version. So we click Add Transition. And we'll say transition it to one zone infrequent access after 30 days of it not being the current version. Clean up old delete markers and clean up incomplete multi-part uploads after 7 days. So it gives you another acknowledgement. I guess S3 doesn't leave any surprises. It lets you know everything that you're doing. So you click to acknowledge the lifecycle rule will apply to all objects, and we save. And we also have access points. So access points are used to create distinguishable host names, right? So you can create different host names for your S3 bucket, and by giving different host names to different users, then you can easier control what happens, and you get more fine-tuned control over your S3 buckets. So I can create an access point and call it dev users, right? It's an internet, and I create the access point. I can create another access point and call it privilege users. So now that I've got multiple access points, I've got multiple URLs that I can give to users, and I can secure these in different ways. So I hope this video showed you how to utilize S3 to really use it for that object storage that it is, and it can really benefit your web application by not only storing your persistent objects, but transitioning them down the life cycle when they are no longer used. Amazon Elastic File System. Amazon EFS is a Unix-based file system that you can use to store shared session data. So it's another option to keep your application stateless. It uses file system access semantics and supports two forms of encryption files. Encryption in transit, so while encryption is in place while the files are being moved around, and encryption at rest. We also deal with throughput and input-output per second for EFS, right? So we can choose our instance performance mode based on higher input-outputs per second, or more of a throughput-based. Amazon EFS with AWS Direct Connect. So there'll be times when you want to integrate your on-premise servers with Amazon EFS using your Direct Connect connection. So a few things to take note: it must be a Linux-based operating system. AWS recommends a Linux kernel of 4.0 or greater. You should also mount the target IP address instead of DNS. So we know how finicky DNS can be, so we want to mount our target using IP addresses. And it's important to note that AWS VPN cannot be used to access EFS from your on-premise servers. So if you have on-premise servers, you want to take advantage of bursting and integrate them with EFS. Make sure it's a Unix-based operating system with a mounted target IP address over a direct connect connection. Amazon EFS access control. So we have to make sure that the people who are making these API calls to EFS have the actual valid credentials. So we can use the root account, but that's not best practice. So when you create your users and your policies and roles, then make sure that you set up EFS appropriately, right? Set up users who can manage EFS. Set up users who can view the file system or can create objects in the file system. So it's all done via your IAM. And data consistency. So Amazon EFS uses an open after close consistency semantics to make sure that the data is consistent across the full file system. So when you store this for your web servers, or you can use this for an internal file system to store session data, you've got the option of access control, and you've got the added benefit of data consistency. So to create our Amazon EFS resources, we have to create an Amazon EFS file system. We can do this in the console. We can do this via the command line. We can even do this via AWS SDK. So we create our EFS file system. Then we create our mount targets. Right, so our mount targets are exactly that. It's the targets that we mount to. Right? Do we want to mount this file system to an EC2? Right? Or do we want to be an on-premise Unix? Right, so we have to create our mount targets, and we have to create our security groups. So we can create security groups for the mount targets to only accept traffic from specific EC2 instances. So then they can only be mounted to specific EC2 instances, for example. We also have to open up ports for NFS traffic, and we can also create the security groups additionally on our EC2 instances as well for that dual layer protection. Amazon EFS file systems themselves and some of the attributes around creating a file system is that once we create that file system, we have to choose our mode. Do we want the general performance, high performance? And we can't change it. Once we create that file system, we have to use the file system. We have to mount it to a target. We have to set up our permissions. Who can access? Who can manage? Who can create resources? We have to users, groups, and permissions set up. Right? So much like a Unix operating system, it uses that read, write, execute. Right? Users and groups can be assigned permissions for specific folders and specific files. Deleting a file system. So once we're done with a file system, we should delete that file system when it's not in use as good practice. And we have to manage access to the file system. So again, who can create resources? Who can view? Right? Who can read, write, and execute is what it really comes down to. Amazon EFS performance modes. You have a general purpose performance mode. This should be good for most of your web applications or corporate file sharing, or storing session data, right? Just like your general purpose modes for EC2, and max IO. So if you really need that maximum input output and that throughput, then this is the option for you. It will cost you a bit in terms of latency, but that throughput has been increased. So depending on what you need, general purpose should do the trick, but if you really need that increased throughput, use the max IO performance mode. And the charges are the same for both. So Amazon EFS throughput. EFS scales as the file system grows. So you don't have to worry about it. You don't have to partition a new volume, create a new volume. It scales automatically as it grows and is designed to burst to high throughput level, which is determined by size. It also uses a credit system to determine burstage, right? So when can the file system burst? It's all based on your credit system. The baseline rate is 50 megabytes per second per terabyte of. In this video, I'm going to show you how to create and mount an EFS file system. So once you're in the Elastic File System console, we click Create File System. You're given an option to put in a name. It's a good idea to put in a name, so we'll call it TechFS, and then you have to choose your VPC. So I'm going to choose this VPC with the 10.0.0.0/16 CIDR block. So I can click Create or Customize. So if I click Customize, we're given a little bit more settings right off the bat. So automatic backups are here. So I want automatic backups enabled. I want lifecycle management. So anything that's been 30 days since it's been last accessed, it's going to get put into the infrequent access storage class. My performance modes are here. So general purpose or max IO. And my throughput mode. Do I want bursting or do I want provision? So I'm going to leave it on general purpose. I'm going to leave the throughput mode on bursting, and I'm going to enable encryption of data at rest. I'm going to create a tag called created by and put my name, and I click next. So here's where we have our VPC. Any mount targets, should we choose to mount these targets using the console, I'm going to mount it using the EC2 Linux interface. So I click next. We have a policy editor, right? So do we want to prevent root access, enforce read-only access? So once you click them, these policies come in. So I'm going to clear those and leave them. Click next. We have a file system policy. I'm going to go ahead and leave that as and click create. So you'll see now that our TechFS file system is created and has a file system ID. Right? It starts off 6 kilobytes in size, but again, it grows as you add to it. So if we can click the file system, you'll see all the options that we selected. Plus, you'll see like the metered size. You can monitor it with CloudWatch metrics, just the basic metrics that comes with it. So it'll show you any like writes and reads and give you some idea on throughput utilization. It creates a utilization warning at 75% by default, which is great. Right, you got client connections, and these are still updating. So our tags are still here. Our file system policy, if we put one in. If we want to create an access point is just a special endpoint for your applications to be able to reach this data. Right, so you can create an access point with a path. You can control the users who access it and what they can do with it. So it's mainly for application access to these EFS data. And it shows you your network if you want to create any mount targets. So I'm going to go back and I'm going to go into my EC2 and I'm going to make a directory and I'm going to call it mount point. So now at this point, I need to come back and I need to click attach. So I've created that mount point on my EC2 instance. Well, how do I go about mounting? So if we click attach, you'll see mount via DNS and mount via IP, and it gives you the commands below. But we want to mount via IP, right? So it automatically finds the instance that I have in that availability zone, and using the NFS client, right, which you need to install on your AWS console, and using the NFS client, which you need to install with your AWS command line, we just copy this command, come back to our EC2, paste it in, but change this EFS to whatever you called your mount point, which I called mine subsequently mount point. We hit enter and we wait. So once it mounts, we can do df-h and we can look and see that we've got our EFS mounted. So you can see the size, right? I've got 172.31.42.211, 0% use, and it's mounted on mount point. I also have another EFS volume, 172.31.46.239, that's also mounted to this EC2 instance using the /apps mount point. So now I can go and add this EFS drive to any EC2 instance, right? So if I replicated this on another EC2 instance, then we've got a shared network drive, right? So that's what we're trying to do here. So if you want to use it for persistent large data, or if you want to somehow store some session data on it, that's fine. But you got to create your EFS volume, then mount it to your EC2 instance. So I hope this video showed you how to create an EFS file system, create a mount point on your EC2 instance, and then actually go about mounting your instance. Once your image is mounted, you can go in and start creating files and sharing files with other users or applications or web services, whatever the case may be. But this EFS really gives you a file system that's shareable. So go in, create some EFS, and mount them to your EC2 instances and really dive into all the powerful features that EFS offers. So in this course, we've examined AWS services for building stateless applications, including how to install and configure these services. We did this by exploring how stateless applications are developed on the AWS cloud, how application state can be stored using DynamoDB, how to create a DynamoDB global table and create tables that automatically replicate across multiple AWS regions, and the use of the AWS ElastiCache service to provide caching. We also learned how to create an ElastiCache cluster on AWS, how to configure simple storage service S3 to persist data, the use of Elastic File System EFS for scalable storage, and how to create and mount an EFS volume. In our next course, we'll move on to explore the AWS tools and services for protecting and securing data and applications on the AWS cloud, including the Key Management Service, KMS, Systems Manager, and the Security Token Service, STA.
In this video, we'll explore encryption. Encryption provides an additional layer of security for storing data in AWS Cloud. Options for encrypting data at rest include automated AWS encryption solutions and manual client-side encryption. AWS also provides key management infrastructure for storing and managing encryption keys, including AWS Key Management Service, or KMS, and the AWS Cloud HSM, which is a hardware security module. Server-side encryption means that the application or service receiving data encrypts it at its destination. Amazon S3 performs encryption at the object level as it is written to disk and decrypts it for us when we want to access it. 3 options exist for S3 server-side encryption, and these are mutually exclusive options, so we can use one of these approaches. The first option is server-side encryption with Amazon S3 Managed Keys, or SSES3. This involves each object being encrypted with a unique key. Amazon S3 also encrypts the key itself with a master key, which is rotated on a regular basis. Amazon S3 server-side encryption uses 256-bit Advanced Encryption Standard, or AES 256, to encrypt our data. Another option is server-side encryption with customer master keys, or CMKs, stored in AWS Key Management Service, or SSE KMS. With this approach, there are separate permissions controlling the use of a CMK, providing additional protection against unauthorized access to objects in S3. Additional benefits include the fact that with SSE-KMS, we get an audit trail so we can track who used our CMKs and when. We can create and manage customer managed keys, or CMKs, or we can use the AWS managed CMKs. And finally, with server-side encryption with customer provided keys, or SSE-C, we manage our encryption keys, and Amazon S3 manages the encryption and decryption. Now, client-side encryption involves encrypting data before sending it to AWS Cloud. There are two options for client-side encryption. First, use a customer master key, or CMK, stored in AWS Key Management Service. With this approach, when we upload an object, we first send a request to AWS KMS for a CMK that's available for encrypting our data. If we're successful, KMS returns two versions of a randomly generated data key, including a plain text version of the data key that the client uses to encrypt the object data, and a cipher blob of that same data key that the client uploads to Amazon S3 as object metadata. When we're downloading an object, the client downloads the encrypted object from Amazon S3 as well as the cipher blob version of the data key, which is then sent to KMS to obtain the plain text version of the data key, which it can use to decrypt the object data. Now, option 2 involves using a master key that we store within our application. With this approach, when uploading an object, we provide a client-side master key to the Amazon S3 encryption client. The client uses the master key that we provide only to encrypt the data encryption key, or data key, that it generates randomly. It uses the data key to encrypt the data of a single Amazon S3 object, generating a separate data key for each object as required. With this approach, when downloading an object, the client downloads the encrypted object from Amazon S3 and uses the object's metadata to determine which master key to use for decrypting the data key. The client uses that master key to decrypt the data key and then uses the data key to decrypt the object. Only a subset of AWS SDKs support client-side encryption, like the SDKs for .NET, Golang, Java, PHP, Ruby, and C++. It's also important to note that the client-side master keys and our unencrypted data are never sent to AWS. And so it's up to us to manage and secure our encryption keys appropriately. The AWS Encryption SDK, not the AWS SDK, but the Encryption SDK, is a special purpose client-side encryption library for encrypting and decrypting data while adhering to industry standards and best practices. The AWS Encryption SDK is provided by Amazon free of charge under the Apache 2.0 license. The AWS Encryption SDK generates a unique data key for each data object encrypted, which aligns with cryptography best practice involving the use of a unique data key for each encryption operation. The Encryption SDK encrypts data using a secure, authenticated, symmetric algorithm. The Encryption SDK protects the data keys used to encrypt data by encrypting them using at least one master key. Encrypting data keys with more than one master key helps ensure the portability of our encrypted data. For example, we could encrypt data under multiple KMS customer master keys from different AWS regions. Then we just copy the encrypted data to any of the regions and use the CMK in that region to decrypt it. The Encryption SDK stores the encrypted data along with the encrypted data key in an encrypted message with a specific defined data format. Therefore, we don't have to worry about protecting the data keys that encrypt our data. Some language variations of the AWS Encryption SDK do require an AWS SDK, but the Encryption SDK doesn't require an AWS account, and it is not dependent on any AWS services. To use the Encryption SDK, we only need an AWS account only if we're going to use KMS CMKs to protect our data. The AWS Encryption SDK is available for Python, C, Java, and JavaScript programming languages, and it is supported by the AWS CLI as well. However, the AWS Encryption SDK is not compatible with other libraries since each library returns encrypted data in a different specific format. So we can't encrypt data using one library and then decrypt that data using another library. In this video, we'll explore AWS Key Management Service. AWS Key Management Service is a managed service for creating and managing encryption keys that can be used to encrypt our data. It is a secure, resilient service that uses the Federal Information Processing Standards FIPS validated cryptographic modules to protect our master keys. AWS KMS has a number of features and benefits that we can leverage. For example, we have centralized key management. AWS KMS is also compatible with other AWS services, so it integrates well with these other services. It offers auditing capabilities and high availability, a custom key store, and it also aligns with industry-specific compliance and regulatory standards. Okay, first let's consider the AWS KMS centralized key management. What this means is that we have a centralized view of all our encryption keys. We can create a customer master key or CMK to control access to our data encryption keys, also known as data keys, and to encrypt and decrypt our data. It uses 256-bit AES encryption. We can use Key Management Service to create keys either by using the Key Management Service, Cloud HSM, or by importing our own key material. We can then manage them with KMS, either using the Management Console, by using the AWS SDK, or by using the AWS CLI. In addition, KMS also automatically rotates our keys annually without having to re-encrypt previously encrypted data. Now, with respect to integration, KMS seamlessly integrates with several other AWS services. As a developer, we can quickly and conveniently create keys that we can use to encrypt data stored in other AWS services like Amazon S3, for example. KMS includes an AWS managed master key for use with various other AWS services that integrate with AWS KMS. It provides the ability to track the AWS managed CMKs in our account, but the service itself takes care of the management of the keys. If we require more control over the encryption process, we can also generate our own CMK. Currently, KMS supports over 50 AWS services. Now, auditing capabilities. API requests and other activity in our AWS account are written to log files if AWS CloudTrail is enabled for our AWS account and region. CloudTrail logs provide us with information like who has used a particular AWS KMS CMK, the API request that was made, and when the request was made with a particular key. AWS KMS is a fully managed service, so that means it can scale automatically to meet growing demand, and KMS stores encrypted copies or versions of our keys using systems designed for 11 nines of durability. AWS CMKs do not leave the Cloud HSM instances, so our keys are stored securely in an AWS region so that no one, not even AWS employees, can retrieve our plaintext keys from KMS. And KMS uses the Federal Information Processing Standards FIPS validated hardware security modules to protect our keys, ensuring confidentiality and integrity of our data. Now, we can also create our own custom key stores in a Cloud HSM cluster under our control. This provides us with the ability to store our AWS KMS keys in a single tenant environment rather than the default multi-tenant environment under KMS. However, note that using a custom key store incurs additional costs for the Cloud HSM cluster. And compliance. KMS simplifies compliance by using security and quality controls that are validated and certified by industry-specific compliance and regulatory standards. In this video, we'll explore access key management. Encryption requires three primary components. First, there's the data to encrypt. Then there's a method used to encrypt the data using a cryptographic algorithm. And then there are encryption keys used with the data and the encryption algorithm. Common programming languages typically provide libraries with a variety of available cryptographic algorithms, like Advanced Encryption Standard or AES. It's vitally important to protect the keys from unauthorized access. To manage the security of encryption keys, we typically use a key management infrastructure, or KMI, which is comprised of a storage layer that protects the plaintext keys and a management layer authorizing the use of the keys. A common method for protecting keys is by using a hardware security module, which is simply a dedicated storage and data processing device that performs cryptographic operations using keys on the device. We have three options while using AWS to provide the encryption method and the KMI. First option, we control the encryption method and the entire KMI. The second option is we control the encryption method and the management layer of the KMI, and AWS provides the storage component. And the third option, AWS controls the encryption method and the entire key management infrastructure. With the first option, we control the encryption method and the entire KMI. We use our own KMI to generate, store, and manage access keys, and we control all the encryption methods used in our applications. The physical location of the KMI and the encryption method can reside outside of AWS or in an Amazon EC2 instance. We can encrypt data in various AWS services like Amazon S3, in Elastic Block Store, the AWS Storage Gateway, the Amazon Relational Database Service, or RDS, and Amazon EMR, which helps run and scale big data frameworks like Apache Spark and Hive. A second option sees us control the encryption method and provide the KMI management layer, and AWS provides the KMI storage component. This option is different than option 1 because the keys are stored in an AWS Cloud HSM appliance rather than in a key storage system that we manage on-prem. Also under this option, applications need to be able to access our Cloud HSM appliances in an Amazon Virtual Private Cloud, or VPC. In this way, the Cloud HSM client interacts with the Cloud HSM appliance to encrypt data with our application. We may then send encrypted data to any AWS service for storage. And this brings us to the third option. AWS controls the encryption method and the entire KMI. So in essence, AWS provides server-side encryption of our data and transparently manages the encryption method and keys. AWS Key Management Service is a managed encryption service that allows us to provision and use keys for encrypting data in AWS services and our applications. Master keys in AWS KMS are used in a similar fashion to how master keys in a hardware security module are used. Master keys are designed such that they are never exported from the service. We can send data to the service requesting that it be encrypted or decrypted while using a specific master key in our account. This provides us with centralized control over who can access our master keys, and it also provides us with audit capabilities over the use of the keys. AWS KMS natively integrates with other AWS services like Amazon S3 and Amazon Elastic Block Store. We can also request that Amazon S3 use server-side encryption when writing Amazon EMR data to Amazon S3 buckets. And Amazon Redshift clusters also support server-side encryption through AWS KMS. In this demo, we'll create and delete a customer-managed key. Okay, I've signed into AWS Management Console. Now to go to the KMS console in Find Services, I'll just start typing KMS. And when Key Management Service appears, I'll click on the link. And that brings me to my KMS console. Now I've got customer managed keys open here, and I have a key already. We'll schedule that key for deletion. But before we do that, let's go and create another key. Now to do that, click Create Key. And now we first have to choose in step 1 the type of key that we're going to use, whether it's going to be symmetric or asymmetric. Now, symmetric uses a single encryption key for both encryption and decryption operations, while an asymmetric key uses a public and private key pair. It can be used for encryption, decryption, or for sign and verify operations as well. Our key is going to be a symmetric key, and I'll leave symmetric selected. Now, if I expand advanced options, here I can choose the material origin of my key. By default, it's KMS, but if I chose external, I can import a symmetric 256-bit key of my own. I can also choose the custom key store and use Cloud HSM as my key's origin. We'll leave KMS selected. Okay, and we'll click Next. Now in step 2, we add labels. First, an alias. Now this is a display name for the key, and it makes it very convenient to work with. For my key's alias, I'll call mine dev-key. I have a test-key, so I'll now use dev-key for this alias. Note that the alias name cannot begin with AWS // The AWS / prefix is reserved by Amazon Web Services, and it represents AWS managed keys in our account. Okay, so I'll leave the description blank. For tags, we can specify different tag keys. We're not going to do that in this demo. Instead, we'll just click Next. Now in step 3, define key administrative permissions. We can choose IAM roles and users who can administer this key. We may be required to add more permissions or additional permissions for the users or roles in order to administer this key. Now, if we don't set administrative permissions, we're going to end up with the default key policy, and we're going to do that anyway. So scrolling down, under key deletion, the allow key administrators to delete this key checkbox is checked. We'll leave that and click Next. Okay, now we define key usage permissions, and this is similar to selecting our administrative permissions. We're not going to choose one, and because of that, we're going to end up with a default policy. And the default policy is an all-encompassing policy, and we'll see that shortly. We could also choose at the bottom of the page other AWS accounts if we want to go cross-account here. We won't change anything here. We'll just click Next. And now we review and edit our key policy. Now this is the default key policy. The one statement on line 9 guarantees that everybody in the account will be able to access this key for encryption and decryption operations. So we'll leave that as is. That's our default key policy. Okay, so now let's click Finish. And now we have our dev key. Now, let's drill down into the test key. On this keys page, under General Configuration, the alias is test-key. I gave it a description. Its status is enabled. It was created a few days ago. I have the ARN here. If I click to expand cryptographic configuration, I'll see that it's a symmetric key type. Its origin is KMS. The key spec is symmetric default, and the key usage is encrypt and decrypt. And again, we have the default key policy. Clicking the Tags tab shows me if there are any tags, and there aren't any. And if I click Key Rotation, I can put in motion a rotation policy that would see this customer managed key rotated automatically every year. Okay, so I'm just going to go back to the customer managed keys page. I'm going to select the test key, and beside key actions, I'll click the down arrow, and here I can enable, disable, schedule the key for deletion, and I can also add or edit tags. So I'll click Schedule Key Deletion, and a notification appears in the Schedule Key Deletion dialog that indicates that deleting a key makes all the data encrypted under that key unrecoverable. It gives us a waiting period. So the default waiting period in days is 30. We can reduce that down to 7 if we like. If we try to go below 7, then we're warned and we have to enter a period between 7 and 30 days. So I'll specify 7 days. Okay, now scrolling down, I can also select the confirm that you want to delete this key in 7 days checkbox, and I'll do that. I would like confirmation. And I'll click schedule deletion. And now the status shows pending deletion. All right, and with that, we've successfully created a customer managed key, and we've also scheduled another customer managed key for deletion. In this demo, we'll work with key policies and IAM policies. The primary way that we manage access to AWS KMS customer managed keys, or CMKs, is through policies. Policies are simply documents describing who can access what. There are identity-based policies, which are attached to an IAM identity, and resource-based policies. And with KMS, we attach resource-based policies to our CMKs. These are called key policies, and all KMS CMKs have a key policy. To get started, I've opened my browser and I've navigated to the KMS console in the AWS Management Console. I'm on the Customer Managed Keys page, and I'm going to be working with my dev key. I also have a second tab open to the IAM Management Console because we're going to explore a couple of policies here. All right, so let's go back to the KMS console. I'll click dev key to bring up the key, and scrolling down, right now my key policy is very simple. I'll click to switch to policy view, and this policy has a single statement. Just recall that when we create a CMK, we can optionally provide the key policy, and if we don't, then the CMK will use the default key policy. And that's what this is. This default key policy has a single statement that provides the AWS account, that is the root user, with full access to the CMK, and this enables IAM policies in the account to control access to the CMK. Another benefit of this statement is that it results in us mitigating the risk of the CMK becoming unmanageable, since the root user account can't be deleted. But, for example, if we gave access to an IAM user and that user subsequently got deleted, and they were the only ones that had access to it, then it would render the CMK unmanageable, and we'd have to call support to regain access. Okay, I'll click switch to default view one more time. I'm going to add a key administrator now. So I'll click add under key administrators. I'll select my administrator user. I'll click add in the add key administrators dialog. And now scrolling down, I'll click the allow key administrators to delete this key checkbox. And under key users, I'll click add. And in the add key users dialog, I'll select my dev user and I'll click add. All right, so now scrolling back up, let's quick switch to policy view again, and now we have a totally different policy. So we've got another statement starting on line 15 that allows access for key administrators, and all the actions that are available to administrators are listed from lines 21 down through line 34. Then starting on line 39, we have a second statement that allows the use of the key, and I've got the dev user as the principal here, and they're allowed to encrypt, decrypt, re-encrypt, generate data key for envelope encryption, and describe key. And then one additional statement that was added in order to allow the create grant, list grants, and revoke grant actions to the user. Okay, so now let's go down to the taskbar. I'll click on the Visual Studio Code icon to bring up Visual Studio Code. And now let's do a couple of administrative operations. First, I'll highlight lines 2 through 7. And this is going to basically output my key policy that we just saw. So I'll right-click, select copy after highlighting lines 2 through 7. Down in the terminal, I'll right mouse click to paste that command in and press enter. And now we've got a key_policy.json file. I'll double click to bring that up. And there is our key policy. All right, back over to the README. Another administrative function is disable key. Now, I'm doing this, but I'm specifying the profile dev user, because what's going to happen here is that we're going to see an access exception. So let's right-click, select copy. Now down in the terminal, first I'll clear, then I'll right mouse click to paste the command in and press enter. And lo and behold, we get an access denied exception, as we should, because the dev user is a regular user and does not have access to the disable key action. So I'll clear. Now, however, the dev user does have access to the encrypt operation. So let's highlight lines 15 through 20. Right-click, select copy. Now I'll paste that down in the terminal below and press enter. And we've successfully encrypted a file named sample.txt. The result is in a file named encrypted.base64. If I double-click to open it, there it is. Okay, so I'll close it. Now we see that the dev user has access to user operations and the administrative user has access to admin operations in KMS. Now let's go back down to the taskbar. I'm going to click to bring up the browser, and now I'm going to go to my second tab. That's the IAM Management Console tab. So a couple of things to look at here. So first, administrator access. If I click to bring this up, I have access to virtually all resources. And if I look at the policy usage, I'll see that this policy is attached to the admins group. Now going back to permissions, if I click policy summary and in the filter I type KMS, I'll see that anybody who is a member of the admins group has full access to KMS. Now let's click on policies to bring up all of our policies again. And now I'll just search for KMS. And this is a policy that I created. So let's click to open this policy. I'll click JSON to open it, and I'll click Edit Policy. Now I'll click JSON so that we can edit this policy. And I'm doing this basically so that we can see the policy. So here is the policy. So KMS admin allows the same actions as we saw when I added the key administrator to the key earlier. And then I've got a statement on line 26 that denies access to encrypt, decrypt, and re-encrypt. So what that means is that my admin user will not be able to encrypt or decrypt or re-encrypt. So it's a combination of the IAM policies with the key policy. So let's verify this. Click on the Visual Studio Code icon on the taskbar to bring up Visual Studio Code. Now I'll clear, and I'll up arrow a couple of times to bring that command back. And now for my profile, instead of dev user, I'll use my default profile. Now this is my jQuery admin user, and according to the IAM policy that we just looked at, this should bring up an access denied exception as well. So I'll press enter, and there we see the access denied exception. So a couple of things to take away from this demo. The default key policy provides that single statement that provides the AWS account, that's the root user, with full access, and this enables, in turn, IAM policies in the account to be able to be used to control access to the CMK. In this demo, we'll encrypt and decrypt data using a CMK and the AWS CLI. To get started, I've opened my browser and I've signed into AWS Management Console. I've navigated to the KMS console, and on a second tab, I've navigated to the IAM Management Console. So I'll click the IAM Management Console tab. Here, I'm going to detach a restrictive policy from my administrative user that is preventing me from being able to encrypt and decrypt data. In the search field, beside filter policies, I'll type KMS, and there's the policy that I want to detach from my administrative user. So I'll click to select it, then I'll click Policy Actions, I'll select Detach. Now in the Detach Policy page, I'll select my user and click Detach Policy. Okay, done. So now I should be able to encrypt and decrypt data. Down on the taskbar, I'll click the Visual Studio Code icon to bring up Visual Studio Code. First, we're going to encrypt sample text. And sample text is a file that just contains some text. It just says just some plain text to be encrypted. And the readme.txt file contains the commands that we'll use. So let's start with lines 2 through 6. So I'll highlight lines 2 through 6. And let's go over these. Line 2 is a simple AWS KMS encrypt command. On line 3, I have the key ID parameter, and here I specify the CMK's either key ID, I could specify its Amazon resource name or ARN, I could use its alias name, which is what I'm doing here, or its alias ARN. Now, when we use an alias name, we need to prefix it with alias / like I've done on line 3. And also, if you want to specify CMK in a different AWS account, then we have to use the key ARN or the alias ARN. Okay, next, line 4. The file B prefix just instructs the CLI to read the data to encrypt. This is called the plain text from a file and pass the file's contents to the command's plain text parameter. Then the output and query parameters extract the encrypted data called the ciphertext from the command's output. And the final part of the command on line 6 with the right angle brace and encrypted.base64, this just saves the base64 encoded ciphertext to a file, which makes things easier because we'll need to go and decode after we do this. So in the second step of this encryption operation, I'll use the certutil utility on Windows 10 to decode my base64 encoded ciphertext to binary ciphertext. And it outputs it to a file named encrypted. Okay, so I'm going to press Control-C to copy lines 2 through 6. And down in the terminal session, I'll right-click to paste that command in, and I'll press Enter. Okay, and now we have an encrypted.base64 file in our projects directory. If I click to open this file, I'll see that it's just a long sequence of letters and numbers and symbols. It's base64 encoded. Okay, so I'll close it. And now we need to decode this file. And we do that with the command on line 9. And again, this uses the certutil utility to decode base64 to binary. So I'll highlight line 9, Control-C, down in the terminal session. First I'll clear, and now I'll right mouse click to paste the certutil command in, and I'll press Enter. Okay, and certutil reports that the decode command completed successfully. Now if I try to open this one, Visual Studio Code might complain. Right, so it says that the file is not displayed in the editor because it's either binary or uses an unsupported text encoding, and it is binary, so I'll click Do you want to open it anyway? And there is our encrypted data. All right, so now let's go back the other way. So down in the terminal session, I'll type clear. I'll close encrypted. Now let's go back to the README. Okay, so now to decrypt, basically we're going back the other way. So in this case, we use the decrypt command. That's on line 12. Then line 13, I use the file B prefix again to specify the ciphertext-blob parameter. The file that we refer to is the ciphertext that we want to decrypt. Now, similar to the encrypt operation, the file B prefix tells the CLI to read the encrypted data from a file and pass the file's contents to the command's ciphertext-blob parameter. We also use the output and query parameters to control the command's output, and these parameters extract the decrypted data called the plain text from the command's output. At the end of this operation, then we'll have decrypted ciphertext that is base64 encoded, and we'll need to decode it. Okay, so pressing Control-C, now down in the terminal session, right mouse click to paste it in and press Enter. Okay, so now we have our decrypted.base64 file. I'll clear, and now for the final part, we'll decode decrypted.base64. So I'll highlight line 18, Control-C to copy, down in the terminal session, right mouse click to paste it in, and press Enter. Okay, and the certutil reports that the decode command completed successfully. So now we should be able to open decrypted.txt and see the original same text that was in sample.txt. So I'll click to open decrypted.txt, and there we see just some plain text to be encrypted. All right, so we've successfully encrypted and decrypted data using the AWS CLI. In this demo, we'll encrypt secret data for Lambda functions. One way to safeguard sensitive data passed to Lambda functions is to encrypt them as environment variables, and these can safely be passed to our Lambda functions and then decrypted at runtime. Essentially, we create environment variables when configuring the Lambda function, ensure that they are encrypted both at rest and in transit, then allow our function to decrypt and use the secret data at runtime. Okay, to get started, I've signed into AWS Management Console. I'm on my KMS console. I'm looking at my customer managed keys. I'm going to need the ARN later on for the CMK that I'm going to use for the encryption. So I'll click to drill down into dev key, and then later on I'll grab this ARN. On a second tab, I've got my Lambda dashboard open. I'm going to create a new function, so I'll click Create Function. I'll leave Author from Scratch selected. Now for basic information, for a function name, I'll specify secure vars function. And for runtime, I'm going to click the down arrow and I'll select Python 3.8. And now I'll click Create Function. Okay, so we have a notification indicating that we successfully created the function. So I'll close the notification. And now scrolling down, under environment variables, this is where I will add my environment variables, but scrolling down further, I want to change some of my basic settings. So I'll click Edit. And for my description, first I'll specify Lambda function that can use encrypted environment variables. Scrolling down further, for timeout, I'm going to increase that to 15 seconds. And for execution role, I'm going to use an existing role, and that existing role is created for us when we create the Lambda function. Now, I'm going to change that role right now so that it has access to the KMS decrypt API. So I'll click View the secure vars function role, and that opens the role in a new tab in the IAM Management Console. Now here I'm going to add an inline policy, so I'll click Add Inline Policy. Now in the visual editor, I'll click Choose Service. I'll type KMS and select KMS. We'll specify the decrypt operation. And for resources, make sure that specific is selected and click Add ARN. And now in the Add ARNs dialog, I'm going to add the ARN. So I'll go back to the KMS console tab. I'll highlight the ARN, right click, select copy, now over to IAM Management Console again, and let's paste that ARN into the specify ARN for key field. And click Add. Okay, scrolling down, it's all good. Let's click Review Policy. Now I'm going to give this policy a name. I'll just call this policy Secure Lambda Vars. And scrolling down, I'll click Create Policy. Okay, so now our policy has been created. I've got the inline policy as well as the managed policy for Lambda basic execution. Okay, so now let's go back to the Lambda tab. And now I'll save my changes. And now scrolling down one more time, I'll click Manage Environment Variables. I'll add environment variable, so I'll click Add Environment Variable. My key will be called secret_variable. And for a value, I'll just specify 1Q2W3E for R. Now this could be a password, for example, a database password. It could be some other variable. It's sensitive data, so we want to encrypt it. So underneath, let's expand encryption configuration. And we want to click Enable Helpers for encryption in transit. And we also want to use AWS KMS keys to encrypt at rest. So I'll click Use a Customer Master Key. I'll select dev key, and now I'll click encrypt. I'll select the same key. Now I'll expand decrypt secret snippets. And let's just grab all of this code. So I'll highlight it and press Control C. And then scrolling down, I'll click encrypt. So now that variable has been encrypted. Okay, so let's click save. Okay, and now in the editor, let's just replace everything here. So we'll highlight everything, press Control V to paste it all in. So what are we doing here? Well, we're importing Boto3, that's the Python SDK. We're importing OS and base64 from B64 decode so that we can decode the encrypted variable. So in line 6, we grab the encrypted variable. In line 9, we decrypt it. And now on lines 15 to 16, I'm just going to add a couple of quick commands so that we can verify that the secret variable was indeed decrypted. So I'll type print secret underscore variable is, and I'll concatenate that with the decrypted string. Now on the next line, I'll just return decrypted. Okay, and now I'll click save. And my function is now saved. So let's test this. I'll click test. We're going to create a new test event. I'll call this test event secure virus test. And I'll click create. And now I'll click test. And let's scroll up. Okay, and execution result succeeded. So let's click to expand details. And under details, I can see the value returned by the function execution, which is exactly what I expected. So we've successfully used encryption on our Lambda function's environment variables and configured the Lambda function to decrypt it for use at runtime. In this demo, we'll create secure string parameters with AWS Systems Manager Parameter Store. Okay, I've signed into AWS Management Console. Now to navigate to Systems Manager Parameter Store, under Find Services in the search field, I'll start typing Systems, and when Systems Manager appears, I'll click to navigate to Systems Manager. Now in the left nav menu, under Application Management, I'll click Parameter Store to bring me to the Parameter Store. Now I have no parameters, so I'll click Create Parameter. Now one thing about Systems Manager is that it was formerly known as Amazon Simple Systems Manager, so that's where the SSM acronym came from. Systems Manager itself is a suite of capabilities that we can use to help us manage our applications running in AWS. And the Parameter Store provides secure, hierarchical storage for configuration data and secrets management. We can use it to store data such as passwords, database strings, license codes, and so on. And you can store values as plain text or encrypted. You can then reference values by using the unique name that you specified when you created the parameter. It's serverless, scalable, and durable, performs version tracking of configurations and secrets, and we can use it to perform configuration management using paths. So let's create the first parameter. We're going to create this parameter under My App. So it's under My App, it's going to be under Test, and it's going to be Password. Now, these names are case sensitive, so just be aware. So the first one's Password. I'll leave the description blank. For tier, I'm going to choose Standard tier for up to 10,000 parameters, and the size limit of a parameter is 4 kilobytes. Advanced, you can create more than 10,000 parameters with a parameter value size up to 8 kilobytes, although charges do apply. Okay, so this first parameter is going to be a secure string. So I can choose string, string list, and secure string. And when I choose secure string, it opens up the field below so I can choose my KMS key source. Now, if I don't specify a key ID here, the system uses the default key associated with the AWS account. You can also specify a key from another account. So I'll click in the KMS key ID field, and I'll choose my own CMK that I created earlier, and the value for this parameter is just simply going to be password. Scrolling down, I'll click Create Parameter, and that's the first parameter. Okay, let's click Create Parameter and create another one. This one will be under My App Test again. And when I click in the field, I can see the hierarchy. Now for this one, I'll call it user. So this parameter is called user. Again, I'll leave the standard tier, but this one will be a string. And the value is just going to be test-user. And I'll click create parameter. Okay, so there are our parameters. Now we'll create a couple of other parameters in the CLI under prod, not under test, right? So let's go down to the taskbar. I'll click the Visual Studio Code icon to bring up Visual Studio Code. And let's highlight the first command. So this is AWS SSM put parameter. And this creates parameters for us. I specify the name, which is my app prod user, a value, which is prod-user, and again, the type is just string. So Control-C to copy. Down in the terminal session, I'll right mouse click to paste it in and press enter. And the output returns the version and the tier. So we're at version 1. So we just created this, so we should be at version 1, of course. So now I'll type clear and press enter. And for the second command, lines 6 through 10, I'm using put parameter again, and I specify my name. The name is password. But this time I'm specifying a little bit more secure value, and I'm using a secure string type. So that's why on line 9, the type flag uses secure string, and I reference the key ID using my key ID's alias. Now I could also specify the ARN here if I needed to, but I'll use the alias here instead. So Control-C to copy. Down in the terminal session, right mouse click to paste it in and press enter. And again, we get the output with the version and the tier. So I'll clear, and now let's go down to the taskbar. I'll click on the browser icon to bring up parameter store. Now I'll refresh to see my two new parameters, prod password and prod user. So you can start to see the hierarchy here. All four come under my app, but I have 2 under prod and 2 under test. So you can imagine in production and test, I have different parameters. Okay, so now back down to the taskbar, I'll click on the Visual Studio Code icon one more time to bring up Visual Studio Code. Now, lines 12 and 13. Here, I'm using get parameters. And for the name, I just specify the name of my parameters. And note that I have to specify the fully qualified name, right? So the /myapp/test/password and /myapp/test/user. So let's press Control-C, and now down in the terminal session, I'll right mouse click and let's press enter. And when it returns now, it returns the information for both parameters, but the value for my password is encrypted, so it returned the encrypted value. Okay, so I'll type clear and press enter. And now on line 15, I'm again issuing the get parameters command, but this time when I get password, I'm using the with decryption flag, and this will decrypt it on the fly for us. So let's highlight, press Control-C, down in the terminal, right click to paste in the command, and now when it returns the information for the parameter, it decrypted the value for us on the fly. Okay, so now let's clear. Okay, so now on line 19, here I'm issuing put parameter, and this time I'm creating a new parameter called max connect. And on line 21, I'm specifying a value of 100. And then on line 22, I specify an allowed pattern. And this allowed pattern is just a regular expression. So here I'm saying it's got a length of 1 to 3 characters. And the type is just a string. So let's go ahead and let's create that parameter. So I'll highlight lines 19 through 23, Control-C to copy. Down in the terminal session, I'll right mouse click to paste it in and press enter. And it returns the familiar version and tier. So I'll clear. And now from lines 25 through 30, here I'm using put parameter again, but because I'm using the overwrite flag, it's like editing. So it replaces the value. And the value here I've specified on line 27 is 1000. Now this violates my allowed pattern, so this should fail. Okay, so Control-C, down in the terminal, I'll right mouse click and press enter. And yes, we get the error. So parameter value cannot be validated against the allowed pattern. All right, so first we'll clear. And now I'll up arrow to bring back the original put parameter command. And now for the value, I'll overwrite the value of 1000 with a valid value according to my allowed pattern of 999. So that is 1 to 3 characters in length. Now I'll press enter and we see the version and the tier returned. So parameter store, again, performs version tracking of configurations and secrets for us. So we're at version 2 for Max Connect. Okay, so now down in the terminal session, I'll clear. And now on lines 32 through 34, I'm using the get parameter history command. So I'm going to get the parameter history for Max Connect, and I'm going to decrypt it on the fly with decryption. So I'll press Control-C. Down in the terminal, I will right mouse click and press enter. Okay, so now we see the parameters history. So version 1 had a value of 100. Version 2 had a value of 999. Okay, excellent. So now it's clear. And now for the final command, we're going to get parameters by path. So for example, say we wanted to get everything under my app test. So I specify get parameters by path, and the path flag specifies the path that I want to return, and I'm using with decryption to decrypt on the fly. So I'll highlight lines 36 through 38, Control-C, and down in the terminal, I'll right mouse click to paste that command in and press enter. And now I can get to see the parameters within my test path. So if I scroll up, I should see 3. So here's Max Connect. Its value is 999, and I'm on version 2. Then we have password, again under test, version 1, and user, again under test, and it's also version 1. All right, and with that, we've successfully created secure string parameters with Systems Manager Parameter Store. In this demo, we'll manage secrets with AWS Secrets Manager. With Secrets Manager, we can replace hard-coded credentials and secrets in our code, including passwords, with an API call to Secrets Manager. That way, we can safely retrieve our secrets programmatically, ensuring that the secret won't be revealed by someone looking at our code because it's just not there anymore. Secrets Manager can also automatically rotate the secret for us, and in this way, since we're replacing long-term secrets with short-term secrets, we have considerably reduced the risk of compromise. Secrets Manager also encrypts secrets through KMS, and you'll see it commonly integrated with databases like Amazon RDS. Okay, so I've signed into AWS Management Console. In the Find Services field, I'll start typing secrets, and when Secrets Manager appears, I'll click Secrets Manager, and this brings me to Secrets Manager. Now I already have a secret defined, but I'm going to go and create a new secret. So I'll click Store a New Secret, and we can choose the secret type, credentials for RDS database, credentials for document DB, Redshift cluster, other database types, as well as any other type of secret that we want to store here. Okay, so now let's specify the username and password to be stored in this secret. So I'll type admin, and the password is going to be capital PASSWORD 1 exclamation. So I can click Show Password to show password. Scrolling down, now I select the encryption key. I can use the default encryption key, or if I click the down arrow in the encryption key field, I can choose my KMS key. So I'll choose my KMS key. Now, scrolling down, AWS polls my account to look for RDS databases, and I have a database already, so I'll choose that database, and then I'll click Next. Now in step 2, we provide a name and description for our new secret, and for this secret, I'm just going to call it prod/db credentials. Okay, and for a description, I'll just type access to MySQL production DB. Scrolling down, I can also specify some optional tags, and I can set up a resource policy. This is also optional. I won't do that now, so I'll just click Next. And in this step, we configure the rotation. By default, automatic rotation is disabled. If I enable automatic rotation, then I can select a rotation interval from 1 to 365 days. Then I specify a Lambda function, either one that's already been created, or we'll create a new Lambda function to perform the rotation for us. Okay, I will disable automatic rotation because I'm not going to write a function to enable rotation at this time. And scrolling down, I'll click Next. Okay, and on the review, everything looks good. And under the review, we have some sample code that we can use in Java, JavaScript, C#, Python 3, Ruby, and Golang. So we can choose this code to get started that shows us how to retrieve the secrets with our application. Okay, so scrolling down, I'll click Store. And now we have my prod DB credentials. Okay, now let's go down to the taskbar. I'll click on the Visual Studio Code icon to bring up Visual Studio Code. And we're going to use the CLI to retrieve our secrets. So first, lines 1 and 2, I use AWS Secrets Manager. So this will get our secret value for us with the get-secret-value subcommand. I just specify the secret ID, which is prod DB credentials, and it will retrieve it for us. So let's highlight lines 1 and 2, Control-C to copy. Now down in the terminal session, I'll right mouse click to paste the command in and press enter. And it retrieves our information. So the secret string has the username, password, the engine, which is MySQL, the host, the port, and the DB instance identifier. Excellent. Okay, so now let's clear. Now I can also retrieve the value using Systems Manager and the get-parameter command. So lines 4 through 6, I'm using AWS SSM get-parameter. I specify the name, and note that the name has to include the /AWS reference secrets manager prefix, and then the name of my secret, which is prod/DB credentials. And I specify the with decryption flag to decrypt on the fly. Okay, so we'll highlight lines 4 through 6, Control-C to copy. Down in the terminal session, I'll right mouse click to paste that command in and press enter. And this retrieves our secret again. Okay, so we've successfully created secrets with AWS Secrets Manager. In this demo, we'll encrypt CloudWatch logs. CloudWatch logs are so important to our service and to our application. It provides us with information for ongoing maintenance, troubleshooting, security issues, and logs contain sensitive information. So it would be great to be able to encrypt them. Well, we can. To get started, I've signed into AWS Management Console, and in Find Services, I'll start typing CloudWatch. And when CloudWatch appears, I'll click it to navigate to my CloudWatch console. Now in the left nav menu, I'll click Log Groups, and I've got some log groups already. For example, AWS Lambda Secure Virus function. When this log group was created, I did not associate a KMS key with it. So I'll click to open it, and under Log Group Details, under KMS Key ID, there is no key associated with this log group. So can I do that here? Well, no. If I click Actions, I can edit retention settings, I can perform other operations, but nowhere can I associate a KMS key with this log group. For that, we have to use the CloudWatch Logs API. Okay, so we'll just leave this open. I'll go down to the taskbar and I'll click on the Visual Studio Code icon to bring up Visual Studio Code. I've got a couple of files open. I've got a readme.txt file open with some commands in it, and I've got a keypolicy.json file. The readme.txt has some commands. First, I'm going to use associate KMS key to associate a key with a log group. So with this command, I specify the log group name, and it has to be the full log group name. That's on line 2. Then I associate a KMS key ID. So it has to be the ARN for the KMS key that I want to associate with this particular log group. And I specify the region, US-East-1. Okay, so let's highlight this command. So from lines 1 through 4, Control-C, and down in the terminal session, I'll right mouse click to paste it in and press enter. And we get an error. And the error basically says that the key either doesn't exist or it's not allowed to be used with the log group. So we need to enable the CloudWatch service to be able to use KMS to encrypt, decrypt, and so on. And that's what the key policy is for. So I'll click the key policy tab, and this is the key policy that I created when I created the KMS key, except for the last statement. And in the last statement, I am specifically referencing a service principal, and I'm specifying logs.us-east-1, that's the region, .amazonaws.com. I'm allowing these actions: KMS encrypt, decrypt, re-encrypt, generate data key, and describe. Okay, so we're going to copy this whole thing and associate this key policy with my dev key. Okay, so I'm going to press Control A to highlight everything and Control C to copy it. Now let's go back to the browser. So I'll click the browser icon on the taskbar, and I'll right-click the AWS logo and select Open Link in New Tab. From here, I need to go to KMS. So I'll just start typing KMS in Find Services, and when Key Management Service appears, I'll click it. Okay, and I'll click Customer Managed Keys, and here's my dev key. So I'll click to open my dev key. And now under Key Policy, I'll switch to Policy View. So I'll click Switch to Policy View, and here's my policy. So right now, this policy is very similar to the one that I have in Visual Studio Code, except for the fact that I don't have a service principal associated with this key policy in here. So what I'm going to do is click Edit. I'll click inside the editor, Control A to highlight everything, and Control V to replace it with my new key policy. So my new key policy, again, is going to allow me to encrypt, decrypt, re-encrypt, generate data key, and describe. Okay, so I'll click Save Changes. And now let's go back to Visual Studio Code. So down on the taskbar, I'll click on the Visual Studio Code icon. And now we'll go back to the readme.txt file. Now this is the command from lines 1 through 4 that we're going to run. So Control C. Now down in the terminal session, first I'll clear. And now I'll right mouse click to paste that command in, and I'll press Enter. And no error this time. So let's go back to the browser. So I'll click the browser icon on the taskbar. Let's go to the CloudWatch Management Console. So I'll click the CloudWatch Management Console tab. And now if I refresh here, so I'll right click and click the refresh icon, I'll see now that this log group does have my KMS key associated with it. Okay, so let's click Log Groups in the left nav menu. And now we can also do the same thing when we create a log group. So down on the taskbar, I'll click the Visual Studio Code icon again. And in the terminal session, I'll clear. And now I'll go grab the command from lines 6 through 9. So what are we doing here? Well, we're using the create log group command. And basically, I specify the log group name. Again, it has to be the full log group name. I'm just calling this test encrypted. And I'm associating the KMS key ID, the same key that I used previously. And I specify the region. So let's highlight lines 6 through 9. Control C to copy. Down in the terminal session, I'll right mouse click to paste it in. Press Enter. And done. Okay, so now I'll clear again. Now, before we go back to the browser, I'm going to highlight lines 11 and 12. So basically, I'm just going to disassociate the KMS key that I associated with the AWS Lambda service virus function log group. So I'll press Control C, right mouse click, down in the terminal session, press Enter, and done. Okay, so now when we go back to the browser, so let's click the browser icon on the taskbar, and I drill down into my secure virus function. If I refresh, I will now see that the key has been disassociated. Okay, so now if I go back to log groups, I'll also see a new log group, test encrypted. That's the one that I just created. And if I drill down into this log group, so I'll click on it, and I see the KMS key that is associated with this particular log group. All right, so we've successfully encrypted CloudWatch logs. In this video, we'll explore AWS Security Token Service. AWS Security Token Service, or STS, is concerned with the provision of temporary security credentials. It's a web service allowing us to request temporary limited privilege credentials for AWS IAM users or federated users. AWS Security Token Service is available by default as a global service with all STS requests sent to a single endpoint. Note that global requests map to the US East North Virginia region. It is recommended, though, that we use regional STS endpoints rather than the global endpoint, as this reduces latency, it provides redundancy, and it increases session token validity. STS supports AWS CloudTrail. CloudTrail records AWS calls on our AWS account and delivers log files to an Amazon S3 bucket, allowing us to understand what requests were successfully made to STS, the party that made the request, when it was made, and other information. An audit trail on our STS operations, if you will. If we activate STS regional endpoints instead of the default global endpoint, then we need to ensure that CloudTrail logging is enabled in those regions, as this is required in order to record any STS API calls made in those regions. We use AWS Security Token Service to create temporary security credentials and provide trusted users with temporary access to our AWS resources. Temporary security credentials work similar to long-term access key credentials used by our IAM users, but there are some differences. First, temporary security credentials are short-term and can be configured to last from a few minutes to several hours. Once they've expired, AWS no longer recognizes them. In addition, temporary security credentials are not stored with the user. Rather, they are generated dynamically and provided when requested. When, or even before, the temporary security credentials expire, the user can request new credentials. These differences result in some advantages. First, we don't have to distribute or embed long-term AWS security credentials for an application. We can provide user access to our AWS resources without having to define an AWS identity for them. And the temporary security credentials also have a limited lifetime. One of the benefits of a limited lifetime is that we do not have to rotate the security credentials or explicitly revoke them once they've served their purpose and are no longer required. Typical scenarios for using temporary credentials include identity federation, where we can manage our user identities in a system external to AWS and grant users signing in from those external systems with access to AWS services and our AWS resources. Another scenario is when using roles for cross-account access. In this scenario, we can define user identities in one account and use those identities to access AWS resources in other AWS accounts belonging to the organization. This is known as the delegation approach to temporary access. Consider another scenario that involves running applications on Amazon EC2 instances where the applications require access to AWS resources. We can provide temporary security credentials to our instances when we launch them, and these temporary security credentials will be available to all applications running on the instance. This means no long-term credentials are stored on the instance. Lastly, we can use temporary security credentials to access most AWS services, including compute, storage, database, and other AWS service types. So in this course, we've examined AWS security and encryption, including the AWS tools and services available to protect and secure data and applications in the AWS cloud. We did this by exploring the use of encryption for protecting data. We looked at how the key management service is used for managing keys on AWS. We looked at how to control access keys on AWS and how to create customer master keys, or CMKs, in the KMS console and using the AWS CLI. We explored how to create secure string parameters using the AWS Systems Manager Parameter Store, protect secrets with Secrets Manager and use a CMK to encrypt and decrypt secret data for Lambda functions. We explored how to work with key policies and IAM policies and how to encrypt CloudWatch logs. And we explored the Security Token Service, STS, and how to obtain temporary restricted privilege credentials for AWS IAM users. In our next course, we'll move on to explore how to work with troubleshooting and monitoring resources available for developers on AWS Cloud, including AWS CloudWatch, X-Ray, and CloudTrail.
Monitoring and troubleshooting on the AWS cloud. AWS offers fully managed services to help you monitor, log, and analyze your application, performance, and system traffic. So basically, it makes everything easier to identify patterns and discover any potential, say, security risks or bottlenecks, right? And it'll help you devise some solutions that are reliable and scalable and secure. AWS offers services such as Amazon CloudWatch, AWS CloudTrail, and AWS X-Ray to assist you in all your monitoring and troubleshooting needs. So what areas are we going to touch on when it comes to AWS cloud monitoring? First, the performance and costs, right? These are your biggest questions. Is the performance for the end users good? And, is it costing me an exorbitant amount of money? So you kind of need to get the happy medium. If you had unlimited funds, you could make the highest, best performing application in history, but you don't, right? So you need to make that happy medium between performance and cost, and this monitoring allows you to really drill down and dig into that. We also have trends, so we can see what our customers are doing or what parts of the application are receiving more traffic. So maybe we want to see what APIs are being utilized the most, right? So just default CloudWatch metrics can help us with that. It's also good for learning, so learning what our customers are doing with the application, right? So X-Ray, even CloudWatch, and even CloudTrail can help us see the inner workings of our application and learn how our users are actually using it. And finally, troubleshooting. So if you've got stuff like failed Lambda invocations or low memory usage, degraded performance, right? These are your troubleshooting tools. So it really comes down to, are your customers having a good experience with your application, right? So the first thing we need to look at is performance and costs. We can easily break this down into measurable metrics. All right, CloudWatch comes with default metrics such as CPU utilization, network bytes in and out, right? We can also install a CloudWatch agent on our EC2 instances and send more custom metrics like memory utilization. So by looking at these metrics, we can see the performance, and if there's any performance issues, we can also see what it's costing us. And again, we got to hit that happy medium between performance and cost. We also have trends. So what is happening with our application? How is it being used? What are the traffic trends? Right? If we can see a spike in traffic every time one of our ads go on TV, and we know we push our ads out at, say, 11 p.m. at night, and we always see a massive spike in traffic, maybe we want to jump on that trend and call Amazon to pre-warm our load balancer, before the commercial airs. Right? And this insight is really efficient for us in predicting changes in our traffic and being able to react to them. So AWS Cloud Monitoring, its real main focus is really troubleshooting and remediation. So where do our problems occur? If we can find out where our problems occur ahead of time, or look at previous troubleshooting or logs or anything that we've used to kind of predict changes, right? We can bring that all together and use it for troubleshooting and make a much better mean time between failures and a much quicker mean time to resolution, right? So that's used. We want a long time between failures. And if we do have a failure, We want to get that up as quick as possible, so we want a low mean time to resolution. And by previous troubleshooting or having the appropriate logs in place, this can be achieved very well with the AWS Cloud Monitoring tools. We can also use it for learning and improvement, right? So we have operational metrics. We evaluate these operational metrics over time. They'll reveal some patterns and some common issues. Say, for example, we have an application that got a memory leak and customers are complaining about degraded performance. So we go ahead, we're not using any monitoring or any custom monitoring, right? So we can't detect any memory leak patterns. So we just go ahead and add more CPU. That's not going to take care of the problem. But if we were monitoring this memory on the application, we can detect how much memory is being used over time, and we would have found that issue quicker, and we would have remediated it without having to add more CPU and costing more money. In this video, I'm going to demonstrate how to create a CloudWatch dashboard using the metrics for your AWS resources. So once we're in our CloudWatch console, you'll see any recent alarms, right? So we create an alarm for the dev machine CPU. We can still see that in our overview area. So let's go ahead and create dashboards. So we'll click dashboards and we'll click create dashboard. We're going to call it dev machine metrics and we'll click create dashboard. And you're brought to a kind of a dashboard wizard. So what widget type? Do you want a line? Do you want a stacked area? Do you want a number? Right, we're going to go with a line. We can also have logs table and alarm statuses to this dashboard. We just want to look at the metrics. So I'm going to say line and click configure. Now we're brought back to our metrics and the namespaces. So we want to look at EC2 per instance metrics. Now we want to use our dev machine. So which metrics do we want to use for the dev machine? Well, we're going to use network packets out, network packets in, CPU utilization, and disk write-ups. We can also put in status check failed, CPU surplus credits. These are all the default metrics, so we'll add them all in. And we'll click create widget. So it creates our widget, and you can see right now, just by one glance, all your default metrics. So everything is pretty low. The only one that's surging was our network out, right, over the last hour. We had some CPU utilization changes. See how you can click on each one of the metrics, right, to get a better look at it. Network outs, and you can separate them, right? Or we can view them all as a whole. So when we're ready, we can save our dashboard. So we can change it to 3 hours. We can change it to 12 hours, right? But it's just a visual representation, right? We can come up, we can add to it. So if we wanted to add more, maybe we want to add a number, right? So we click configure, we come down to EC2 per instance, and maybe we'd rather see our CPU utilization as a number, right? So we click create widget, and now it's added over here, right? So multiple widgets will make up a dashboard. You can combine all of your metrics into one, or you can create multiple widgets to make up the full dashboard. Let's add one more widget. Maybe this widget is going to be based on my EBS volume. So I click EBS volume, I say per volume metrics. I come down and look at volume read ops, and I click create widget. Now this widget shows up in my dashboard. So I've got 3 widgets. I've got all my default metrics for my EC2 instance for my dev machine. I also created a visual CPU utilization widget for my dashboard and a volume read ops for EBS. right? Maybe I want to add another widget that's based somewhere around my elastic load balancing, right? Or Elasticache or my logs, right? So I can choose application load balancer, maybe per app ELB, per availability zone. I can find my load balancer. Maybe I want to have an idea of how many 500 counts I've got. I can click it on, click create widget, and now I've added that to my dashboard, right? So I save my dashboard. Now it's saved, and I've got it all here, right? And I can change the times, right? So it's a good way to take your most important metrics from all your services and combine them together into one dashboard where you can get all that information at the same time. Now let's take a look at AWS X-Ray. AWS X-Ray is a service that collects data about requests that your application serves and provides tools that you can use to view, filter, and gain insight into the data to identify issues and opportunities in your application. So why would you want to use AWS X-Ray? X-Ray helps you as a developer monitor, improve, and even helps in the initial building of your application. You can use it to identify performance bottlenecks. So you'll see visually all the workings of your application, and we can decide, hey, where's the bottleneck? Right? We can even visualize it and look at it and see where bottlenecks are occurring. We can pinpoint specific service issues. Right? If we've got certain issues that are occurring, maybe notifications aren't being sent as part of our application. Right? So we can use X-Ray to maybe look into SNS and view our workings with SNS to see where the service issues lie. We can use it to identify errors and then identify the impact of these errors to users. Right? So where is the error occurring in the application and what else does it affect and how does it impact the user? So what makes up AWS X-Ray? First, we have a trace. So a trace is a path of a request through your full application and all the services that it entails, right? It's end-to-end, so it may go through EC2, VPC, S3, Lambda, API gateway, right? So this trace is from end to end, and a trace ID is passed through the AWS services with the request, so X-Ray can then put all those related segments together. A segment is data from the particular service. So it could be S3, it could be Lambda, whatever you're using. And when a segment is reported to X-Ray, a trace ID is reported. And then X-Ray can put all those trace IDs together, right, and complete that chain. A subsegment identifies the underlying API calls from each particular service. So if you have API calls for S3, like a get item or a put item, then subsegment will identify these API calls as well. So just to conclude on AWS X-Ray, we know it's great for viewing system performances. It'll give you a visual graphic of what your application is doing and how it performs. It'll help you identify problems. But what it doesn't do is provide auditing capabilities, right, or track your number of requests. It does, however, trace your requests from end to end through all your AWS services. Its main idea is to focus on troubleshooting. Right? It's not used for HIPAA compliance, right? It's used for identifying bottlenecks, figuring out what sections of your application are not working, and taking a literal X-ray of your application to give you a lot more insight into what is actually happening. In this video, I'm going to demonstrate how to create an Elastic Beanstalk application that utilizes AWS X-Ray through a CloudFormation script. So first we have to come into AWS CloudFormation and click Create Stack. I'm going to use a template that I already have. It's an AWS sample application. So I'll choose my file. I'll find my file. You'll notice that it's a YAML file. And I'm going to click View in Designer so we can take a look at and see what it actually does here. So once it finally loads up, we can take a look at our template itself. So we've got a few parameters, and once we need to specify a VPC and a subnet, then we create some instance profile roles. So we create an IAM role that'll allow us to have our EC2 instances to assume other roles. And we also have an X-ray write-only policy. So it's an IAM policy that'll allow you to publish to SNS, put telemetry records to X-ray, put trace segments to X-ray, and put items to DynamoDB on all resources. When we get down into the actual application itself, you'll see that it's an application, right? We need an application version. And we specify a source bundle. So since this is an AWS public sample application, it's already instrumented for X-ray, right? So what we're doing here for our source bundle is just to say our actual source files are in an S3 bucket. It's called AWS X-ray assets. And here's the key. So we go up and we get that source bundle. Then we create an environment, right, that has auto scaling. And we just have our namespaces here, right? So if we're in the AWS EC2 VPC, then associate a public IP address, give us some subnets, right? And then we have some outputs. So our Elastic Beanstalk environment URL, sample instance profile role, so everything, it creates some outputs as well. So if we take a look into our diagram itself, right, you'll see we have an Elastic Beanstalk application. We have the application version. We have the environment. It is assigned these roles we created, and it can write to X-ray. So we validate our script. The template is valid, and let's go ahead and create the stack. So again, we have two parameters. So we click Next. We give it a stack name. So we'll give it X-ray stack. We specify a VPC and a subnet. So I'm going to put it in my default VPC, and I'll just put it in this subnet. Click Next. We can specify any tags, permissions, rollback policies. We're going to leave it all default. Click Next. We get our overview. We acknowledge that there's going to be some IAM resources created. Then we click Create Stack. At this point, our stack will begin to create. It's a bit of a process because you're creating resources like IAM profiles, Elastic Beanstalk environments, applications. So it takes a little bit of time. So as you can see, our Elastic Beanstalk application version has been created. Some more of our roles have been created. And now we're starting to create the X-ray write-only policy. And if we come up and look at resources, we can see what has been created. So our application's been created in Elastic Beanstalk. And some of our roles have been created in policies. So if we come back to events, our X-ray write-only policy has now been created. Now we can see our Elastic Beanstalk environment is being created. This is usually the last step and one of the more lengthier steps. So you'll see that another stack gets spun up here. And this is the Elastic Beanstalk environment. So if you click it, you'll see the environment and all its settings are set here in a separate stack, which are tied together. So we come back to the X-ray stack. And now you'll see that once the Beanstalk environment is created, then the stack as a whole has been created. So if we come out to resources, let's take a look at our Elastic Beanstalk application. So we can click the physical ID. It'll bring us right into Elastic Beanstalk, and we can take a look. And so we have our environment name, we have our URL. So if we click the URL, it brings us to our sample application. This is an AWS sample application that simulates sign-up. So if we click Start and Stop and Start and Stop, just to generate a few requests so we can see something come into X-ray. And we come out of there and we can come back into X-ray, and we should start seeing some traces going. So you can see the URL that was hit, the average response time, the percentage of traces. And if we come up to the service map, we can generate a service map based on the traffic that we generate. We can get the insight into our application. That's the beauty of X-Ray. So we can see our client, right? We can click the client. You can see the source and destination, the response status. Then it comes into your Elastic Beanstalk environment, right? So you get a little bit of statistics about each one. And the Elastic Beanstalk goes to the startup signups table in DynamoDB, and it also sends an AWS SNS message to a new signup topic. So for instance, if we're having issues with one of our applications not sending stuff to SNS, right, we can come in here and we can use these traces to really see what's going on. We can dig in and drill down and look at the duration, how long it took, the page rendering, how long that took, right? So X-Ray, and then you also have the raw data as well. So X-Ray gives you a beautiful service map, right? That really maps out your application. And you can imagine this is a simple application, but if we have multiple more and more services, then this service map is going to be very well integrated and very well used for any troubleshooting that we need. So the key steps are to integrate your application to use the X-Ray daemon, spin up a CloudFormation stack with an Elastic Beanstalk environment that you want, create your X-Ray roles and policies, and launch your stack. And from there, your X-Ray daemon should collect that trace data and start sending it to X-Ray where you can see your map. Right? We can filter by different times. We can come back down into traces again. If there are more traces, every time we hit the website, we're going to get another trace. Right? So get in, instrument your application for X-Ray, and then fire up a Beanstalk environment and play around and even add more services so you can see even more interactions between the two. So I hope this video helped you understand how X-Ray can be utilized in Elastic Beanstalk using a CloudFormation script. Now let's discuss AWS CloudTrail. CloudTrail is a fully managed service that's used to continuously monitor and record every single API call in your AWS organization, and then stores them in long-term storage in Amazon S3. It'll provide logs to troubleshoot, resolve issues, and verify compliance, such as HIPAA compliance, for example. AWS CloudTrail events. We have multiple CloudTrail events. So CloudTrail event is any single API activity in an AWS account. So it could come from multiple services. It could come from something like an IAM user. It could come from an IAM role applied to an EC2 instance. Or it could be from an AWS service. So we're going to monitor every API call from every user, every role, and every service. So what types of events are we talking about? Well, first we have management events. So they'll give you insight into operations. So, for example, who attached a policy to a role, or who gave a IAM user a specific role. So management events, and they are really good. You need to see these. You may need to investigate something. You have data events. So gives you more insight on where data is being stored or extracted from in your AWS resources. So any get objects or put objects operations for S3, for example. And we also have global service events. So you can create some resources that are global services, like CloudFront and Route 53. Global services are logged as if they occurred in US East region. All trails created in the CloudTrail console for global services are delivered to an Amazon S3 bucket for the trail. So we've got management events, we've got data events, and we've got events for our global services. So what makes AWS CloudTrail actually work? And if you said trails, you are correct. If you need long-term storage of events for compliance, maybe it's HIPAA or the payment card industry compliance, right? You can store it in something like, say, S3. You can also have a trail that configures log files, and they can be stored to an S3 bucket or CloudWatch logs or even a CloudWatch event. So when you configure a trail, you can filter the events that you want to be delivered, right? So your trail is what kind of makes CloudTrail tick, right? It's a trail through your system, and it looks at the trail of the API calls, and it can store them or configure them as log files and store them in various places. In this video, I'm going to demonstrate how to create a CloudTrail trail that will help you create permanent records of all the API calls that are being used in your resources. So as soon as you come into the dashboard, you see recent events, right? So you can see a user named Tech created a bucket, right? User named Tech ran a delete VPC API. You can kind of pin down and take a look at even more details, what region, the time, the source IP, right? And we can also create a custom trail, right? So we've got a trail here. I can go ahead and create another trail, and I can call it Lambda trail. I want to put a trail on my Lambda function specifically, right? So do I need to apply trail to all regions, right? So that'll create the same trail in all regions. In this case, no, it only needs it in this region, right? Everything is going to be in North Virginia. We don't have any global events that we're going to actually need to create a trail for. So read-write events, I could have read-only, I could have write-only, I could have none. I want all read and write events. And I want to log all KMS events. So anything to do with the key management service, I want logged. We can also have insights, so that'll usually like catch fraudulent or unusual call volumes for writes, right? So it's kind of catching on to suspicious activity. We can also specify data events, right? They're records of resource operations performed on a resource, and we want to do it on a Lambda resource. So I'm going to call my Lambda function 2, and I want to create a trail on that Lambda function. So where do I want to store it? I can create a new S3 bucket, and I can call it Lambda Trails. There's more advanced features here like encryption, log file validation, or send a user SNS notification when a log file gets delivered. So I'm going to go ahead and click Create, knowing that my Lambda function is going to be trailed as a data event, and I'm looking at all the management events as well. So I come down and I click Create, and once it gets created, it'll be right alongside of our previous trails. So Lambda trails, once we go in, we can click the name. We can see all of our trail settings that we just selected, right? We're looking at the Lambda function for data events. We want all the management events, so this is all the same as what we did. We can also configure CloudWatch logs to monitor our trail logs, right? So we're kind of piggybacking into CloudWatch, right? Configure those logs that'll monitor the trail logs, and when a specific activity occurs, then CloudWatch can take action on that. So in this case, what I really need to do now is come over to Lambda and run my function. So I'll click it a couple times and test it, and then that should be enough. So if I come in over in S3 now, that's where our records go. So I'm looking at the bucket, and we said that Lambda trials tech is where we're going to put our Lambda trails. So I click AWS logs, gives me my unique number, gives me a digest, right? This is currently empty, but it also under the main cloud trail, it's breaking down by region. So if I click US East 1, then it breaks it down by year, month, and then day. And then you see all your trail sessions. So if I click the first one there, I can download it, I can open it, right? If I click open, I can see it. So it shows me the records. It says it's a type of IAM user. That user IP address is 47.55.50.58, and they have, this is their access key. I mean, it's all there everything that they did, the time, right? What API calls. So if we come back out and back in, we can come back and look at another one, right? We can open this. We can take a look. This was a much bigger. If you really need it for compliance, right, this is the tool for you. It's a lot of information, no doubt, but everything is there, right? You can see the event names like get bucket encryption. So if I type event name, we can go down and see all the API calls, right? So get account public access block. Here's the region. Here's the source IP. List buckets, get buckets. Every click we made is an API call. So it's going to log everything. Get account public access block, get bucket encryption, right? All the way down to get public access block, list buckets, everything that we clicked on in S3, we have an API record for it. List access points, get bucket policy status. So this is the beauty of CloudTrail, right? You can get a complete trail of everything everyone's doing with every click, because essentially every click is going to be an API call. So get in, play a little bit around with CloudTrail, create some trails of your own, and then just do some simple actions, and then go back and look through the trails and kind of trace yourself through that trail, and you can see how every API call is accounted for. Troubleshooting and monitoring on AWS. So in this course, we've examined a number of resources for troubleshooting and monitoring both applications and services on AWS Cloud. We did this by exploring the available resources for monitoring and troubleshooting on the AWS Cloud, how to work with metrics, alarms, events, and logs with AWS CloudWatch, how to create a CloudWatch alarm and a CloudWatch dashboard, how AWS X-Ray can be used to monitor, troubleshoot, and improve applications. We've also learned how to use X-Ray to collect application data, the use of AWS CloudTrail for monitoring and recording API calls and user activity, and how to create a CloudTrail trail to keep a record of events on AWS Cloud. In our next course, we'll move on to explore AWS tools and services for optimizing performance and efficiency, including AWS autoscaling and elastic load balancing, ELB.
In this video, we'll explore optimization in AWS Cloud. Optimization is concerned with optimizing resources and costs. The goal is to be as efficient as possible and minimize costs. To achieve our goal, we need a good strategy, and the AWS well-architected tool can help with our optimization strategy, helping us understand the pros and cons of the many decisions that we must make over resources in AWS Cloud. The well-architected tool is based on the well-architected framework, which defines key concepts, design, and architectural best practices for systems in AWS Cloud. The framework is focused on 5 pillars: security, reliability, operational excellence, performance efficiency, and cost optimization. Including these pillars as the foundation of our architecture makes it possible to generate optimized, stable, and efficient systems. Another option available for optimizing applications in AWS Cloud is tagging. By tagging AWS resources, we associate our own custom metadata with them. When tags are applied and activated, AWS appends this information to cost and usage reports. One type of useful tag is the environment tag. Tagging by environment allows us to clearly differentiate infrastructure. We know what resources are used by dev, which ones are used by test or production. We should also consider tagging by application ID, as this allows us to determine any AWS resources used by a specific application in order to effectively track costs. It also makes it easier to identify resources that can be turned off when no longer required for a project. Automation opt-in, opt-out is a tag type that can identify whether a resource should be included in specific automated activities like starting, stopping, or resizing instances. Another useful tag is the cost center or business unit that an AWS resource is related to. This is commonly used for tracking costs and planning. And the owner tag identifies the party responsible for the resource. Although this is typically the technical owner of the resource, we can have multiple separate owner tags. For example, we can have a technical owner and a business owner tag. The tag could be the respective owner's email addresses, which supports automated notifications. We can tag resources as we create them, and AWS also offers the AWS Tag Editor for managing tags, and AWS Config can also be used to identify any resources that violate our tagging policies. Optimizing means reducing AWS usage to reduce waste. An organization can establish a process to review consumption of AWS resources on a regular and consistent basis. We can use AWS monitoring tools to track resource usage and their related costs. With this information, we can then make confident, informed decisions to curb overspending, waste, and to reduce risk. For example, we should always delete unnecessary EBS volumes. When we stop an EC2 instance, it leaves any attached EBS volumes in an operational state, and so we incur charges for these volumes until they're deleted. We should also stop unused instances. We should consider deleting any idle resources. We should update outdated resources as a best practice. Updated resources are typically more efficient. We should also delete unused keys. Each customer master key created in Key Management Service incurs a cost until it's deleted. We should consider deleting old snapshots, for example, those more than 30 days old. Right sizing involves matching instance size and type to performance and capacity requirements, while at the same time minimizing costs. Effective right sizing is an ongoing process since performance and capacity requirements typically change over time. Resources can sometimes become underutilized or even become idle. We start by deciding the use case for our workload. This involves monitoring performance and identifying patterns of usage and applying the most efficient but practical resources and services. For example, a steady state load remains constant over time. Demand is relatively easy to forecast. In this case, use reserved instances for substantial savings. Sometimes the load is variable, but predictable. So the load does change, but it does so predictably. For this, we should consider using auto-scaling. The environment may also impact right sizing. For example, dev resources are typically scaled down versions of production, and dev, test, and production environments can sometimes be turned off after hours. Then there are temporary workloads that have flexible start times and can withstand temporary interruptions. These are excellent candidates for spot instances rather than on-demand instances. Right sizing also means selecting the right instance family when launching an instance. Each instance family has different compute memory and storage capabilities, and so we need to choose the most appropriate one for our workloads. For example, if we have a compute-intensive workload, then it just makes good sense to go with a compute-optimized instance type rather than one that is storage-optimized. Another consideration is using instance reservations. EC2 instance reservations offer various purchasing options which allow us to optimize costs based on our own organization's requirements. EC2 reserved instances give us the option to commit to usage parameters. We can save as much as 75% on hourly rates over on-demand's hourly rates by committing to a 1 or 3 year duration at the time of purchase. And there are flexible payment options as well. So reserved instances can include a no upfront payment, partial upfront, or all upfront payment. Amazon reserved database instances are essentially discounts related to instance type and AWS region. Reserved instances can reduce costs by up to 69% over on-demand when used with steady-state workloads. Amazon EC2 Spot instances provide spare compute resources at very discounted rates compared to on-demand instances, saving up to 90% in fact with certain workloads. We can use Spot fleets to automatically request and manage multiple Spot instances to get the lowest price per unit of capacity. Amazon EC2 fleets allow us to provision compute capacity across different availability zones, instance types, and across on-demand, reserved, and spot instances to help achieve scale, performance, and cost optimization. With spot instances, we specify a maximum price, and if the spot price exceeds the max we set, or when capacity is no longer available, our instance can be stopped, hibernated, or terminated automatically. To help us track and control spot instances, we use features like termination notices, persistent requests, and spot block durations. So for example, if we require that some process completes before a spot instance is terminated and reclaimed by AWS, for example, say we have to save state, then we can use termination notices. These are issued 2 minutes before interruption. Our applications running on spot instances should be designed to poll for a termination notice at very frequent intervals, for example, 5-second intervals, leaving the application almost 2 full minutes to complete any required processing. We can also make persistent requests. In this case, we set our request to remain open, and that way when an instance is interrupted, a new one is launched to replace it. We can launch spot instances with a fixed block duration of 1 to 6 hours. Spot instances launched this way are not interrupted due to changes in spot price. Now, to minimize the impact of interruptions on our applications on spot instances, the applications themselves must be designed for this type of environment. For example, we could implement checkpoints in our code to save our work periodically to an Amazon EBS volume. Alternatively, we could also design our application in such a way that we can split up the work and integrate Amazon Simple Queue service to queue up work increments and to track work already completed. In this video, we'll explore AWS autoscaling. We can use AWS autoscaling to scale our workloads. Autoscaling can automatically increase the number of resources when demand spikes in order to maintain optimal performance, and scale back or decrease capacity when demand scales back down. AWS autoscaling is excellent for applications with stable demand patterns and applications encountering hourly, daily, or weekly usage variations. We've just discussed how we can use autoscaling to scale capacity up or down. Now, this scaling is based on conditions that we define. Typically, autoscaling is used with elastic load balancing to distribute incoming traffic across multiple Amazon EC2 instances in an autoscaling group. Autoscaling uses scaling plans with policies defining how we want the scaling to happen, along with CloudWatch metrics and alarms that trigger the scaling events. The auto-scaling service includes dynamic scaling, which automatically increases or decreases capacity based on load or other metrics. Scheduled scaling allows us to scale applications in anticipation of known load changes. For example, setting up specific business hours or in typical dev test environments that only run at specific times. Fleet management capabilities mean automatically replacing unhealthy instances, maintaining our fleet at our desired capacity, and balancing instances across availability zones. We can provision and automatically scale instances across purchase options, availability zones, and instance families. And a golden image is a snapshot of the state of a resource, like an EC2 instance or an RDS database instance. This allows us to customize an EC2 instance and then save its configuration to an Amazon machine image. We can then launch as many instances as we require from the Amazon machine image, and all of those instances will include the customizations that we made. A golden image used in this way means quicker start times, and it also eliminates dependencies on configuration services or third-party repositories. This is crucial in autoscaled environments where we need to respond to changes in demand quickly and reliably. Now, consider DynamoDB autoscaling. This is a good example of an autoscaling scenario involving a web application experiencing variable traffic over the course of the day. Say we use a standard 3-tier architecture using elastic load balancing to distribute incoming traffic, using EC2 instances for the compute tier and Amazon DynamoDB for the data tier. In this scenario, autoscaling scales one or more EC2 autoscaling groups and DynamoDB tables in response to the changes in demand. DynamoDB can leverage the autoscaling service to adjust provisioned throughput capacity dynamically in response to real traffic patterns. This way, a table or a global secondary index can increase its provisioned read and write capacity in response to sudden spikes in traffic without throttling. When the workload scales back again, autoscaling dynamically decreases throughput, so we avoid paying for unused provisioned capacity. Amazon Aurora automatic scaling can dynamically scale the number of Aurora replicas provisioned for an Aurora DB cluster. Aurora automatic scaling is available for Aurora MySQL and Aurora PostgreSQL. With Aurora automatic scaling, our Aurora DB cluster can scale to handle sudden spikes in connectivity or workload. When the demand slows down again, Aurora automatic scaling automatically removes unnecessary replicas. So here again, we avoid paying for unused resources. For accessing AWS autoscaling, we have several options. We can configure autoscaling through the AWS Management Console, and we can also leverage autoscaling using the AWS CLI. The CLI has many commands that we can easily use with EC2, with CloudWatch, and with Elastic Load Balancing. We can also configure autoscaling using the AWS SDKs, and when we want to scale AWS resources other than EC2 resources, we can take advantage of the Application Autoscaling API to define scaling policies for scaling AWS resources automatically or by scheduling one-time or recurring scaling actions. In this video, we'll explore AWS Elastic Load Balancing. Elastic Load Balancing distributes incoming traffic across multiple targets, like for example, EC2 instances, containers, and IP addresses in multiple availability zones. Elastic Load Balancing automatically scales as traffic changes for almost any workload. It also checks the health of instances to ensure that traffic is only sent if the target can reply to requests. With Elastic Load Balancing, we configure one or more listeners for our load balancer. A listener is simply a process that accepts connection requests. The listener is configured with a protocol and port number for connections from the clients to the load balancer, and similarly, it is configured with a protocol and port number for connections from the load balancer to the targets. Elastic Load Balancing supports three types of load balancers. Application load balancers support layer 7 and are particularly well suited for microservices and container-based applications. Network load balancers are on layer 4 and forward TCP and UDP traffic with lower latency than application load balancers, so more oriented for extreme performance. Classic load balancer is the older generation, and it supports TCP layer 4 and layer 7. One key difference is how the different load balancer types are configured. For application load balancers and network load balancers, we register targets in target groups and then route traffic to the registered target groups. With classic load balancers, we register instances with the load balancer. To access Elastic Load Balancing, we can create and manage our load balancers in the AWS Management Console, the AWS Command Line Interface, various AWS SDKs, and the Query API, which provides low-level API actions that we can call using HTTPS requests. When enabling an availability zone for a load balancer, Elastic Load Balancing creates a load balancer node in the availability zone. AWS recommends enabling multiple availability zones. In fact, with application load balancers, it's a requirement. With this type of configuration, we can be sure that the load balancer will continue to route traffic if an availability zone becomes unavailable or has zero healthy targets. Under such circumstances, the load balancer routes traffic to healthy targets in another availability zone. When cross-zone load balancing is enabled, each node distributes traffic across the registered targets in all the enabled availability zones. And when cross-zone load balancing is disabled, each node distributes traffic only across the registered targets in the availability zone that it's located in. With application load balancers, cross-zone load balancing is always enabled. With network load balancers, cross-zone load balancing is disabled by default, but after it's created, we can enable or disable cross-zone load balancing whenever we want. With a classic load balancer, the default for cross-zone load balancing depends on how the load balancer is created. If using the API or the CLI, cross-zone load balancing is disabled by default, but in the management console, it's enabled by default. But we can enable or disable it once created at any time. With application load balancers, the load balancer node that receives the request evaluates the listener rules in priority order to figure out which rule to apply, and selects a target from the target group for the rule action, and uses the routing algorithm configured for the target group. The default routing algorithm is round robin. With network load balancers, the node receiving the connection uses a process whereby a target is selected from the target group for the default rule using a flow hash algorithm, and routes each individual TCP connection to a specific single target for the life of the connection. With classic load balancers, the load balancer node receiving the request selects a registered instance using the round-robin routing algorithm for TCP listeners and uses the least outstanding requests routing algorithm for HTTP and HTTPS listeners. When creating a load balancer, we choose whether we want it to be an internal load balancer or an internet-facing load balancer. The nodes of an internal load balancer only use private IP addresses, and they can only route requests from clients with access to the VPC where the load balancer resides. For an internet-facing load balancer, the nodes have public IP addresses, and the DNS name of an internet-facing load balancer is resolved to the public IP addresses of the nodes. So internet-facing load balancers can route requests from clients over the internet. And note that when you create a classic load balancer in EC2 Classic, it must be an internet-facing load balancer. Also, since both internal and internet-facing load balancers route requests to targets using private IP addresses, our targets do not require public IP addresses to accept requests from an internal or an internet-facing load balancer. In this demo, we'll create and configure an application load balancer. Okay, to get started, I've opened my browser, navigated to the EC2 dashboard. In the left nav menu, I'll scroll down and I'll click Load Balancers. And I'll click Create Load Balancer. Now we're going to create an application load balancer. Our application load balancer will work with HTTP and HTTPS traffic. Now I'll click Create. And for the name, I'm just going to call my application load balancer Demo ALB. It is an internet-facing load balancer. The IP address type is IPv4. Scrolling down, the load balancer protocol is HTTP, and that's port 80. Now for availability zones, I'm going to click the down arrow beside the VPC that is currently selected, and I'll select my default VPC. And for the availability zones for our load balancer, I'll specify all 3 availability zones. Scrolling down, I can choose add-on services like create an accelerator. I won't do that at this time, so I'll just click Next, Configure Security Settings. I won't do anything here. I'll just click Next, Configure Security Groups. And now for security group, I'm going to choose the Apache group because that allows traffic over port 80. I'll click Next, Configure Routing. And now for the target group, I'm going to give my target group the name ALB Target Group. The target type is instance. The protocol is HTTP and the port is 80. For health checks, again, HTTP, and the path is just /. If I expand advanced health check settings, scrolling down, I can change these settings. I think they're fine for now, so I'll just leave them as is, and I'll click Next, Register Targets. So now we have to register targets for our target group. So scrolling down, I'll see that I have 4 instances available. I'm going to choose the instances prefixed with LB, which is load balancing. It's just a prefix that I gave it for this demo. So I'll select all 3, and now I'll click Add to Registered. And now these are added to my registered targets. So now I'll click Next Review. Everything looks good, so I'll just click Create. and close. And this brings me to the load balancer console, and the state currently is provisioning. While we're waiting for the provisioning to complete, I'm just going to grab the bottom pane and make it a little bit larger by pulling it up. And scrolling down, I can see the description for my ALB. Under listeners, I have my ALB target group. I can drill down into the target group from here. I can view and edit rules as well. Also under the monitoring tab, I've got some monitoring metrics that I can review. I can also configure alarms from here. Under the integrated services tab, this is where my integrated services are located. And of course, under tags, I have my tags. But I haven't added any tags to this load balancer, so I'll just leave that as is, and I'll click on description one more time. Now let's go up and refresh. So I'll click the refresh icon. When the state changes to active, then I can copy the DNS name and I can open a new browser tab and paste the DNS name into the address bar and confirm that my load balancer is working. Okay, and now it reports as active. So I'm going to go down, I'll click the copy icon beside the DNS name. I'll click the plus icon to open a new tab, and I'll right click and select paste and go. And each time I refresh, I see a different IP address, and this is how it should work. This is balancing the load across my targets. Awesome. So we've successfully created and configured an application load balancer in AWS Management Console. In this demo, we'll create a launch template. When you create a launch template, you're creating a template that includes the necessary parameters required to launch an EC2 instance, like the ID of the Amazon machine image, the instance type, security group, user data, and so on. Once a template is created, we can reuse it, we can share it, and we can launch instances with it at any time, including using a template as the source for creating an auto-scaling group. Okay, to get started, I've signed into AWS Management Console and I've navigated to my EC2 dashboard. And we'll find launch templates under instances in the left nav menu. Also, scrolling down, you'll also find launch configurations. Now, launch configurations is the older standard, and AWS recommends using launch templates instead. Okay, so scrolling back up, under instances, I'll click launch templates. And now I'll click create launch template. And first, to get started, I'll give my template a name. I'll go with my template. We can also specify a template version description, but that's optional, and we won't do that at this time. Now, there's also an option for auto-scaling guidance. So if you click the checkbox under auto-scaling guidance, this will provide guidance to help us set up the template so that we can use it with EC2 auto-scaling. We also have template tags, so we can apply tags to our template. And we can also choose a separate source template. We're going to create a new one, so I'm just going to pass those two configuration details. And scrolling down, I'll choose an Amazon machine image, so I'll click the down arrow. Now I'm going to take the Amazon Linux 2 AMI. Now for instance type, I'll click the down arrow, and in the search field, I'll type T2, and I want to go with T2 Micro. It's free tier eligible. Scrolling down, need to choose a key pair in order to SSH into the instances. So I'll select my key pair. We have our network settings. So I'll leave virtual private cloud selected. We're not going to launch into EC2 Classic. And for security groups, click the down arrow. And I'll choose my Apache group. That allows traffic in over port 80 for HTTP requests. Next, we configure storage volumes. We'll just leave the default. And we can also provide tags or supply tags to the resource itself, but that's optional. We'll leave that out for now. We can also specify network interfaces. Now, here's the thing. If you click Add Network Interface, you'll see that network interfaces and instance-level security groups cannot be specified together. So because we've specified an instance-level security group, we're not going to specify a network interface. We don't have to. So I'll click Remove. And I'll click Advanced Details to expand Advanced Details. Here we have options for requesting spot instances. We can specify an IAM instance profile, so clicking the down arrow here, for example. So I can select S3 Full Access, which is a profile that I created earlier that allows full access over S3. We don't have to do that at this point, so I won't. Notice that shutdown behavior and stop hibernate behavior are both grayed out, and that's because they're not applicable for EC2 autoscaling. So this is part of the assistance in helping create this template that can be used for autoscaling. Okay, now we can specify termination protection, CloudWatch monitoring, elastic GPU, and a number of other configuration details. But we won't do anything there. However, we will specify some user data because we want to bootstrap from this template into a web server. So down on the taskbar, I'll click the Visual Studio Code icon to bring up Visual Studio Code, and I've got a file named userdata.sh open. I'll include this in the downloads for this video. So basically what we're doing here is just updating all the packages, installing Apache, enabling it, and setting up the security, and then creating a bootstrapped message so that we know that it actually works and we can distinguish the different machines from each other. Okay, so I'll place my mouse in the editor. I'll press Control A to highlight everything, Control C to copy. Let's go down to the taskbar and we'll click the browser icon again, and in user data, I'll right click and select paste. Okay, so there's our user data, and now our template configuration is done. Now, one other thing, a launch template does let you configure the network type as we just saw, the subnet, also the availability zone. However, these settings are ignored in favor of what is specified if you're using an auto scaling group. So let's click Create Launch Template. Okay, and we're done. So click View Launch Templates. And so now I've successfully created a launch template. So now if I click to select the launch template, if I click Actions, I can launch an instance from the template. I can modify the template. I can delete it from here. I have a number of other options. I can delete the template version because I can have different versions as well. I can set the default version, manage tags, create spot fleet, create an auto scaling group, and view details. I'll click Launch Instance from Template. And I'm going to specify the number of instances. It's just going to be one. I'm going to use the default template version. We only have one at this time. Under Instance Details, I have some other options that I can select. So we'll, for example, choose the key pair name. I'll choose EC2-key pair-Ohio. The network settings will leave at their defaults from the template, and we'll click Launch Instance from Template. Okay, and now I'll click View Launch Template. And now over in the left nav menu, I'll click Instances. Okay, and to see that the instance that I just launched with my template is now coming up. So the instance state is pending. Now once the state reports running, we should be able to confirm by opening a browser and navigating to the public DNS for this instance. All right, so the instance state now reports running. So I'll click to select my new instance. And under the description tab, I'll click the copy to clipboard icon to copy the public DNS to the clipboard. Now I'll click the new tab icon to open a new tab. And in the search with Google or enter address field, I'll right click and select paste and go. And there we go. So we see the bootstrapped message and the IP address for this instance. Okay, so we've successfully created a launch template and confirmed that it works. In this demo, we'll create and configure an auto-scaling group. Okay, I've signed into the AWS Management Console, and I've navigated to my EC2 dashboard. First, a couple of things that I'm going to do for this demo. I need to deregister some targets from a target group because we're going to be using the application load balancer that I created earlier. So let's scroll down in the left nav menu, and under load balancing, click target groups. So I'll click on the target group the ALB target group to go into the target group, and I'll click the Targets tab. So I've got 3 registered targets here. I'm going to click the checkbox to select all of them, and then I'll click Deregister. Okay, so we've successfully deregistered 3 targets. Okay, so I'll close the notification. Autoscaling groups use launch templates or launch configurations. I've got a launch template that I'm going to use because the launch template is the new standard, and we should move to the new standard anyway. Okay, so let's have a quick look at that launch template. So again, over in the left nav menu, under Instances, click Launch Templates. So this is my launch template. If I drill down into my launch template, I can look at the details. I can look at the different versions. I only have one version at this time. Let's return to Details. So I'll click on the Details tab again. Within the Launch Template Version Details, I'll click on the Advanced Details tab. If I expand spot purchasing options, I'll see that there is really nothing here because I haven't enabled spot purchasing options. But scrolling down at the very bottom, here's what I want to look at, the user data. I'm creating a web server, basically. I'm updating all the packages, installing Apache, setting up the security, and then creating a bootstrap message. Okay, so that's the launch template that we're going to use. All right, again, over in the left nav menu now, let's scroll down and click Auto Scaling Groups. And I'll click Create an Auto Scaling Group. And my auto scaling group is going to be named Demo ASG. Now I'll scroll down. Here's where I select my launch template or launch configuration. So I'll click the down arrow for the launch template, and I'll select My Template. Okay, and now we can choose a version. I only have one version, so I'm not going to actually do anything with that. So I'll keep on scrolling down and I'll click Next. Okay, so now we have, in step 2, Configure Settings, we choose the purchase options and instance types first. So we can adhere to the launch template, which is the default, or we could combine purchase options and instance types. And this is really valuable when you want to optimize scale and cost for a fleet of instances. Okay, but we'll leave the default adhere to launch template. Okay, and now for network, we have the default VPC chosen. I'll leave that selected. Now for subnets, click the down arrow, and I'll choose all 3 subnets that I want to launch my instances into. Now scrolling down, click Next. And now in step 3, configure advanced options. So here we can enable load balancing, and we'll go ahead and do that. So I'll click the Enable Load Balancing checkbox. And we're going to use an application load balancer. So I'll leave the application load balancer or network load balancer option selected. Now we'll choose a target group. Now recall that I went into my target group earlier and deregistered some targets. So let's click the down arrow and choose the ALB target group. Now for health checks, by default, autoscaling groups use Amazon EC2 status checks. And when an instance fails a health check, Amazon EC2 autoscaling automatically terminates it and replaces it with a new one. If using a load balancer like we are, Amazon EC2 autoscaling gracefully detaches the impaired instance from the load balancer. It then launches a new instance and attaches it to the load balancer. And this is all done automatically. So I'll check the ELB checkbox. And scrolling down under additional settings, I can enable group metrics collection with CloudWatch. I'm not going to do that at this time though, so I'll click Next. Now our group size. Our desired capacity will say is 1, and the minimum capacity is 1. And we'll say that the maximum capacity is 2. Okay, now scrolling down, scaling policies, this is optional. We can set up a scaling policy to dynamically resize the auto scaling group. We won't do that in this demo, so I'll leave none checked. Now we can also enable instance scale-in protection, and this is optional. We won't enable it, so let's click Next. Now we can also add notifications if we want to. We won't do that at this time. Click Next. We won't add any tags, so again, click Next. And now review. Everything looks good. And let's click Create Auto Scaling Group. Okay, so the auto scaling group was created successfully, and now the status indicates updating capacity. So I'm going to close the notifications. Right now, our auto scaling group is provisioning an instance to meet our desired capacity. So now in the left nav menu, I'll click Instances. Okay, in the first instance at the top of the list, that's the instances being provisioned by our auto scaling group. And under status checks, it reports as initializing. Okay, so we've successfully created an auto scaling group based on a launch template. In this demo, we'll schedule an AWS auto scaling action. Okay, to get started, I've signed into AWS Management Console and I've navigated to the EC2 dashboard. In the left nav menu, I'll scroll down and I'll select Auto Scaling Groups. Okay, and I have one auto scaling group. I'll click to select it, and now I'll click the Automatic Scaling tab. Okay, so here we have a couple of options. We have the scaling policies that we can set up. So if I click Add Policy, I can specify a policy type. Now with target tracking scaling, we select a scaling metric and we set a target value. Amazon EC2 auto scaling automatically creates the CloudWatch alarms that trigger the scaling policy, and it determines the scaling adjustment based on the metric and the target value. If I click the down arrow here, I have a couple of other options as well. I have step scaling and simple scaling. With step and simple scaling, we select the scaling metrics and threshold values for CloudWatch alarms that trigger scaling, and what scaling actions to apply when a threshold has been exceeded. However, AWS strongly recommends using a target tracking scaling policy based on metrics like average CPU utilization or the application load balancer request count per target metric. Okay, so we won't set up a policy. I'll just click Cancel. Now we'll create a scheduled action. So scrolling down, I'll click Create Scheduled Action, and I have to provide a name. I'll call this Demo Scaling Action. We need to provide at least one value for desired min or max. For desired, I'll specify 2. For min, 1. For max, 2. And for recurrence, we're going to select once. But if you click the down arrow, you'll see that you can specify a cron alarm. You can specify a recurring action every 5 or 30 minutes, hour, daily, or weekly. We'll leave the recurrence at once. Okay, now for the start time, we specify the date. So I'll select today's date, and we have to specify the start time in UTC. Now UTC is Coordinated Universal Time, and right now it's 10:19. So if I specify 10:20, then the scaling should take place at 10:20. And I'll click Create, and a notification appears telling me that the scheduled action created or edited successfully. Okay, now over in the left nav menu, I'll click Instances to go to the Instances page, and I'll refresh until the new instance from the auto scaling action appears. Okay, and the new instance has been started and is initializing the status checks at the moment. Now, over again in the left nav menu, let's go back and look at our auto scaling groups again. So I'll click Auto Scaling Groups, and I'll drill down into my auto scaling group by clicking on it. Now if I click the Activity tab, scrolling down, I can see the activity history, and it tells me that a new EC2 instance was launched at the prescribed time. And it tells us that the capacity went from 1 to 2. All right, so we've successfully created an AWS auto scaling action. In this video, we'll explore AWS storage optimization. Different AWS storage services are optimized for different storage scenarios because the reality is that there is no single data storage option ideally suited for all workloads. So when we evaluate storage requirements, we must consider the various data storage options for each workload separately. In order to optimize storage, we must understand our workloads. So we'll perform an analysis to understand input-output operations per second, or IOPS, throughput, durability, sensitivity, size, and budget. Amazon offers three classifications of storage services. There's object storage, block, and file storage services. Each is designed for a specific storage requirement. First, let's consider object storage. Amazon S3 is highly durable, general-purpose object storage that is excellent for unstructured data sets, like, for example, media content. There are various storage options in S3. First, there's standard. This is the best storage option for frequently accessed data, delivering low latency and high throughput. Typical use cases include dynamic websites, content distribution, and data analytics. Then there's Amazon S3 Standard Infrequent Access. This storage option is used for data that is accessed less frequently, obviously, like long-term backups and disaster recovery. This option provides less costly storage over time, but has higher charges for retrieving or transferring data. Amazon S3 Intelligent Tiering is a storage option designed to optimize costs by moving data to the most cost-effective access tier automatically without impacting the performance of our application. Amazon One Zone Infrequent Access is a storage solution offering a lower cost option for infrequently accessed data that requires quick access. The data is stored in just one availability zone and can save up to 20% of storage costs as compared to standard infrequent access. A typical use case for this option is storing secondary backups of data that can be easily recreated. Amazon S3 Glacier is designed for long-term storage of infrequently accessed data like end-of-life cycle, regulatory, or compliance backups. Retrieval can take from a few minutes to several hours. Amazon S3 Glacier Deep Archive is the lowest cost object storage class designed for long-term retention of rarely accessed data. Data is retained for 7 to 10 years and may be accessed once or twice a year. When the data is needed, we can retrieve it within 12 hours. Deep Archive is ideal for maintaining backups of historical compliance or regulatory data and disaster recovery backups. Amazon Elastic Block Store, or EBS volumes, are durable block storage volumes to use with EC2 instances. We use EBS for data requiring long-term persistence and quick access. There are two types of block storage: solid-state drive and hard disk drive storage. Solid-state drive storage is optimized for transactional workloads with performance requirements closely linked to IOPS. There are two solid-state drive volume options. First, there's general purpose SSD, and this is designed for general use and strikes a balance between cost and performance. Provisioned IOPS SSD is optimized for latency-sensitive workloads requiring a minimum guaranteed IOPS. With these types of volumes, we pay separately for provisioned IOPS, so unless there is a real requirement for high levels of provisioned IOPS, general-purpose volumes are more suitable. Hard disk drive, or HDD, storage is designed for workloads that are throughput intensive. For example, data warehouses and log processing. There are two types of HDD volumes: throughput optimized HDD, which are best suited for frequently accessed throughput intensive workloads, and cold HDD, which are also designed for throughput intensive workloads, but less frequently accessed than throughput optimized. Amazon Elastic File System, or EFS, is simple, scalable file storage used with EC2 instances. EFS is designed for workloads and applications like big data and media processing workflows, as well as content management and serving up web data. Both Amazon S3 and Amazon EFS allocate storage based on usage, and we pay only for what we use. But with EBS volumes, we pay for the provisioned or allocated storage, whether we use it or not. To keep storage costs low, then, we should maximize the use of Amazon S3 when possible, and only use the more costly EBS volumes with provisioned I/O only when our applications require it. Optimizing Amazon S3 involves identifying the appropriate storage class for our workloads and moving less frequently accessed Amazon S3 data to a less expensive storage class. For example, we can move data from S3 Standard to S3 Standard Infrequent Access and save as much as 60% per gigabyte. We can move data that's rarely accessed to Amazon S3 Glacier and save up to 80% over the cost of Amazon S3 Standard. Some of the tools that we can use to help determine when to move data to a different storage class include cost allocation S3 bucket tags, which can be used to track the storage costs or other criteria for specific projects or groups of projects. With Amazon S3 Analytics Storage Class Analysis, we can analyze storage access patterns that can help us decide when we should consider transitioning data to a more appropriate storage class. Amazon S3 Inventory is a tool that provides audits and reports on the replication and encryption status of S3 objects on a weekly or monthly basis. It generates CSV output files listing objects and their associated metadata, and it allows us to configure multiple inventory lists for a single bucket organized by different Amazon S3 metadata tags. And finally, Amazon S3 can also post storage, request, and other data metrics to Amazon CloudWatch. Storage metrics are reported on a daily basis and are also available at 1-minute intervals. Amazon S3 Select allows applications to retrieve only a subset of data from an object using simple SQL expressions. By using Amazon S3 Select to retrieve only the data needed by our applications, we can realize significant performance increases, in some cases as much as 400% improvement. Amazon Glacier Select allows us to filter directly against an Amazon S3 Glacier object by using standard SQL statements. To optimize storage performance and costs for EBS, we can monitor volumes to identify any volumes that are unattached or perhaps under or overutilized. We can then adjust provisioning to match actual requirements. There's also an opportunity to check our EBS volumes configuration. For example, for consistently best performance, instances should be launched as EBS optimized or enable EBS optimization after the instances are running. We should choose an EBS optimized instance, providing more dedicated EBS throughput than our application requires to also avoid performance bottlenecks. And also keep in mind that EBS volumes restored from snapshots must be initialized before the block can be accessed. And this takes time and can result in a significant increase in the latency of an I/O operation the first time each block is accessed. We can also use a RAID 0 array for a higher level of performance. We can use monitoring tools to help optimize block storage. For example, Amazon CloudWatch automatically collects a variety of metrics for EBS volumes, and we can then set alarms based on volume behavior. AWS Trusted Advisor provides another method to analyze our infrastructure and identify unattached or under or overutilized EBS volumes. Now, when unattached volumes are found, we should delete them. We should downsize or change the volume type of underutilized EBS volumes, and we should delete stale EBS snapshots. We can check for stale snapshots that are more than 30 days old and delete them to reduce storage costs. So in this course, we've examined how to optimize performance and efficiency of both services and resources in AWS Cloud using tools available in AWS. We did this by exploring the optimization of applications in AWS Cloud, how AWS autoscaling is implemented against scalable resources in AWS Cloud, how to create a launch template for a scalable resource, how to create an autoscaling group for scaling resources, and how to create a scheduled action for an autoscaling group in AWS Cloud. We also explored how load balancing is implemented using elastic load balancing, and how to use elastic load balancing to create an application load balancer in AWS Cloud. We explored key considerations in the optimization of AWS storage and databases, and best practices for performance optimization in AWS Cloud.